Check, check, 1 2 1 2 1 2. Randy, we're muted. Check, check, 1 2 1 2 1 2 1 2. Check, 1 2 1 2. Check, check, 1 2. Check, check, 1 2.
I just need to switch these.
I'm ready whenever you are. So what am I wearing? Am I wearing any mic or anything, or just using this one? Check, check. That's fine. Check sound. Check 1 2. Check, check, check. All right.
There are 1 million viewers listening to your presentation on YouTube.
All right, folks, good morning. It's 9 o'clock, at least by my watch. But we'll have a slow start. I'll make some housekeeping announcements, this and that, and we'll get underway in a few minutes. So first of all, a few logistics. We are in Ackerman Hall B17. Most of you know this. Some of you are new to this room. So facilities-wise, the bathrooms are right behind us. When we have coffee and other breaks like that, the coffee and things are over there on the left, to your right behind. And we'll be in this room all day today and all day tomorrow. If you want to stretch a little bit, go outside, take a walk. There should be campus Wi-Fi. Those who are not from JHU, GuestNet should work for you. It probably requires you to agree that you'll not engage in any criminal behavior and things like that. But as long as you agree to that, it's free, and so on and so forth, right? The other thing I want to tell you is the agenda. So today we're going to start in a couple of minutes, like I said. And I'll start off with a little introduction. To many of you, it'll be familiar. It's the kind of introduction I've been doing for many years about these workshops. After that, we will have 2 team presentations today. Each team presentation is roughly a 3-hour block. So the first team today is from 9:30 to 12:30, with a break in between to stretch your legs and recaffeinate if needed. And then we have a 1.5-hour lunch break, 12:30 to 2. And then second team is from 2 to 5, again with a short break in between. Now the break times are sort of notional in the sense that the teams will run their 3-hour block like you run a special session at a conference, and they'll take a break at some reasonable point in the middle. So people online don't count with the timing too much. We'll try to stick to the endpoints of each, but within that, there'll be a little bit of flex. And tomorrow's schedule will be similar, but shifted. So the first team is from 9 to 12, and then we'll do a break from 12 to 1:30 for lunch. The second team is from 1:30 to 4:30, and then we'll have a little closing session from 4:30 to 5. So both days it's 9 to 5, except on the first day, there's an opening thing in the middle, 3 hours lunch, 3 hours. And then tomorrow, 3 hours lunch, 3 hours, and a closing session. So tomorrow also we start at 9. Okay. The other thing is, for all those people who've been in the workshop and been here for 8 weeks, do put on your badges. We have a number of people who are coming in just for today, so it'll be nice when they mingle with you and talk to you for them to know your names. Most of our visitors should also have name badges for them. If you don't, there might be some blank ones, just put your name on it, just so people get to know each other, right? Okay. And if there are any logistical questions, ask them now. Otherwise, I'll get started with my presentation. Yes.
Maybe just at the very end, when we're going to be leaving to the military stuff, we're going to be any information on where to be fees.
We'll do that tomorrow, right? Okay, cool. So the question was about people who are checking out tomorrow, and these are the resident workshop people. Yes, we'll take care of that tomorrow. One important thing for people in the audience, unlike all the previous talks we were doing, this talk we have professional guys doing the recordings, and they request that you come up to the mic to ask your questions. So yes, it'll be a little bit of work, but just come up to the mics. That way they can get you as well in addition to the audio. So again, speakers use this mic. It is both for the room and for the online streaming people. Audience use this mic for questions. We do have a second mic, and if there are too many questions, we'll start 2 parallel sessions with quick questions and go from there. But questions are very much encouraged. In fact, the agenda doesn't quite show it, but each team, instead of preparing for 3 hours or 2 hours, 45 minutes, is actually prepared for half an hour less than that, and they have half an hour for questions built into their presentation time. So this is a time for lots of questions and discussions. So please, everybody, take advantage of that, ask lots of questions. This is an informal session, and we are not going to be very strict about when you interrupt. The speakers can control that. They can say, no, hold the question, I'll answer you later. Or they can say, questions are open, ask me anything, right? Okay. All right, so if that's all the announcements I have to make and there are no further questions, let's take a long breath and get started. It's a long day. It's going to be a long, productive day. All right. Welcome to the closing session of the 10th Frederick Jelinek Memorial Workshop. It is by some count the 30th or the 31st summer workshop in the series, but we've been calling it or naming it after Fred for the last 10 years, so that's why this one goes that way. I'm Sanjeev Khudanpur. I'm a faculty member here. I run the workshop along with my colleague Paula Garcia, who's sitting here in front of us. And this year, our co-conspirators in running the workshop are Antoine. Antoine is from Le Mans. He's not only a team leader, he's also responsible for a chunk of participants in this workshop who come through this project called Esperanto. And then, of course, Samir Khurana, who's sitting over here. John Wu, he's not here at the moment, but he'll be here in a minute. Marek Cruz, who's in the back over there, and Jason Eisner. These are the 4 team leaders who led excellent teams, did some fun work over here. So just to, again, this is a little bit of a repeat for those who have seen it, forgive me, but there'll always be new people in the audience, especially the online audience. So if you really want to understand how these workshops started, you have to actually go way back. And in the 50s, there's this place, the place is still there. It's called the Institute for Defense Analysis. It's in Princeton, and they've been having these summer workshops since the 50s. It started off with a bunch of people trying to work on code making, code breaking, the usual cryptography type of science. And their idea was bring a bunch of mathematicians together, lock them up in a room for 3 months or 2 months, and let them do beautiful math, right? So basically this idea was taken up, or it became viral, as they say. Sometimes I use viral analogies. I'm not sure if it's a good thing or a bad thing, but basically this virus jumped from cryptography to speech and language. And many people are credited with it, but it basically started in 1993 at Rutgers University. Tom Crystal, Arthur Howes, Kurt Boyles, many names are mentioned. The 2 people I associate most with it are Jordan Cohn on the left, your left, my right, and Jim Flanagan. They were at Rutgers at that time. They started it, and they said, oh, let's do this IDA Princeton-like workshops for summer. And they had another one in '94. And these workshops basically had the same formula: get a bunch of senior researchers, give them a nice place to work, give them some hard problems to work on and see what happens. Then in '95, the workshops moved to Hopkins. It started off with Fred Jelinek being hired away from IBM. Jelinek is a big name in the field, so many of you are too young to know this name, but you'll see his name in papers and things. He used to be at IBM. Hopkins managed to hire him away. He came here in '94. And then when he came here, the workshop sort of followed him and came here. And the first summer workshop was held at Johns Hopkins in 1995. So by that count, this is the 30th one in that series. If you count the 2 at Rutgers, it's 32. But if you drop the 1 because we didn't have one during COVID, then it's 31. So long tradition. One of the things that Fred did is until the Rutgers workshops, it was mostly senior people. There were a few PhD students, but it was mostly focused on senior researchers getting together. It was based a little bit like the Princeton model. But Fred said, no, grad students are where the action is. They're the ones with the good ideas. So let's have grad students. So grad students became integral to the workshop. In fact, you'll see in a minute that now they're a big portion of the workshop participants. And one of the grad students was me in '95, and somehow I just stuck around and I've been here for a while. Just to give you an idea, this is something I tell people just so that you have some perspective. Everybody's talking about large language models today. This was the focus of the '95 workshop. There were 4 teams, and every title, if you notice, has language model in it, right? So we've been working on this topic for a while. So no, language models weren't invented by whoever at Google or whatever it is that you think about. Okay. In '96, '97, the workshops continued. And every year the formula was there were 3 or 4 teams, about 15, 20 senior researchers, 15, 20 grad students, or roughly 40 people. And one of the things that Fred did is he said, oh, after graduate students, he says, let's get undergrads. And there's a little funny saying, this is not Fred's quote, but this was one of our university presidents many years ago, and maybe he got it from somewhere else. What's the idea of bringing undergrads into a team, right? Well, the undergrads, they don't know anything. So there are these commonly held beliefs in the field, oh, this can't be done, that can't be done. So put some undergrads on it. They don't know, they'll just do it. So basically we said, okay, let's bring undergrads in. And also the other reason was the National Science Foundation kept telling us, hey, we need to build undergraduate strength in computer science and applied math and so on. So we said, okay, let's bring undergrads, give them a flavor of research. So they became integral to the workshop starting '98. This is a picture, in case you want to know, a team led by Jan Heich, who is the leftmost in the picture for me, rightmost for you. And then there are two undergrads in here, Oren Schwartz, I think, he's the one with the dark glasses, and Cynthia Ko. I'll mention Cynthia in a minute. So she was an undergrad in '98. Others you might recognize sitting in the bottom right side for you, sorry, left side for you, right side for me, is Doug Jones. He's at MIT Lincoln Labs. Well, there are lots of standard names you might recognize. The other thing that the workshops did is they actually started new trends, new fields. So statistical machine, of course, nowadays everybody takes Google Translate for granted, neural translation's a thing. But in '99, there had been this one paper that started statistical machine translation, but it died because the people who worked on that paper all left IBM and joined a hedge fund. And so nobody kind of remembered how to do statistical machine translation or use their papers. So we put together a team, and that team was led by Kevin Knight, and it pretty much resurrected statistical machine translation in academia. The other thing that the workshops did is we've been looking at our neighboring fields, so although it's a speech and language workshop, already back in 2000, we were looking at audiovisual speech recognition and seeing if lip movements and other things can help a speech recognizer. So this combined computer vision and speech researchers into one team. The other thing that the workshops have done very well is there have been big breakthroughs. So yes, 6 weeks, 8 weeks is not a whole lot of time, but if you just measure what the teams did there and where it went afterwards, in a few weeks, in a few months, usually a couple of years, something really big comes out that you can trace back to the workshop, right? So Drago Radev led a team in I think in 2001, where they worked on multi-document summarization. And one of the de facto tools that people use in summarization, this is of course pre-LLM days, is called MEAD, and Drago built it. Philip Kuhn is known as the guy who wrote the book on machine translation, and then the guy who wrote the second book on machine translation. So he started his Moses work here at the workshop. iVectors came out of the summer workshop in 2008. The Kaldi speech recognition tools were born in this workshop, again in 2009. And these things became de facto things, standards in the field where everybody used them. So both breakthroughs and toolkits have come out of this workshop. Right? The other thing is, these collaborations with computer vision. I already mentioned the one in 2000 with Chalapati Nethi and audiovisual speech recognition. Then in 2004, we worked on image and video retrieval type of tasks. So at that time, people were starting to do text-based content retrieval from video. And this team was led by Giri Iyengar from IBM and Manmatha. Manmatha, for some reason, goes by only one name. He was at UMass at the time. Now he's in some lab 126. I don't know where. He's somewhere on the West Coast. So these guys led a team on, retrieving video and images using text queries. These are the precursors of CLIP, for example. They were trying to find common embeddings between images and text. And not just images and objects, then we went on to recognizing actions. So there was a team led by Jan Newman, who used to be at Comcast at the time, and Evelyn Zuckerman, and they worked on recognizing actions in videos. They had a cool idea. They used this PBS Sprouts videos, their cooking shows, and so there's a lot of action going on when you're cooking, and somebody's narrating what's going on. So fry the onions until they're brown, and there's frying, and there are onions, and there's a video, and there's a text, so they leveraged that to build models for action recognition in video. The idea about joint modeling of text and images went further. Tamara and Alex Berg are sort of known names in the field. They started their work. They had this cool demo at the end of the workshop where if you put up an image, the computer said something not quite perfect. It said something like, this picture has one man and one dog standing in front of one bench and drinking one lemonade or something like that. So because it used to count and try to figure out how many things there are. And so anyway. And then, of course, Andrea Vidaldi led a team in 2012 on detailed understanding of objects by studying their parts. I saw something very interesting just last week. So CVPR was there earlier in the summer, like a month ago, and there were 3 awards given at CVPR. One was for a best paper. Its author was Ross Gershich, who was a grad student in Andrea's team. And then Andrea got an award for some kind of big, major achievement, and he was the team leader. And this is today's CVPR. So you can see the arc of the workshops, things keep happening. And so all of you who are here, keep working. You're some of the best people working in this field. keep doing it and good things will follow. Right? Good toolkits will come out of it, groundbreaking research will come out of it, you'll get awards, all sorts of good things are going to happen. All right. The other thing we did is, the workshops, when they started in 95, for the longest time, they were always in Baltimore at Hopkins. Then we said, let's do something outdoors. Let's go somewhere else. So in 2014, for the first time, we took the workshop on the road, as I say. We went to Prague. Prague was also Fred's birthplace. Actually, not Prague. He was born in Kladno nearby, but yeah. So he is from Prague, or he considers himself from Prague. So we went there. Jan Haich hosted us. It was a great experience. So we said, okay, how about we do this every now and then? So roughly every other year, 2015, we went to Seattle. Mari Ostendorf and Les Atlas hosted us. 2017, we went to CMU in Pittsburgh. Florian Metza was our host. 2019, we went to Montreal. Patrick Cardinal and the guys at ETS hosted us. And then finally, 2023, we were in Le Mans, where Anthony Larcher and Antoine were our hosts. So we've been doing 1 year in, 1 year out. So now we're back in Baltimore this year. Okay. The workshops, of course, do many things. They create new science, they make breakthroughs, toolkits. The other thing they do, which is very important, is they create friendships, right? So if you look at this picture just for a minute, there are many people in this who met at the workshop and stayed friends for a long, long, long time after that. And by the way, one of the other things I claim credit for is Franz Ock. I say Google Translate minus minus. So the precursor to Google Translate started at Hopkins as well. And Franz then went from here to Google and actually started Google Translate. So basically, these people have become friends over years and they still collaborate. And in fact, one of our workshop collaborators, Dan Juravsky, was here this summer back to give us a talk and talk about things. He works with Anjali, who's sitting over there. Right. Undergrads was a success. Remember I mentioned Cynthia Kuo in that picture in 1998? She's now a professor of the practice at CMU West, as I like to call it, in Silicon Valley. Another undergrad, some of you recognize, he's a professor at UW, one of our own, Noah Smith. Again, started his NLP career as an undergrad at the workshop. David Kirsch, I was mentioning him to someone the other day. He's now the CTO of a medical informatics company. Rachel Rudinger is a professor down the street at the University of Maryland College Park, started NLP here at the workshop. So yeah, so overall adding undergrads was a success. But of course, this is not something we do only in the summer. It's a year-round thing. So let me just walk you through it. So we are right now at the bottom right corner of this, right? So we are at the point where the workshop is ending. The team leaders already know that we have to write final reports. And I and Paula and some of the other organizers know that we have to start preparing a call for proposals for next year's workshop. So what happens in September, the team leaders submit their final reports to us. We distribute the call for proposals, start asking people, hey, what do you want to do in summer 2025? And we solicit ideas, and we also go after money, because after all, funding all this requires somebody to loosen their purse and give us some money. The proposals usually come, by the way, they're very short, just one page. They come in the early or middle of October. We look at the ideas, we convene people, and then have a meeting. That meeting typically happens in November. And it's an interesting meeting. It's an interactive peer review. Unlike normal things, when you write a conference or a journal paper, they go to some anonymous reviewers, they vote you up or down. Here, you sit down with the reviewers, and they say, hey, I don't like this. You say, oh, okay, I know I can fix that. Or the reviewer says, have you thought about this? You say, oh, that's a good idea. Let me incorporate that. So we develop proposals interactively rather than just review them. We do vote on them at the end. We do try to evaluate proposals. So that happens in November. And this meeting has two purposes. One is to come with the ideas. The other is to come up with people who are going to lead the teams. Because we've discovered many times that it's very easy to say to somebody, this is a cool idea, you should work on it. And then you say, how about you? No, I'm going to do something else. No, if you really want the idea to work, be part of it. So we sort of pull team leaders out of this meeting as well. Usually the people who propose the ideas get together with others and say, okay, I'm going to lead this team, you're going to help me, and so on and so forth. So the teams start forming. By December, we try to nail down the funding. So this is a call to our sponsors for next year. By this December, we'd like you to tell us that you're going to fund us for next year. We finalize senior members over Christmas, New Year's, grad students over the next month by February. And in the meantime, we've sent out a call for undergraduates. We've asked people all over the country to apply. And then we select half a dozen. This time we went up to 10 undergraduates from around the world, and that we do by sort of mid-March. Another key thing in the preparation is that it's not just a summer thing, is that each of the teams meets at least once. We usually encourage 2 face-to-face meetings, day long, 2 days long, to try and start making real plans. Because as you know, in any research, you need to figure out what data you need, and wrangling data takes time. You need to build some baselines, as we like to call them, basically measure where the state of the art is in whatever you're trying to do. That requires time. Sometimes open source implementations are available. Sometimes you have to build it on your own. So you do all that in the spring. You have a second meeting. You look at where the baselines are. You look at where you want to be. You refine your problem definition. In fact, Samir will tell you his team's title changed twice between December and now. So, these are the kind of things you do. You refine your plans as you go and fix things and so on and so forth. And then finally show up in the summer. And even then, there's something before the real research begins. We have the summer school. So we wanted to bring, the summer school idea started actually when we first got undergrads. We said, oh, these students don't have enough background. What should we do? So we started putting together some lectures and labs for them to get up to speed with the grad students. And we very quickly realized that what we were putting together over a period of 2 weeks was, if you just count contact hours with the faculty and the labs and so on, it's a semester and a half's worth of coursework, all packed into 2 weeks. So I think this is what the executive MBA people do when they do their 2-week courses. They try to cram a whole week's or semester's worth of stuff into 2 weeks. So that's what we do. So then we opened it up, and now other students come to the summer school, and NACL actually supported us this year. I mean, they try to every year. Some years works out, some years doesn't. But the NACL is, of course, the North American Association for Computational Linguistics. So they supported the summer school this year. And then once that gets over, the senior people show up. By the way, there was another important reason to have the grad students come out 2 weeks ahead. We discovered very early that if you bring professors and students all together at once and say, okay, start research, then for the first week or so, the professors are just idling around while the students set up the infrastructure. And then the work begins. So I said, let's bring the students out ahead of time and get started. Okay, so I know you're laughing, but it's just, this is how you run a good workshop. You recognize what's going on and you work with it. All right, so then the workshop happens. So that's where we are. So 2024, we sent out the call back in September, like I said. We had October deadlines, planning meeting in November. You can see some of the topics. They're pretty broad. We just said we want things in speech, things in text, things in multimodal interaction, responsible HLT AI, the typical topics that, and we come up with these topics by interacting with the whole community, trying to figure out where we think. So the main ingredients we look for is it needs to be a pressing problem. There needs to be something new happening that makes us feel that we can make a dent in it now. And it needs to be something that will benefit from having people from multiple universities and multiple organizations and multiple disciplines, frankly. And you'll see examples of that when I tell you how it turned out this year. Okay. So for this year, we started the planning. We had about 34 people come to this meeting in November, mostly in person, a few were virtual. There were 6 initial topic ideas that we started with, and then the authors of those, which were mostly, most of those also came in person, some were virtual, so everybody got together. So this is the interactive part of the review, where the authors also come in. And then for 2 days, we just brainstormed ideas, critiqued the ideas, iterated over it, and so on and so forth. We had this voting system. It's based on this Cambridge single transferable board idea, which tries to build consensus around where everybody thinks the good ideas are. And then that ended up giving us 4 proposals or 4 topics. So the topics were in the order that we're going to present them today, not in any particular order, but just today's presentation order, was multimodal audiovisual transformers. And this team's name, like I told you, has evolved to now just be audio generative modeling, but that was the title back in when they proposed the idea. And it was led by Samir and Antoine, and their team has 5 senior researchers, lots of grad students, and a few undergrads. This is one of the teams that has industry participants as well. The other team is evaluating LLM performance in the context of research astronomy. This is one of the questions everybody's been asking. Can these LLMs really help science, scientific discovery, and so on and so forth? And this team looked at one aspect of that. It's led by John Wu from the Space Telescope Science Institute, which happens to be down the road from here. It has several senior members, a couple of grad students, 4 undergrads. The third team was on sign language translation. This is the team led by Marek from West Bohemia. It has 5 senior people, 6 grad students, 4 undergrads. And then finally, a team on AI curated democratic discourse. So this team is led by Jason Eisner and has 4 senior members, 3 grads, 3 undergrads. So these are the 4 teams that emerged. Not all of these were set in November, but they evolved, and by February or March, these were the teams that we ended up with. Just to give you a quick glimpse of what the team structure looks like. This year, like last year, we managed to touch 18 countries and all 6 continents. And like I said to someone the other day, I can't get these penguins to do speech and language, so Antarctica is going to remain a challenge. We have 22 men, 15 women, 26%. That's not bad, but we'll keep trying to push it to make it bigger, because the more diversity we have in our teams, the better ideas we tend to generate. This year, we have 4 people from industry. Usually this varies a little bit based on topic. Some years we've had up to like 30% industry people, or maybe 25, but it's kind of this is a hallmark of the workshops, that we do pick topics that even industry cares about, so that there's a lot of back and forth between academia and industry. And last but not the least, most people are actually here 6 weeks for the senior people, 8 for the students. A few people who are critical to the teams but couldn't come full time, I counted them as half-time or 1/3 time people, so that's about 57 total. In terms of academic preparation, about 1/3 of the workshop participants have PhDs, they're researchers, that's a yellow slice, it's roughly 1/3. Another 1/3, roughly the gray one, are PhD students. And then the remaining 2 are actually bachelor's and master's students. So in some sense, it's roughly 1/3 each. People who are doing PhDs, people who have PhDs, and people who are not yet doing PhDs. So it's a good mix of people. And like I said, there's a lot of energy from the younger crowd and a lot of wisdom from the older ones. And altogether, these make good teams. This year's summer school, again, we had a nice set of lectures and labs. We covered LLMs right away because we said, hey, that's the elephant in the room. Let's discuss it. Let's teach people about it. Kevin, Du, and a number of other people managed this tutorial. I talked about speech recognition, Jesus and others on speaker diarization. Philip, of course, who else, on machine translation. We had a lecture on social media. This was Jason's team essentially doing a team tutorial. And then we had information retrieval, which was both a tutorial and useful for John's team, as he might tell you later. We also had John give a tutorial on his team. This was actually a nice primer on what astrophysicists care about. So it was nice to hear their view on how LLMs, first of all, what their core issues are in the science, and then how LLMs are used for it. Florian came down from New York and gave us a tutorial on computer vision. This was tough though, because this year CVPR was actually in this week. So all my computer vision colleagues are away at CVPR, but Florian very kindly agreed that he wasn't going to CVPR, so he'd come down and do a tutorial. And then we had Marek talk to us about sign language and how sign language recognition stands currently in the field. And last but not the least, Samir and Antoine talked about neural audio language models and their team's work. So as you can see, it's a mix of basic stuff and what the teams are doing. And at the end of the day, everybody was sort of hopefully up to speed on what's going on. The rest of the 6 weeks was pretty packed. As you can see, there's something or the other going on every day. Mostly, I don't need you to read everything. There are a few highlights. One highlight is on July 11. We all went to eat crabs. Another highlight was July 13. We all went to see an Orioles game. That was really fun. I don't know how Ruth managed tickets for us because it was against the Yankees, but somehow we got in. And other than that, of course, we had a number of plenary lectures. Those are in green. One thing we do in the workshop is once a week we do a progress report. It puts a little bit of pressure on people to keep going and keep making progress. But more importantly, it helps you take stock of where you are, make course corrections, and so on. Okay. And so we started on Monday, June 24th, and we are now on August 1 at the bottom, almost right of that chart. So plenary lectures, we had Lale Akanur come and talk about human 3D models. So we learned a bit more about where computer vision is today, where the state of the art is, and how modeling humans in 3D is still a challenge. That's why most computer vision papers, if you see anything about humans, you see stick figures. So it's pretty difficult because human bodies are interesting to model from a computer vision point of view. But it's very important because if you want humans and computers living and working together, the computers need to have a pretty good idea what the humans are doing. Megan Ansdell from NASA came around and told us how LLMs are being used in space science. And she is a key member of the NASA, NASA headquarters, the Science Mission Directorate, I think it's called, SMD. And so she told us NASA's interest in LLMs. Gordon Weikern from Merle was here. He talked about audio source separation, more generally about generative audio models. Hanseok Ko came around from Korea University, and he talked about human-machine interaction and his recent work in building realistic 3D-like models for human-machine interaction. Deborah Matthews talked to us about governance of emerging technology. This was a lecture on policy and ethics, and she was explaining how it's hard for laws to keep up with tech and for lawmakers even to think about what to do with tech. So there's a very interesting and important field that we all need to be aware of, even though we might be more on the techie side of things. Alberto Akomatsi came around, told us about this nice project called the Astrophysics Data System, ADS. It's the system of record where a lot of astrophysics papers and data and everything lives. So it's a rich space in which to do NLP research. And finally, Dan Jarowski came along and talked about how NLP interacts with various social issues. So we had a nice spectrum of talks, made us think about where we are, what we're doing, in addition to the little research problem that we were preoccupied with most of the summer. So that was pretty much all the things that happened in the summer. Of course, tons of research happened. I only told you the non-researchy part. So Samir and Antoine will come up next. I'm short on time, so let me cut this short. They'll come up and tell you a little bit about their work in the audio generative modeling team, essentially thinking about how to create representations where you can have audio and text and speech live in the same space, how to work on vocoders to take those representations and generate speech, how to sort of make it possible to prompt these models with other cues than speech, namely text or images and so on. So you'll hear from Samir and Antoine and their team about that. You'll hear after that this afternoon from John and his team about research astronomy and LLMs. They'll talk about what astronomers want to do if you give them an LLM interface to archive of papers, what kind of questions they ask, what they expect, how they react to it, and also about how one should improve the retrieval pipeline so that the engine that's answering these questions can actually access the right papers, how to do retrieval augmented generation, and so on and so forth. So you'll hear about the interaction between astronomers and the archive that they work with. What's interesting about this group is that they have real live astronomers, not part of the team, who really want to do astronomy, who are using these systems to try and understand what they want to understand. And then you'll hear tomorrow morning from Marek's team about sign LLMs. This is a nice interdisciplinary project, many components to it. They've got the framework going, and you'll see how you can basically focus on the fine hand poses that you might get from a model-based analysis of the visuals, some more generic big open field view of the video, because nowadays everybody says, why do I need component models? Let me just throw the whole video stream at the LLM. Yes, there is information in the open space because sign language uses a lot of space around you, not just the hands. And the face, for example, is important. And then, of course, you need more direct visual cues of the hand itself. So these multiple modalities, even in sign language, multiple pieces of the signal need to be brought together. Evaluation is a big challenge because sign language is, it's not, you shouldn't say sign language transcription because there's no one way to transcribe what someone's saying. It's more a translation. So all the headaches of evaluating translation come into sign language evaluation as well. And in fact, they're a little bit more intense, as you'll see when Marek talks about how there are ambiguities and other things you need to address. Then last but not the least, we'll hear from Jason's team on democratic discourse. So this again involves orchestrating a social media platform where people who are interacting with each other, posting things, get a chance to have an LLM be their co-pilot, analyze what posts they're posting, figure out what other similar posts exist so that you can inform the user about what's already out there, analyze the user's posts as to whether they're asserting facts or opinions, show them things supporting their facts or things opposing their opinions, and then finally, how to evaluate this. So all sorts of issues having to do with, can you use AI to help people be more civil in their social media interactions? So these are the 4 teams. Again, we are now at the 9:30 mark, over by 5 minutes. Sorry about that. We'll continue with Samir and Antoine's team. We'll have a break in the middle for some time, continue with that till lunchtime, and after lunch, it'll be John and his team. So with that, let me stop. And while I'm asking Samir and Antoine to come up, let me see if you have any questions. I'm not expecting any, but you may still ask. Okay, if there are no questions, then all yours.
Thanks, Sanjeev. So hi everyone, welcome to the first presentation. We are the Universal Audio Generation team, and I am Samir Khurana. I work at Mitsubishi Electric Research Lab, and I'm the leader along with Antoine Laurent, who is in Limau University. So the goal is pretty simple. It can be summarized as this figure. So we want to build an audio generator that can be prompted on multimodal context that the user provides, and the model should be capable of generating audio that is contextually relevant. So several tasks can be performed by this model depending on what context the user inputs and what type of audio the model generates. So some common tasks that we are interested in is like text-to-speech synthesis, acoustic scene synthesis, spoken image captioning, and so on. In this workshop, we did not get to all these tasks. We mainly focused on building a model that can be trained in the future on all these tasks, but currently we focus on getting text-to-speech synthesis working. So this is the overview of our overall generative model. Oh, sorry. So this is an overview of our overall generative model, and individual teams will talk about the different components of this model more. But the way to read this model is from left to right. So the input to the model is multimodal, audio and text. Then there are respective tokenizers for these 2 modalities that convert these signals into discrete tokens. And depending on what tasks you want the model to perform, you have the token combination. So one of the sub-teams worked on building an audio compression algorithm that can convert audio into sequence of discrete tokens, and they will talk more about the technical details of their work. The other team worked on building a decoder-only language model, such as GPT or Llama, which can model the distribution over these discrete tokens. And this model is a multimodal, so it can model both text and audio tokens, and also generate both text and audio. Finally, the third team worked on multimodal representation learning, and mostly we were interested in how to translate visual modality, for example, into text-like representations that can then be used to prompt this audio-text language model. So here are the team introductions, and they will talk more about it in their presentation. But in the first presentation will be from the multimodal representation learning team, and we have here 4 PhD students and 1 senior member, Salima. And so from left to right, we have Antonio, Haroon, Hugo, and Tuan at the end, and there is Salima, second last. And for the neural audio codec, the team is pretty interesting, actually, mostly pre-PhD students, and only 1 PhD student here. But me and Antoine were quite involved in this project as well. And then the last presentation will be from the generative modeling team, and they'll show you how to build these decoder-only multimodal language models on audio and text tokens. So yeah, let's start with the first presentation. Sorry. We have some other collaborators as well who could not make it to the workshop because of some visa issues, but they are also working with me on generative modeling, and hopefully we can continue our collaboration in the future. In particular, we have Sadeen, Sarah, and Ahmed Ali, who is here for the final presentation. Okay, so now we can start with the first presentation, which is multimodal representation learning.
That way you can walk and talk.
So thank you, Samir, for the presentation. So I will be the opening for our team, the multimodal representation learning. So we have 5 members in our team, and I will be the first one to introduce our team. So a little bit of background. So as Samir already present, our team in charge of generate the meaningful information that can condition the decoder-only language model that can help to generate a better quality audio. In order to do that, we decide to train a multimodal transformer that can try to generate a meaningful representation, encapsulate different modalities, and in our case, it should be the speech, image, and sound. And why we decide to choose multimodal learning? Because recently, multimodal learning have gained more and more attention from our community, science community, due to various applications such as JSALT classification, recommender system, multimodal LM, and so on. So just by a few years recently, our community managed to generate, to introduce different noticeable models such as clip, which can encapsulate the image and text in the same joint embedding space, or clap is between audio and text. And also we have between speech and text, like SAMU XLS or Sonar. And last year we have image by that encapsulate various modality into the same joint embedding space. So I want to bring a little bit of background for clip. So clips is introduced by OpenAI, which is different than traditional supervised image classification. The idea of OpenAI is that they want to learn the image information directly from the raw text source. And why they want to do that? Because by doing that, they can have a much broader scope of supervision and can introduce more rich presentation and meaningful presentation that can help the model to do the zero-shot classification later. And in order to do that, they using the constructive methods. So really in specific case, they're using the info NCEs and train on web-scale image text pair data. So what is the constructive learning? So imagine we have two modalities, the image and the text. So they project the image and the text into the same embedding space through a specific encoder, and they perform the push and pull action. So what is the push and pull action? That's where the constructive come in. So for the pull action is basically they try to maximize the similarity between the positive pairs. So they try to find the meaningful to pull positive pairs close together, and they minimize the similarity between negative pairs. By doing that, they can have the joint presentation that can closer the image and the text together. And similar to clip, we have clap models. So instead of using image, they learn the audio also through text with the same behavior using the info NCE loss. The same case, they just train the image to the sound using the audio, so the sound encoder, and they do the same push and pull action. So last year in 2023, we have the, for Meta AI, they introduced the image by. So different than clip and clap, they decide to grounding different various of modalities into the same embedding space, but here is image embedding space. And in order to do that, they collect different type of data that can connect to the text. They have the web image text data, the depth sensor data that collects the depth sensor with the image, the sound to the video or basically image, the thermal data and the sensor data to the video, and they generate the image embedding space by using the pre-trained clip image encoder. So the way they do, they first project the clip image, image on the embedding space using the clip image encoder, and they imagine we have another modalities, let's say sound. They project the same thing on the encoder, and they perform the constructive learning by push and pull action. And they try to maximize the positive similarity of positive pair and minimize the negative pairs. And they will do that not pairwise, so not only with sound, between sound and image, they also do it with different modality connect directly to the image. So sensor data, thermal, depth sensor, and text data. So being inspired by this idea, we decided to use text by data. So we call our work is text by. So what is text by? It is similar to that, but we connect different modalities like audios, in our case speech and sound, and image into the text embedding space. And why we want to do that? The motivation, because first of all, we have large transcribed speech and audio data already linked to the text embedding space, and speech image pair data is really difficult to get. And also after that, we have a huge data of sound and text and music text, so can help us after the workshop to scale up our data. And also since this one to condition the generative LLM model, so it's based on text, it will be better conditioning for the multimodal audio text LLM. So in order to do that, we are using the query formers, and I will pass the mic to my colleagues who will introduce about the architecture.
Okay, so our goal is to build a multimodal embedding model that can take image or speech to this multimodal space, which is a kind of a text. So to obtain some representation which is in the same joint space of the text, we need that our representation be in some fixed token. So this will be done by a query transformer. To introduce the query transformer, I will present before the normal transformer. A normal transformer consists of a self-attention layer and a feed-forward layer. For example, if we process a signal, we will put is as an input to a self-attention and after to a feed-forward. And the latent representation obtained by this transformer, the dimension would be affected as the sequence of the length. In a query transformer, we will condition the modality by a cross attention, and we will put as an input learnable queries, and this will pass by a self-attention, the cross attention, and the feed forward. And these learnable queries are learned from some downstream tasks. And here we can control the complexity of our latent space, since we have our output will be fixed by the number of the queries. So the key-former transformer has been introduced for vision understanding in the key-former architecture in the paper released in SML 23. So what is the key-former? The key-former is a joint vision and text model, and it consists of two branches. So we have the transformer, which is the same for the image or for the text. So if we process some images, the output will be the learnable query, which will pass to the self-attention, the cross-attention, and the feed-forward. And if we will process some textual data set, the output will be the text to the self-attention and the feed-forward. So the key-former is trained with three losses. The first one is the constructive loss, which is a pairwise similarity between each query output and the text output. And after, the highest one is picked. The second loss, so we will generate some text, and after we will compute a loss function to evaluate if the text generated by the system and the reference text matches. And the third losses, it's a binary classification loss that will indicate if the text match with the image or not. And for here, we need some negative samples, and in the key-former, these negative samples are obtained with negative mining. So here, in the key-former paper, the transformer is initialized by using BERT. Okay, the same architecture can be used, for example, to process a speech, and we can change the image by a speech and the encoder with a speech encoder to have a joint speech text model. And also we can do the same, for example, with audio. So we will replace our input by audio, and we will use an encoder, audio encoder, to have some joint audio and textual representation. So now how we can pass from the original keyformer to a multi-model keyformer. The first experience that we can use the same model to train a multitask learning. So here we have the audio, the vision, and the speech, and we keep the same architecture of the keyformer. And a second experience that we can do, it's the modality-specific cross-attention. So each modality will have its own cross-attention layer. This can allow to the model to handle the unique characteristic of each modality. So here, the changement, we have the multi-task learning. Just we have for each modality, one cross-attention. Now, how we can improve the original keyformer in our multi-model keyformer? We said that maybe we can put some experience in the queries part. So the first experiment will be, we will use a set of query modalities instead of using the same learnable query for all the modalities. So here each modality will have its own set of query, and so the changement is here. Instead of using one space for the learnable query, we will use some learnable speech query, some learnable image queries, and some learnable audio queries for our multitask learning. The second experience is we can use a fixed query to condition the modality. So we will add a token in our query, which is a fixed query for each modality, and here we can condition the modality. And a third experiment that we can do, it's to the same one that I presented before, just we can add a classification loss. So each modality have the additional fixed query and a classification loss. So we will use the same architecture that I presented before, just we will add a modality classification. So this is the experiments that we will do to train our multi-task learning. And I will pass to Hugo to the result. Okay, I will present before the experiment setup. So to train our multi-task learning, we will use for speech dataset the LibriSpeech and MLS dataset. For the vision modality, we will use Flickr and Coco dataset. And for the sound, we will use Wavecaps dataset. So for the training, we will use the official release of all these datasets, and we will have another set for the evaluation. And how to evaluate our multi-model keyformer, our space. So we will evaluate that for some tasks. The first task is the alignment task, and we will compute a cosine similarity for all the modalities. The second task that we will evaluate is the retrieval, and we will compute a retrieval accuracy. And the last task is the text generation task, and we will compute a word error rate for speech and the blue score for vision and sound. So I will present that in detail. For example, for the retrieval task, we have our target speech segment that we will pass it, for example, here for the speech encoder, which is whisper in our case, but it can be any speech encoder. And after we will pass that to the keyformer to obtain some representation, which is in the same join of textual presentation from the speech. And after we have some evaluation set included the textual segment for the target speech, and we will pass that the keyformer sent the textual one. It can be obtained directly from the keyformer to obtain some representation from for all this set. And after we will see if we are able to get the same representation from text and from speech, and we will compute a retrieval accuracy at top 1. For the evaluation using for the text generation task, so we have our target sample that can be an image, a sound, or a speech. We will pass that to the modality encoder and to the keyformer to obtain our representation. And after we will apply at in the top of that BERT language model heat, and here we will get our generated text, and we will compare that to the reference one, and we will compute a blue score or a word error rate. So I will pass to you.
Okay, so first we try to use QLabC as our QFormer and WaveLM as the speech encoder and Clip as the image encoder as a baseline. So we tried to change the model we used for the QFormer. We tried QBERT as well. So here we can see that we get better cosine similarity scores using BERT, but we lose some retrieval accuracy scores. And overall, the text generation metrics are improving, especially for blue. So we will try to use BERT instead of LabC in the next experiments. So yeah, all the models I'm presenting are the models that are like the best for the retrieval accuracy and not for the cosine similarity. Then we tried to use Whisper instead of WaveLM as a speech encoder. So this time we can see that the cosine similarity is better on the speech, but we lose a bit of retrieval accuracy for image. And once again, both the text generation metrics are hugely improving, this time especially WER. So we will use for the next experiments QBERT and Whisper as our next baselines. So here I have, we try to train models using all combination of all the modalities. So here we are using all the modalities, so speech, image, and sound. So here, here we have the first 3 models are on the single, all the models trained on the single modalities. These models are all the models trained on dual modalities, so each combination of 2 modalities from the 3 modalities we have. And then the last model is the one trained on all modalities at once. So here I highlighted all our best results in green and all of the worst results in red. So what we can see from this table is that most of the worst results we get are from the model trained on all modalities at once, and most of the good ones are from the other models. So what we can get from this experiment is that training on more modalities actually is harder than training on less modalities, so 1 modality or only 2 of them. So then we try to use a shared cross-attention layer or modality-specific cross-attention layers. So the first line is our baseline, and the second one is like using trying to use modality-specific cross-attentions. So here we can see that the only metric that is changing is the cosine similarity for sound, so it's getting a bit worse. And our results for text generation metrics are more or less the same, if not worse. So it doesn't really make sense to use like modality-specific cross-attentions. So we will stick with a shared one. So then I will explain present the results we got from the using a modality-specific QFormer conditioning query. So here, if we remember, we are adding a query to the learnable queries, and we are like conditioning it on each modality. So here, the first line, we are using the standard queries, so the baseline. And for the second line, we have like the additional query that is conditioned. So here we can see that most of our results are worse using this experiment. And we are losing a bit of blue as well, so it doesn't really work to do that. Then we try to use modality-specific sets of queries. So here we have like a set of queries for each modalities. So for this first experiment, I tried to train a model on only 2 modalities. So basically, we have 2 sets of queries here. We can see that we get slightly improved results in cosine similarity using this experiment on 2 modalities. And we get more or less the same text generation capabilities. We got a slightly worse WER, but a slightly better blue. And these experiments were carried out using another tokenizer. That's why the WER score is quite different from the previous models. So here, these are the curves that we get from training these models for the cosine similarity on the left and for the accuracy on the right. So here we can see that the contrastive loss manages to optimize well the accuracy metric, but it's not really the case for the cosine similarity. So having a high retrieval accuracy doesn't mean that the cosine similarity is going to be really good. So we can see that there is a misalignment problem because cosine similarity is more or less trying to measure the alignment of the model. So here I tried to perform the same experiment, but this time on 3 modalities instead of 2. So this time we can see that we are losing actually cosine similarity score by using several sets of queries. And this time we are getting a better WR score, and a slightly worse blue score. But overall, we can see that the results are far worse when using 3 modalities rather than using 2 of them, as we saw earlier. And these are the curves for these models. So there's a slight mistake on this slide. Actually, the red model is the single query set one, and the blue one is the multi-query set one. So here we can see that, once again, our contrastive loss is successfully optimizing the accuracy metrics, but it's not the case for the cosine similarity. And when using more modalities at once, we can see that the cosine similarity scores is actually decreasing sooner than when we are using only 2 modalities. So now I'm gonna introduce what get a summary of what we got from this alignment problem. So as we said, the contrastive loss alone is not enough to get a good alignment between the modalities. We can see that because the cosine similarity score is not improving. The modalities, so yeah, getting a better retrieval accuracy doesn't mean we get a better cosine similarity. And yeah, the modalities seems to compete against each other rather than like being mutually beneficial, because we get better results using 1 or 2 modalities rather than using all of them at once. So I'm gonna let Antonio present some insights we have about that. So thanks.
Thank you. Hello. Yeah, I'm gonna be talking with about the misalignment problem, like this what Hugo was explaining about, that accuracy and cosine similarity are not related, and also that accuracy is not very correlated to generation performance. And I'm gonna be talking like more. I'm gonna be giving like more theoretical perspective about this. So first, I want to start with an example with image captioning. Let's say that we have this image, and we could have like a short caption, just saying picture in Orioles baseball uniform. We could also have like a longer caption, and we could have like even longer caption. So we could have like many ways of describing like an image. So yeah, a picture is worth 1,000 words, or I usually said, or in like more scientific words, images are more entropic than text. Here, another example about automatic speech recognition.
If I play with Roger, I am playing with Roger, but not me against Roger, no, me with Roger.
Yeah, we have like some information about the audio in the text, but we don't have all the information about the audio in the text. For example, by just listening to the audio, we can see that the speaker is a man, that he is, for those who are familiar with tennis, he's Rafa Nadal, and maybe he's like in a stadium or another crowded space, because we can see listen that background noise. So the point is that an audio with end words is worth more than end words, which, yeah, again, audios are more entropic than text. So then the point of this is that we have some information which is modality dependent. And yeah, the point, I mean, our question is if we need this modality dependent information, or if we just need the information which is common to both modalities. And as always, it depends on the application, and we want to see what's happening about generating one modality from another modality, which is our actual task. So first, I'm gonna, just to do a recap of some information theory basics that I need to explain what I want to explain. First is the KL divergence, which is just measuring how the probability distribution P is different from a second probability distribution Q. Then mutual information, which is the amount of information that we can obtain from Y, from X by just observing Y. also Markov chain in this case. What this means is that C and Y's are conditional dependent given X, or that, yeah, probability of C given X and Y is equal to probability of C given X, or the other way around as well. And then the data processing inequality, which given the previous Markov chain, we have that the mutual information between the variables that are further is lower or equal than the mutual information of those variables that are closer in the Markov chain. So yeah, this is like our problem. We have, we want to get embeddings from two modalities, or yeah, two modalities. So then we have like inputs in two modalities, 1 and 2 in this case, and then we have also like two encoders, one per modality, and then we want to get embeddings, one embedding per input and modality. So in our formulation, we assume that the input are composed, the first inputs are composed of what we call gamma, which is the essence. We have called the essence the information that is common to both modalities, and then it's also composed of N1, which are the nuisances that are more typical, that are typical in modality 1, and the same for modality 2. We have N2, which are the nuisances of modality 2. So then in the same example I showed before, we have like this image captioning problem, and then we have that N1 is the empty set because all the information which is in the text is also in the image, so we don't have text-specific information. However, we have like many image-specific information. We can get many information by just looking at the picture that we cannot find in the text. For example, in this case, it could be that the player is wearing like a white T-shirt, that he's wearing a cap, that there's audience watching the match, that the player has concentration phase. So there's like many information which is in the image and we cannot find in the text. So these are like the nuisances of the image modality. So when we are trying to solve the retrieval task, our goal is to try to maximize the mutual information of the embeddings and the essence. So the embeddings should contain as much information as possible about the essence or the common part between both modalities. The point is that, yeah, this essence is just an abstract concept that we have defined to formulate our problem, and then we cannot calculate this mutual information between the embeddings and the essence. So, but we can, we have this Markov chain in which, yeah, we just have that the, like, since the only connection between the inputs of both modalities is gamma, then the only connection between the embeddings of both modalities can be only gamma. It's like we cannot have more information than gamma in one embedding about the other embedding. So by just having this Markov chain and applying the data processing inequality, we have this inequality of here. So then, yeah, we can just maximize this lower bound of the mutual information between the embeddings and the essence. So yeah, then we know that to maximize the mutual information, we just, like in the literature, in the M4NC paper, they demonstrate that this is equivalent to minimize the contrastive loss. So yeah, we can just try to minimize the contrastive loss to try to maximize the mutual information between the embeddings and the essence. So our question again is this sufficient to generate a modality Y from modality J and vice versa? So the point is that we don't think so. As Hugo explained before, there's like some, there's no like clear correlation between retrieval accuracy and generation performance. So we want to analyze why this is happening, or just to give an hypothesis of why we believe that this is happening. So yeah, the point of retrieval goal is we want to maximize the information that each embedding contains about the essence. So we are trying to maximize this overlapping area between the embeddings. So they should contain as much information as possible about the essence. But we are not imposing any condition on the nuisances. So maybe the embeddings could have many information about the nuisances of each modality. And yeah, let's see what happens if we, for example, want to generate modality 2 from modality 1. The first point is that the embedding of modality 1, it has like some information, these nuisances of modality 1, and the point is that the modality 2 decoder is not able to lead with that kind of information, and it doesn't know how to work with that kind of information. So the first step would be to remove that information, and also the second point is that the embeddings of modality 1, they don't have any information about those nuisances of modality 2. And the point is that if we are not having these nuisances of modality 2, maybe the samples that we are decoding, they are not going to have like such a good quality as we are used to. So here I give you an example in the literature. It's like this DALI 2 paper in which they want to go from like to generate images from text prompts. So here modality 1 could be text and modality 2 could be image. So then what I explained before. The first goal could be to reduce the information about the nuisances in the text embeddings. So as I explained with the baseball player example before, we can consider that this is the empty set, since all the information which is in the text, we can also find it in the image. And again, they have to create the nuisances of modality 2. And what they do for that is to include this like a generative model, a diffusion model, or autoregressive generative model to add that extra information about the nuisances of modality 2 to the text embedding. So they are adding that extra entropy to get like better quality images. I just show you some of the results that they give in the paper. Is when we are just using the text embedding to decode our samples, then the quality of all the information which is in the caption is also in the image, but the point is that the quality of the image is not as good as we could expect, because there's like some, they are not very fine-grained details in the images. So when they actually create this extra entropy, this extra information about the modality 2, then we have these image embeddings, and the images that we are getting are a bit better. We can just see, for example, the image of the motorcycles. In the first case, actually, maybe you can see two motorcycles. We can imagine them, but this is not the idea that we could have in mind when we are just seeing that caption. And then when we are adding that extra entropy, the quality of the images are like a bit better or more realistic for us. So yeah, if we want to go the other way around, we want to generate modality 1 from modality 2, we should do like the same, but like the opposite way. We should just reduce the nuisance of modality 2, and then we should add the nuisance of modality 1. So this is actually our case. We want to go from image or audio to text, and here, yeah, this is like the Q-former goal. So the first step could be to create, the nuisance of modality 1. And as I said before, as playing with the baseball for example, we can assume that this is the empty set, again, because all the information which is in the text is also in the image. And then we should try to reduce the nuisance of modality 2. So the nuisances of image or audio. So this is what we want to find out how to do it. So yeah, we want to apply the information bottleneck to do that. It's very well known in the literature. So here our goal could be to reduce the mutual information between the embeddings and the nuisances of the modality of those embeddings. But then again, the nuisances is just like an abstract concept that we are defining just to formulate our problem. So we are not able to calculate exactly this mutual information. However, again, we have this Markov chain of here. This is simply that since C is a representation of X, is fully described by X. So it's like once we know X, we don't care about the nuisances. They don't affect to the representation once X is known. So we can just apply this data person inequality, and then we have that the mutual information between, we just simplify an upper bound for the mutual information between C and N, which is the mutual information between C and X, and we can just try to minimize, that mutual information, like this upper bound. So we have find a paper that they propose a demonstration which is kind of similar scenarios ours, and they demonstrate that minimizing this mutual information is equivalent to minimize the KL divergence between the embeddings of both modalities. So if we assume that these distributions are normal with identity matrix as covariance matrix, and that the magnitude of the means are equal to 1, then this is like equivalent to minimize the cosine similarity of positive pairs. So yeah, to get this information bottleneck, we can just try to maximize the cosine similarity between positive pairs. So just to sum up everything in the retrieval task, we want to get embeddings that contain as much information as possible about the essence, and with the information bottleneck, we want to have embeddings that contain just as little information as possible about the nuisances. So in one case, in the first case, we want to maximize the mutual information between embeddings and the essence, and in the other case, we want to minimize the mutual information between the embeddings and the nuisances. So yeah, for the first case, we just want to minimize the contrastive loss, and in the second case, we want to maximize the cosine similarity between positive pairs. So we propose this last function of here is just we want to minimize this contrastive loss and to maximize the cosine similarity of positive pairs. Here I just show you like the expressions for those of you who are familiar with them. And this is what happens when we play with the value of beta. When we are decreasing the value of beta, then the embeddings will contain more information about the essence, but also about the nuisances, which is something that we believe that it's going to decrease the performance of our system. But when we are using a higher value of beta, then we are, maybe our embeddings won't contain that much information about the nuisances, but maybe we will be also removing some of the information about the essence, which is something that we don't want it to happen because it could also decrease the performance of our generator. So I just created an experiment just to illustrate better what I was playing. With two modalities, one of them is text, and the second one is image. So it's just in this example, we have that the essence is shape and figure color, which is the information that we have in both modalities. The nuisances of text is nothing because everything that is in the text is also in the image, and the nuisances of image modality is the background color, which is something that is not described in the captions. So first, we train our system by our two encoders by just trying to minimize this loss function that I propose. Then once these encoders were trained, we just froze the text encoder and trained just the text decoder to get text from text embeddings. And once we trained this text decoder, then we just took the frozen image encoder to get embeddings with the frozen text decoder. So the idea here is that we would like to obtain text from images, and for that we would like that the embeddings of text and image are as aligned as possible. So here again, when we have like a low value of beta, then the image embeddings will contain a high level of information about shape and figure color, but they will also contain many information about the background color, which are the nuisances of the image modality. And we believe that the text decoder doesn't know what to do with that kind of information because the text decoder is only trained to decode shape and figure color. So it's like the text decoder doesn't know how to lead with that kind of information. So we believe that this could decrease the performance. On the other hand, if we have like a value of beta which is high, then it will happen just the opposite. Maybe we won't have a lot of information about the nuisances in our embedding, but then we won't have also information about the essence, which is important to get like good samples, like good quality samples. So we have to find this trade-off between values of beta. Here I show you like the reconstruction error, so the lower the better. So this is like the performance of our system. And we can see that with low values of beta, then the quality is not very good because we still have some presence of background color. Yeah, okay. And with high values of beta, then it's like we have the absence of the essence. So we still have some information about we are missing some information about the shape and figure color. So the quality of the samples is not very good. So we have to find these intermediate values of beta that control the trade-off between these two scenarios. So finally, I just want to show you some of the samples that we generated from the Q-former. This is the slide that I showed you before. We wanted to find a way of reducing the nuisances from modality 2. So what we propose for that is this last function. So as I was saying, we train Q-former with different values of beta, and then we use the text decoder to get some samples from the image embeddings. So here, show you an example of this picture of a bear. When we don't apply information bottleneck, we are just applying a contrastive loss. We can see that it's saying that, the caption is that our model is generating is a brown bear sitting in a grassy field with trees in the background. But if we look at the picture, we don't have any trees in the background. So when we apply some information bottleneck, we are just reducing this idea of having trees in the background. So we just have a brown bear is sitting in the grass with its mouth open, which is actually happening. So what we believe that here is happening is that when we don't apply the information bottleneck, is that the decoder tends to imagine that what's something that is likely to happen. For example, we believe that the embeddings of grassy field and grassy field plus trees in the background are close in the space. So then the decoder, since we have not removed that information, is trying to just imagine that there are some trees in the background because it's kind of likely that it happens. I show you another example also with baseball players. When we don't apply information bottleneck again, this is something that we don't know what is happening. Is when we don't apply information bottleneck, it's just saying a baseball player. It's like it's not describing the player in the back. but this shouldn't happen, but we don't know why. But it's also interesting to see that this running to a base in a stadium. Again, it's happening the same. It's like when we're not applying this information bottleneck, is that the model it tends to imagine that since it's very likely to play baseball in a stadium, and maybe you have many samples of people playing baseball in a stadium, then it tends to say that, okay, they are playing baseball, so maybe they're in a stadium again. Maybe the embeddings of playing baseball in a stadium are close to just playing baseball. When we are applying this information bottleneck with a low beta, then we have like a perfect description. A couple of baseball players are running in a field, which is kind of good description. And then we have like a higher beta. We are removing one of the baseball players. We are removing too much information, and we just have a baseball player is trying to catch a ball. Finally, we have this example, which is also interesting. When we have beta equal to 0, we have that a highway with cars and a traffic light next to a road. Again, we cannot see any traffic light in the image. So yeah, again, the model is trying to imagine something that is very likely to happen. Maybe when we apply like a higher information, information bottleneck with low beta, then a highway with many things on it near buildings. So here, actually, we can see some buildings here, but the point is that we don't know if the model is actually like looking at those buildings or it's just imagine that buildings are usually close to highways. So we don't know if it's just adding information or it's just looking at the buildings. And finally, when we are like increasing the value of beta, we have that a highway with a bunch of signs on the road. So yeah, here the point is that with higher value of betas, usually the captions are more simple. They don't have like as much information, but they don't tend to add information, which we believe is great. So yes, so conclusion of what I explained is contrastive losses are usually used when trying to align different modalities, and they work well for retrieval. They are like a good option, but they are not designed to remove a specific information. And we believe that the presence of this modality-specific information tends to worsen the performance of generating one modality from another one. So then we just propose a loss function to remove modality-specific information by using this information bottleneck that I explained before. Time for neural audio codec team.
Thank you for the Q-Former team. So hi everyone, my name is Ellen and I'm part of the Neural Audio Codec team. So I guess our team focuses on audio compression, and given some sort of digital audio data, we want to compress it into these discrete tokens so that it requires less information to store or download. At the same time, there's going to be some loss of information. So the goal is also to retain, The goal is also to retain the information so that it can be reconstructed and still maintain the original quality. And for a project, we're like focusing on the generative models, and nowadays, with the popularity of large language models, it's a good idea to like leverage these and incorporate them. And to do so, we need to have some sort of discrete audio tokenizer that is able to encode the necessary information, which is why we want to develop a new sort of audio tokenizer. Another reason why these audio tokenizers are important is that, again, we want to compress the audio efficiently while preserving the quality. And this requires a balance. For example, the 2024 Descript audio codec compresses the 16 kilohertz audio to 8 kilobits per second. The popular MP3 audio compression compresses to 128 kilobits per second. So the DAC is 16 times more efficient than the MP3. And so we can see that these like neural audio codecs are like really compressing at a high rates. There's two main types of machine learning based audio tokenizers. The first is the neural audio codec. This is based off of vector quantized generative adversarial network. An example of this is the Descript audio codec. And this kind of model leverages the discriminator and generator losses. The second type is self-supervised based audio tokenizers. These are commonly used in audio language models, and they are built off, they use the mask span prediction. An example of this is the Hubert and Wave2Vec models, which you all may know. There's some limitations, particularly with the neural audio codecs. The first is that since it only focuses on compressing audio, but it doesn't, it's not designed with the end in mind to generate audio, and so as a result, it doesn't encode the abstract linguistic information that is usually necessary for these language models. So we kind of asked, what happens if we build a generative model on these tokens? So by training an autoregressive transformer on these tokens, and I'm gonna play audio. I'm not sure how to play. Okay, yeah, I'll play it once, and I'll just play it 2 times.
And for Annie. Outside that, it was as though a dark cloud was conjunction. She can also kind as went also of a doctorate of.
So this audio, it's prompted with 3 seconds of cohesive audio in the beginning, which makes sense, but it generates
And for
a lot of
Annie.
nonsense
Outside
in the
that,
end
it was as
because
though a dark cloud was conjunction. She can also kind as went also of a doctorate of.
because it's not, it's trained using these tokens which don't encode the necessary amount of information. And so for our team, we wanted to design a neural audio codec to effectively compress audio into different levels of abstraction. And the most important of which is the semantic codes, which prior audio codecs do not encode. This encodes the high-level structure, grammar, meaning, etc. And also somehow keep retaining the low-level codes, which help you reconstruct the original audio. Yeah, so I think Dominic will now introduce and talk about the model architectures.
Okay, thank you, Ellen. So as Ellen pointed out, these neural audio codecs are usually built on top of the vector quantized GAN networks. So let me just introduce some architectures. So at first, these networks are trained using short audio chunks, usually something around 380 milliseconds. And then a convolutional encoder is applied. So for each 20 milliseconds of audio, the convolutional encoder outputs one single embedding, which means that if you have 16 kilohertz audio at the input, the frame rate after the encoder is 50 hertz. However, encoder outputs continuous embedding, and we were talking about the discretization or tokenization. So for that part, the model uses vector quantization layers. These layers are nothing but code books or kind of like sets of codes, and for each code, we have an embedding. So for a particular, for a single input vector x, the codebooks is trying to look for the closest vector in its set of entries. And as is pointed now on the image on the right, it finds that and outputs it. But the problem with the single vector quantizer is its bit rate. So usually raw waveforms have bit rate around megabits a second. But here, if we quantize it with one vector quantization layer that contains only 1024 codes, we obtain bit rate of 500 bits a second. So you can imagine how reconstruction can sound with only that low bit rate. So an immediate solution can be to increase number of codes. But we know that, for example, if you want to use 80 bits to encode one single embedding, we will need to store 2 powered 80 codes, which is not really feasible. So what we want to do instead is to use residual vector quantization. So we know that the first vector quantization contains only 1024 codes. But after quantization, there's going to be some residual, which means that if we subtract the quantized embedding from the input, there's going to be something left. So we can further quantize the residuals and obtain better quantization as we go through the layers. So by doing that, we can store n times 2 powered q codes, where n is the number of codebooks and q is the logarithm number of codes per codebook, instead of storing 2 powered nq codes. And at the end, we know that we are quantizing the residuals, which means that in order to obtain the final embedding or final quantized embedding, we just sum all the outputs of the quantization layers. So now that we have the quantized embedding, we need to reconstruct the audio. So in order to upsample the quantized embeddings, we are using convolutional decoder, which is usually transpose of the convolutional encoder. So instead of convolutional layers, we are using the transpose convolutional layers. And the output of the CNN decoder is raw waveform at 16 kilohertz. So as Ellen pointed out, this GAN consists of generator and discriminator. So generator is the top part, which takes audio as an input, quantize it, and reconstructs the audio. So the fake samples here are the resynthesized audios, and the real samples are the inputs. And the discriminator says whether the audio is resynthesized or not. For training these models, we are not only using the GAN losses, but also something called reconstruction losses. And these losses are usually distances between waveforms or MEL spectrograms. And these losses ensure that we actually match the input audio, because we want to not generate, but we want to only tokenize the audio, which means that for a given input, we are trying to generate an audio that resembles the input. And then we have the adversary losses that are coming from the GAN framework. And at the end, we have this vector quantization codebook, but these vectors are randomly initialized and need to be trained in order to quantize the space properly. So after we train the neural network, we can use it in two stages. The first one is audio tokenization. So if you want to train a language model, we need tokens, not the audio. So we can just pre-quantize the whole database into a set of discrete tokens. And after they train a language model, the language model is going to output a set of tokens. We know that each token is coming from, it's coming from a single codebook, or we have this RVQ kind of structure in the codes, which means that we only sum the codebook entries for each code, obtain the sequence of embeddings, and then we can pass these embeddings into a neural decoder and obtain audio. So far I've been talking about the audio, or the new audio codecs, the models that are trying to model the fine audio details. We also have another models that are trying to model some more structural information in the data. And for that, we are using models that are trained using mask prediction. So compared to the neural audio codecs, these models need more context, which means that instead of a few hundreds of milliseconds of input audio, they are usually trained using 30 seconds long waveforms. After that, these models apply convolutional encoder. Yet again, it's simpler than the one that neural audio codec uses, but it downsamples the audio from 16 kilohertz to 50 hertz. So far, we have the same sampling rate embeddings, but now the mask prediction part comes. So in order to learn context, we are first masking out some sort of span of embeddings. What do I mean by that is that we sample a start index and then mask continuous embeddings. To model the context, the Hubert model uses transformer architecture and tries to predict the mask tokens. So the overall task is just classification. We are trying to classify the masked embeddings, or we're trying to predict the labels for those masked embeddings with the context of the unmasked ones. And also, we can turn these models into tokenizers by quantizing the transformer outputs, for example, using k-means, and then we obtain the centroids, which represent our codes. So, as I mentioned, we have different, or mainly two types of audio tokenizers. The first ones are trying to focus on the fine audio details, but they really can't model well the phonemes and words. But on the other hand, we have these semantic or more semantic models that are trying to model more structural information in the audio. But on the other hand, they really lack these fine details in the audio. So for example, if we were to reconstruct the audio using the Hubert or wave-to-vec model, the audio wouldn't sound really well because these models weren't trained specifically for audio reconstruction. So our primary goal is to have best of both worlds. So the prior work, model coming from the prior work called speech tokenizer was just dealing with this problem, or they try to design a model that is trying to combine both the fine audio details and the semantics coming from the pre-trained SSL model. So how do they do it? We have an input audio that is passed through audio tokenizer and Hubert, and they are trying to distill the knowledge from Hubert into a first RVQ layer, which means that they compute the average of all the Hubert layers and then they are trying to pull the output of vector quantization layer of the first vector quantization layer close to the Hubert embeddings, which means that after a model is trained, it can output some embeddings that are correlated with Hubert ones, which means that this way we are bringing the semantics into a neural audio codec. So as I mentioned, we have these audio codecs that output tokens, but these tokens, they don't have any disentangled information. The information of the audio is spread across the codes. And on the other hand, we have the models like Hubert that output semantic tokens, but they really lack the fine audio details. And the third model is the combination of both. So at the first layer, we have the semantics, and on the other layers, we have the fine audio details. But there's another thing to the audio or language itself, and there is different timescales of like this different timescale hierarchy. So we know that we have some global semantics on top, which means some meaning or speaker information in the audio, which is usually utterance specific. So it doesn't change throughout utterance. And then we had words, syllables, or phonemes that are sampled at 12.5 hertz. And at the bottom part, we have the audio itself. However, none of these architectures that are presented so far are introducing this inductive bias in the models. So in order to do that, we are using the multi-resolution RVQ layers. What do I mean by that is that after the CNN outputs embeddings at 50 hertz, we progressively downsample them into 12.5 hertz, which is exactly what's the phoneme sampling rate. Then we progressively upsample the codes, and finally we obtain codes that are sampled at 50 hertz. And basically the rest is just the audio parts. So what are we trying to do by that is we're trying to downsample the embeddings so that they contain more structural information. And then we leave the rest of the layers to model the fine audio details. So to summarize things up, we presented the new audio codec architectures based on VQ GANs, and also we described the mass spam prediction models that we are using to distill the information into the new audio codecs. We also introduced the semantic tokens and incorporated the inductive bias coming out of this hierarchy into our model by introducing the multi-resolution RVQ. So if you have any questions, please ask. Otherwise, I guess we can do a break if you want.
Just about the last part, how do you upsample? How do you do that?
We first, we have the embeddings at 50 hertz, and then we pull the embeddings. We do vector quantization, and then we do interleave or repeat, or we can do we can do convolutional sampling.
Which one?
Interleave, repeat. Sorry, repeat interleave. That's the in Torch. There's this method called repeat interleave.
Okay.
So that one. Or you can use convolution and then transpose convolutions afterwards. We're just doing similar thing.
Okay.
Yeah.
Bottleneck just reducing the embedding dimension?
Okay,
Yeah.
so I don't know what, I mean, do you know if the question is referred to the Q-former or in general? Maybe in the Q-former? I don't know.
Yeah, I think it's for the Q-former.
Okay. No, we haven't, but it could be also like very interesting. Like the point is that for sure, if we are, okay, yeah, sure. I don't know what it is. There are many. Maybe this is slide. I mean, it's not like a exact slide, but yeah, maybe this is the best one. It could be interesting to try to reduce, to apply like information bottleneck by just reducing the dimension of the embedding. The point is that we could be reducing information, but maybe not the type of information that we want to remove. So yeah, we believe that doing it with the last function tends to be more efficient, and in the literature there are many examples doing it with the, not in this specific scenario, but in other scenarios they are doing it with the last function because it allows you to remove the specific information that you want to remove. I don't know if this answers the question. Just in case if they want to answer again, we can discuss about it. Thank you.
Hello. I have a question about to the person who talked about generation, evaluating the embeddings. I think it's maybe one before you, right? Yeah.
It was before my.
Yeah, before you.
Okay, yeah. I don't know who's the one who can answer.
Okay. So two questions. One is there was a degradation in quality when you used multiple modalities, if I remember correctly. So I'm curious as to how that training was done because, yeah, so maybe.
You mean this slide, maybe? Okay.
Yeah, I think there's much left to be analyzed here, but the training was pretty simple, like just mixing the 3 data sets together for 3 different modalities and just training a single model on multitask learning.
Yeah. The reason I ask is did you require that you have all 3 modalities at the same time, or because that might?
Yes. Actually, yes. This is how we implemented it. So in every training iteration, we had batches from all 3 tasks, and then we sum the loss function for all these 3 batches and then optimize.
Yeah. So I'm just asking because it's possible that that intersection is a small one, and so performance might degrade because you don't have enough data. Right?
So intersection, you mean?
Meaning, if you only have data points with all 3 modalities present, that might preclude the data points with just partial supervision, right? Like just image and speech or image and text.
So just to clarify, actually, we don't have alignments between all modalities. So we only have alignment between a particular modality and text.
Okay.
Yeah.
Anyway, we can.
Yeah, we can discuss more about this. Yeah.
Let me make a comment.
Yeah, sure.
So I think, Shankar, if I understood you correctly, what you're saying is, did you have any more than 2-way parallel data? Did you have simultaneous 3 or 4 modalities?
No.
And the answer is no.
Yeah.
So even though the training batch might have had many pairs, they were each was something in text, something in text, something in text.
Exactly.
Thank you. Yeah, I think that's yeah. One more question, actually. So this is about the evaluation. So I saw blue and word error rate, and one problem with this here is they are very strict metrics. It might be good to take like more text generation metrics like BLERT or COMET or word score, which are more flexible because you might not get the same words, right? You might get semantically
No, for sure. Yeah, and that's a good point. Like the main goal was not really text generation, but we had this LM head, so we were just evaluating on it. But the main goal was to evaluate this joint embedding space, which you do by retrieval. But yeah, I agree with these other metrics.
Okay, I have a question to the coding guys. Actually, that was very charming for me because my thesis was on speech coding like 25 years back or something like that. So basically, you claim that this is a neural audio coder, but everything I saw was was using the semantic information of speech, like phonemes, verbs, etc. So did you do at least a little work, or do you have plans to extend it or to test it with music or noises or bird sounds and stuff like this? Because I haven't seen that in the presentation.
Yeah, so we started with speech because it was easier for us, and also we worked on speech data sets at the beginning, and then we are trying to extend the model to audio itself. Because, for example, for speech, we can use the models like BERT that are pre-trained on speech, but for music, it's more challenging, or like for general audio, it's more challenging to bring the semantics. Because, for example, from speech, we are able to kind of imagine what maybe information disentanglement is, or like what kind of information should be stored in different kind of RBQ layers. But for general audio, is much more complicated.
Especially in music, there is a lot of other semantic information, like, I don't know, rhythm, BPM, stuff like this. So
I think this, so our original goal was like general audio generation, but in this workshop, we just worked on speech, just because it's easier. But actually, the Descript audio codec that, Dominic was talking about is a universal audio codec. So it can actually generate music, sounds pretty faithfully, yeah.
Okay, yeah. So Dominic, just so you know, this is fresh off the press. Matthew is building a model right now where he has this interesting training paradigm. He mixes and matches audio cuts from many sources. Some of them are speech with transcripts, some other are like from audio set, which has some class label. Others are just noise and things like that. And he is training a model with all of those so that its embeddings can represent all sorts of things, including music and bird sounds and typewriters and words and so on.
So is he like also building tokenizers or doing sorry. is he working on like self-supervised learning more or compressing audio? Yeah, but that's pretty.
He is mainly focusing on transcription. He wants to have the transcription accommodate everything. But I'm trying to see, is he here? He's not here, but yeah. Okay. Ahmad, go ahead.
So that's a question for a couple of colleagues. The first one for the misalignment. So have you guys considered doing some kind of data augmentation for the various transcription for the images or adding some noise to the audio and have more alternatives? And given that what Samir has mentioned as well for don't have data paired across multiple modalities, you could leverage a lot of data augmentation in both tasks. So I don't know if you guys had planned or thought about it during your work.
By data augmentation, you mean to create new pairs of data or just to augmentate like
yeah,
just
you have
images?
a transcription for an image. You can have multiple ways of doing this, or you have an image. I mean, the example you mentioned for the traffic. So you could have dealt with this if you get transcription from multiple modalities and get variables from it. I wonder if it has helped in this kind of misalignment.
Maybe they could improve it, I believe, since usually when they are doing augmentation, the distribution that our data is learning to generate tends to be like less picky, like more, yeah. So maybe it could tend to improve the alignment. I'm not sure about it. So maybe, I mean, we should think about it. I'm not sure how it could help. I don't know if someone has some intuitions about it.
I think it would definitely lead to a much richer representation space. And it would be nice to analyze, like, if you train with a lot of data augmentation strategies, what type of space you get, and is it more aligned or less aligned? Yeah. But we didn't try a lot of those things.
Do you think it would make sense?
I think so. I think it will make sense, yeah, for sure. Thank you.
So we are at a break, right, Samir? Okay, so let's take a 10-minute break, recaffeinate, bathrooms, whatever. Paula, you have an announcement? Yeah.
Yeah, we have the tags on the left side. Yeah, the name tags. So please grab yours. Please, yeah. So they're at the end of the auditorium.
Just like that. Okay, thank you. I'll take that.
Where he has basically Google audio set, USAN, and all these different speech corpora in multiple languages. So he has all those things all in one big file, and we set up a training routine where he cycles between them and randomly creates a concatenation. So he'll take a 2 seconds from livery speed, 2 seconds of something from I see. Audio sets, and take another set from the Spanish call home, another one from News Van, and you concatenate the audio, concatenate the supervision, and play. This way he's coping. Yeah. So this way, this model's internal representation knows everything.
So it produces a token called birds chirping, typewriter, in square brackets, saying, like, and he said, this is impossible, bird chirping. Que pasa, señorita? Typewriter.
Okay. I need to talk to him about it because currently we've been busy with JSALT. We think about future work.
You're here, so you can continue talking.
Yeah, I know that he's been busy with the NAC
that's
version as well. Oh, yeah. Okay. Yeah.
Jakby nasuwasz na I will play the audio. Tak dam tam można jeszcze pauzy. I tak będzie wyjechać albo powiem pani, że jako wygrać audio, że to powiem, no jasne.
Hey folks, let's start settling back down. It'll take a few minutes with so many of us, but everybody please come back. Again, let's start heading back to our seats. We'll start in a couple of minutes. Hey, and if you're going out, tell the guys outside to come back in. Okay, now it's on. All right, guys, let's head back in. Thomas, Murat, Karahan, whoever is back there. All yours.
Okay. So let me just re-summarize things. So for now, we introduced the neural audio codec that's trying to encode some fine audio details. Then we introduced the semantic models that are trying to encode more structural information. And then we also introduced a way how do we combine those models, this neural audio codec that is encoding fine audio details with more semantic or structural information by distilling the Hubert model into the first REQ layer. And also the last part was about the audio hierarchy or the linguistic hierarchy that we incorporated into the model by using multi-resolution vector quantization layer. So now the other Dominic will present the experiments and the experimental setup. Thank you.
You mean the second of many Dominics.
Right. Okay, so as it has been outlined before, we basically got two goals. The first one
is that we want to have a codec, a model, which are very good at reconstructing the audio. So it is reconstructing audio with high fidelity, with high quality. But additionally, the second thing we want to achieve is that we want to add some semantic information to these tokens, to these codes. So we want to know what kind of linguistic information is there, and also how well we can like disentangle the information between different codes and layers. Okay, so by now we used LibreSpeech for training and evaluation. So that's like 1,000 hours of audio. And since we want to know in numbers how the good reconstruction quality we have, we used several evaluation metrics. So basically, we have the original audio and the reconstructed one. And we used metrics like MEL distance, waveform distance, SISDR, STFT distance, and WSCL. And each of them got some specifics, and but they, in general, say something about the differences between the original and reconstructed audio, but mainly we focus on these two metrics, and that's the MEL distance and WSCL, since we mainly focus on speech by now, and WSCL gives us some mean opinion score about perception, and it has in the numbers are in range from 0, which is what is the worst quality, up to 5, what is the best quality, and MEL distance is a good measure because the MEL scale is similar to human perception. Okay, and the next step was to also find out like what kind of linguistic information or what kind of semantic information we are able to easily extract. So we used some SuperB and here benchmarks to probe the codes. And what is the probing? So this is our architecture, and the here benchmarks and SuperB benchmarks are basically just some small classifier. And the thing is that we use the ZQ codes, which are the representation after the vector quantization. So we took this, we trained a small classifier upon this, thanks to benchmarks, and then we got the score regarding the task we want to measure. So from SuperB benchmarks, we mainly focused on phoneme recognition and speaker identification, where phoneme recognition is just some sequence-to-sequence mapping where we got the sequence of tokens and we map them to underlying phonemes. Speaker identification is able to classify like 40 speakers in this benchmark. And for here benchmarks, we evaluated emotion, pitch, and speech commons classification, where emotion classification is able to classify like 6 classes, so 6 different emotions, and speech commons is basically a simple keyword detection. So we can compare to some existing models. We chose really strong state-of-the-art models. So for example, for reconstruction quality and for reconstruction models and a codec, we chose discrete audio codec. For downstream tasks, we used Hubert, trained or fine-tuned to some different downstream tasks. And for knowledge distillation, we used speech tokenizer. So for the reconstruction quality, first we have the original DAC compared to our version of DAC using multi-resolution. And we can see that we basically got the the same reconstruction quality. So it's so it doesn't really like worsen the quality of the reconstruction. And what about the knowledge distillation version? Here we got again the original DAC, but also the speech tokenizer, which is using the knowledge distillation. And we can see that our DAC using knowledge distillation is close to the speech tokenizer one, while we are slightly better. But the main point here was that we were actually trying to mimic the performance of the speech tokenizer because we used the knowledge distillation. So we basically made it. And here again, I want to express the trade-off we got because of the knowledge distillation. So here we see that the knowledge distillation models are worse at the reconstruction, while the original DAC and the multi-resolution is at the same range. And for the downstream task probing, we did this task as I mentioned before, and this is how we perform. So we can see that for phoneme classification, we didn't actually quite get the phoneme error rate as Hubert, but we still do some improvements from the original DAC, and we can see that the knowledge distillation helps. So we are able to distill the information from Hubert into our DAC codes. For speech command classification, we can see that we quite improved it a lot. So the knowledge distillation really helps. And here, for pitch classification, pitch detection, we can see that even the original DAC is performing quite close to Hubert, but thanks to knowledge distillation, we were able to like take some additional information from Hubert, and in combination with DAC, we were able to even get some better results. And for speaker identification, that's quite unfortunate that we were not able to really catch the specific information to individual speakers. However, it's important to say that it's 40 speakers which were classified. So it helped somehow, but really it's probably not the best for this kind of task. And regarding emotion detection recognition, we see that the knowledge distillation helps, so the point is proved. Okay, so this task were about it using the ZQ codes, but we also want to know if we manage to disentangle the different layers. So we use some layer-wise analysis where we probe after each individual layers. And thanks to this layer-wise analysis, we can see that the original DAC basically can't do any like disentangling, that each of the layers are like evenly distributed. The information is evenly distributed among these layers, and it's also hard to extract those information. So the smaller classifiers have some problem extracting those information, while thanks to knowledge distillation, we can see that the speech tokenizer and knowledge distillation version of DAC got the semantic information, the high-level semantic information in the first layer. That's what we want. And so here are like some phoneme information, and in the other layers there is more like prosodic and other information about the audio. And the same goes for PNMI. What is a phoneme normalized mutual information? That again, in the first layer, there is we got it like separated from the other layers. So the phoneme information is mostly in the first one. So just to sum up, what we've done is that we find out that for audio reconstruction, the multi-resolution is not decreasing any quality, so it preserves the quality of the audio reconstruction. But we find out that we got this trade-off, that knowledge distillation is decreasing the quality a bit of the reconstruction. However, it really helps to distill the Hubert information into the codes, and we were able to improve our accuracy on many downstream tasks. And also, it helps to disentangle the layers. Now, Juraj will continue with analysis.
Having numbers from benchmarks and reconstruction metrics is good and very important, but it may be challenging to interpret or just get an intuition of what's going on with the model for us. So it's very important to actually hear the reconstructed audio with different configurations, different models, different quantization layers. So that's what I'll be showing now. Let's take DIC without knowledge distillation, our baseline. That's what we have started with. And the issue with this model was that it didn't disentangle the information. In every quantization layer, there was like a little bit of everything. When you'll hear, when I played the recording, that the reconstruction using only first out of 12 quantization layers have like a little bit of everything. It will be audio full of artifacts, not high quality, but you'll hear the speech, you'll hear the prosodic attributes of speech, and you'll hear, as I said, artifacts.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
Actually, it's not that. You may not be able to hear the artifacts on those speakers, but it's really apparent if you use headphones. I don't increase the volume, they do. Okay, I will play it again.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
So yeah, you can definitely hear the speech, hear the everything, but not in a great quality with only one quantizer layer. Now I will play the same recording, but using 4 quantizer layers. You will see that the quality will get better, but yet still there is like a little bit of everything. So I'll play the recording.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
So it's pretty good quality now. Now next I'll play with using all 12 quantizer layers. You will hear that the audio is actually flawless. The DIC without knowledge distillation is very good in terms of reconstruction quality and especially regarding speech. So first I will play the original one.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
And now I'll play the reconstructed one. You will hear no difference at all.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
Okay, so now let's take DIC with knowledge distillation, and what you will hear is some kind of robotic voice which is stripped of prosodic attributes of the speaker, but there is still all the semantic information. You will hear the speech. You will clearly hear what is she saying, but you maybe will be able to tell if she's male or female. I mean, you have already heard that she's female, but that's the thing. The information is disentangled in lower quantization layers. There are semantic information, speech, the content, and as we will add more quantization layers, prosodic attributes of speech will emerge, and you will be able to hear them. So now I will play.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
And to show out that the trade-off of lower quality is not that bad actually with the knowledge distillation, I will play the reconstructed audio using all, in this case, 8 quantized layers because it's enough apparently. And you'll hear that the quality is still very good, and I don't think you will hear the defects at all.
JSALT is the best workshop I've ever been to, especially because of the cookie breaks.
If you used quality headphones, you could maybe hear some artifacts and such, but I mean, it's pretty good. And to touch up on the knowledge of the disentanglement which we achieved, that in the lower quantization layers there are semantic information, in the higher quantization layers there are more prosodic attributes. We can actually show this off by taking 2 recordings and swapping embeddings of lower quantization layers. So what will happen, or what could happen, is we will like change the voice. The content will stay, but we will change the voices of those 2 recordings. So let's hear the first recording.
Perhaps you could put on your coat and walk out with me for a few minutes, said Trevelyan.
Let's hear the second recording.
The hospitality of the wigwam is only limited by the institution of war.
And now what you will hear is male voice, or some kind of male voice. It's not very clear, but with utterance of female voice.
Perhaps you could put on your coat and walk out with me for a few minutes, said Trevelyan.
I mean, it's not great quality, but that wasn't the main goal. This is just a neat feature of disentanglement, that we can swap those lower embeddings from lower layers and achieve some sort of changing voices. So yeah, to sum it up, we have achieved, the original DAC was really bad at disentangling information across the multiple quantization layers, though it was very good at reconstruction. And what we achieved was make the DAC better with knowledge distillation, so the information is disentangled in various quantization layers, but the reconstruction quality is still pretty high. So now Dominic will continue with.
Thank you, Rai, for interesting audios. So the last analysis that we did with the DAC model was with codebook utilization. So if these models usually suffer from low codebook utilization, which means that, for example, you have 1024 codes in one layer, which means you have 10 bits of information, but effectively you're using only 8 or 7 bits, which means you're not fully utilizing the bandwidth of the quantization layers, which then results in a lower reconstruction quality. It can be seen here that, for example, the original DAC model or DAC multi-res model, they achieved quite good codebook utilization compared to the knowledge distillation models. And I will tell you why in a minute. So actually, to make knowledge distillation work, okay, so we break the system.
No, don't worry. This happens in this room once in a while. I think it'll come right back. Yeah. Just wait a minute.
I think your audio broke the system.
No, this is a good occasion. On times it has blinked and not come back.
So as I mentioned, we had to do some tricks in order to make the knowledge distillation work. So as I mentioned, these audio codec models, they really suffer from codebook utilization problems. So what the authors of the DAC model did, they, instead of quantizing the embeddings in high dimensional space, concretely in 1024 dimensional space, they first down project the embeddings into only 8 dimensional space. then apply vector quantization, and then subsequently upsample it into back into 1024 dimensional space. Actually, this subsampling really helps with codebook utilization because at low dimensional space, the space is more clustered compared to the 1024 dimensional space, because we know that there is something called cursive dimensionality, which means that as we increase the dimensionality, the space volume grows exponentially. But on the other hand, if you're trying to distill the Hubert knowledge into the codebooks, we are actually observing the opposite. If you're using low dimensional, if you're using only 8-dimensional bottleneck, then we see that we cannot really distill the information from Hubert. So the y-axis here is the knowledge distillation loss. So it's quite high at the end of the training. But as we progressively increase the bottleneck size, we know that we can distill more knowledge from Hubert. This mainly comes from the fact that that maybe Hubert embeddings vary a lot more than these audio embeddings, and basically that's what causes the inability to distill the knowledge. But on the other hand, we have this bitrate efficiency or codebook utilization, which decreases as we increase the latent space. So there are two factors that are fighting each other. On the one hand, we cannot distill enough information from Hubert, but we will get high codebook utilization. But on the other, if we want to really distill the knowledge from Hubert, we really suffer from the codebook utilization. So this is one of the main challenges that we have to face, and currently we are working on fixing it, because we want to have at the same time high codebook utilization to really reconstruct high quality audio, but we still want to distill as much knowledge from Hubert as possible. So let me just conclude what we just presented. We showed you different neural audio codec architectures. We showed you both audio codecs and semantic codecs. We brought the semantic knowledge into the audio codec and also introduced this inductive bias into our model by using this language or linguistic hierarchy. And guys with the experiment showed you that the multi-resolution model doesn't really perform worse than the original DAC model. And also that with distillation, we are not really suffering the audio quality in terms of semantics that we are bringing into the model. And now I'd like to invite the guys that are going to explain you how to actually create language model on top of those audio tokens.
Dominic, before you go, I had a question for you. Okay. So if I remembered your results correctly, the probing results, if you will, you were doing reasonably well on pitch detection, right, with these models. But you're doing poorly on, compared to Hubert, let's say. But you're doing poorly on phoneme recognition. So that sort of puzzled me a little bit. So can you do some further analysis, or did you do any to figure out if you're getting pitch right as often as Hubert, but getting the phoneme wrong? Is basically, are you making errors within phoneme classes? Do you know what's going on?
Yeah. So I don't think we analyze into details like how phonemes are changed, or like whether there is some misalignment between the audio tokens and phonemes. So we'll have to analyze it more into depth.
You can use this.
So the other result that we have is the PNMI, which is actually pretty. So if you go to the PNMI slide, so this is the mutual information between the tokens and the phoneme alignments, which is actually with KD is pretty high. So I think we have to like understand what's going on with PER. Maybe there's some issue. Maybe there's some like issue with our training for PER probing. But the PNMI clearly shows that if you do distillation, then in the first layer you have a pretty high mutual information. Yeah. So are these the models that were trained on small data, or?
Oh, that's actually true. These models were trained with a small subset of data, and we are training the models on the whole Libre speech at the end. So actually, there's something to investigate as well.
Okay. All right. Thanks.
Okay, so hi everyone. So I want to present the team. So we are the team working on the generative part of our model. And our team is composed of Adele, who is with me here presenting, Laura, who is also over there, and we have two senior supervisors, Richard over there and Mikkel sitting over there. So so the codebook team, the codec team, made was explaining precisely how do we turn the audio into discrete representations. And now is our part on explaining how do we use those discrete representations to build a generative model. So here's the problem statement. We will train a language model on sequences of audio codec tokens, namely the output from the previous team. And we want this language model to be promptable through different modalities. Now, I will start with some background in the concepts on this problem statement, like to motivate our proposal. And we'll keep coming back to this, to the problem definition. So, let's start with the language model part. So first, some background on language models, something very brief. I guess the simplest way of defining a language model is just as a next word or next token prediction. So usually, this is how a language model task looks like. You have some input sequence. In this case, we have some text, although it doesn't have to be text. It can be any sort of discrete symbol. We have every time I fire a linguist, the performance of the ASR goes, and then there is blank. So the objective of the model should be to predict the upcoming token after that context. So what the model does is define a probability distribution where the whole vocabulary of possible continuations. So we see, for instance, that it assigns a very low probability to the token A or to the token, aardvark, I guess a place probably, and assigns higher probability to words that should make sense from the context, such as down or up. Now, the way that we train these models is to maximize the log likelihood of our data. So we gather a large corpus of token sequences, and we train them to do this next token prediction using a cross-entropy logic, which is essentially equivalent to that thing that we have over there. Now, language modeling is very interesting because it can be extremely multitask if you train it on a diverse enough data set. So, for instance, if we have this kind of inputs, you have the context of in my free time, I like to, and then there can be some possible continuations. And the model to choose one that makes sense, for instance, in this case, run versus banana, it has to be able to understand, like after this context, I should put a verb, an action. So it can get grammatic knowledge, same as semantic knowledge. From the example that we see over there, we can find word knowledge, so common facts, sentiment analysis, so understanding based on a context, like what is the feeling behind this chunk of text. And translation, for instance, if you have multilingual data, it's very common that you will find like pair samples. And if you're training your language model to predict like those pair samples, your model can be also a translation system while being a language model. So we like language models because of that, because it's a task that is very powerful and it can lead to learning a lot of very interesting things. And there is another reason why we like language models and why we chose them as actually, not only we, if you think of the generative modeling community, like language models have been overtaking everything over the last few years. And it's mainly because of this concept of scaling laws, or in a big part because of this concept of scaling laws. And scaling laws, what they tell us is that, I will explain a bit this plot that we have over there. So on the x-axis, we have compute, and you can think of it as the size of the model plus the size of the data set. And on the y-axis, you have the loss of the model. So essentially, this log likelihood that we had in the previous slide. And what this tells us is that as you increase the amount of compute that you use to train your models, the performance that you get, it consistently improves, and it also in a predictable fashion. So it tends to follow like this power law. Because here the axes are in logarithmic scale, so the line indicates a power law. So this was the conclusion of these guys who presented this paper. Language modeling performance improves smoothly as we increase the model size, the dataset size, and the amount of compute used for training. It's also something interesting that that improvement and the behavior on scale is not that much dependent on the specifics of the architecture. So that language models in itself, like there is a lot of magic in the task. Let's say, like just the task of language modeling, it has this very interesting property. And the summary of this is that we should expect to get a better language model if we scale up model size, dataset size, and so on. So this is another nice property that has been driving a lot of the progress on natural language processing over the last couple of years. And this is the reason why language models through scale have been meeting the state of the art on a lot of applications. And hence the reason why we also were motivated to use them as our generative model. Okay, so going back to the problem statement. So we said we want to build a language model on sequences of audio codec tokens. And that we call audio language models. And as a reminder, but I mean, it was just 10 minutes ago, so the codec team told you audio can also be tokens, right? Audio can be discretized into discrete representations. So if you have discrete tokens, as I mentioned, language modeling is not only constrained to text. You can apply it on top of any discrete representations. So we can use language models to learn to model and generate also audio sequences that have been discretized. And the process is essentially the same. You input your sequence of discrete token IDs to your language model, and the language model will define a probability distribution over the possible continuations in matters of in this case, the codes of the audio. Now here a very quick definition, because it's some terms that we will use afterwards. So we call semantic token audio language models to those that use the type of audio tokens that these guys described before. So from models like Hubert or Wave2Vec, that they mostly encode the linguistic information and they discard all of the paralinguistics and all of the extraacoustic variants. And we will codec audio language models to the ones that we will use a proper codec. So something that keeps all the information, including phonetics, paralinguistics, all of the recording conditions, and so on. So something like the previous team described. Now, there are some problems with audio language models in particular. So one of them is that they tend to have troubles modeling long-range dependencies. And there is, we have here an example that there is a finding that training audio language models, it is significantly more inefficient to learn like high-level linguistic features versus text language models. And we can see that here in this plot. So here is something very similar to the scaling laws that we had before. So on the x-axis, you have compute. So this is once again model sizes, dataset size. And on the y-axis, you have a task of, let's say, that evaluates the syntactic knowledge of the model. So it's knowledge of syntax, of grammar. And what we see is that, and we have on this line with the green spots, an audio language model. It's actually trained on semantic tokens, not on codec tokens. And the black spots are from text language models. And what we see is that for a given compute budget, like a text model is much more efficient, that gives much better performance than an audio language model. And not just that, but this ratio of their coefficients of their power laws indicates that they are, so if you take this ratio, it will give you roughly 3. So that tells us that speech language models or audio language models are up to 1,000 times less efficient than text language models to learn these sort of complex linguistic features with long-range dependencies. And there is another part of these issues with the language models. And it is that we want, for our specific problem, we want our language model to be promptable through different modalities. And this is how we usually do it when you have text language models. So these are 2 examples from the literature. And the procedure is fairly straightforward. So you can take, for instance, an image, pass it through an image encoder, and this can be your standard image feature extraction. So a vision transformer, a dyno model, convolution, a ResNet, something like that. Then you simply you keep frozen your image encoder. So this part is not trained. You do a linear projection that is trained, just a simple linear projection, and you project it to the embeddings, to the input embeddings of a text language model. And this has proven to be surprisingly efficient on allowing the text language model to retrieve, to understand the content of the images. And something very similar can happen in speech. You can have a speech signal, you pass it through a speech encoder, so a Hubert, Wave2Vec, whatever you choose. You similarly apply a linear projection, you project it to the input space of your text language model, and the language model is capable of generating text conditioned on that speech input. But our intuition is that if we will try to do something like that with audio language models, that is part of the goals of our project, it will be very hard. And the reason is something very similar to what Antonio was describing in his misalignment problem. So let's imagine that we have this image of a bell, and this blue bar encodes, let's say, the information in that image. And now we also have an audio of and this audio will be just the audio of a bell, the sound of just a 1-second recording of the sound of a bell. And now, these 2 signals are very different, but they have a latent feature in common. That is, they both can be mapped to the abstract concept of a bell. And this abstract concept is something that is roughly text-like, because text is sort of the encoding that we use to speak of these abstract concepts. And now, when we were doing something, for instance, like in the previous slide, that we take an image feature encoder and we project it linearly, it's doing something like this. We take the image feature extractor, we map it from the blue space to the green space, which is roughly text, because this type of models we tend to use, for instance, for classification, so they naturally tend to cluster things so that they correspond to categories. And since they correspond already roughly to the abstract concept, it's very easy to linearly map them to text, because these abstract concepts are something very, very close to text. But if we will want to do a similar thing, but mapping from the blue, so from the image space to the audio space, we'll probably first have to go to this common Latin variable, and then adding all of the extra information. So let's say like the pitch of the bell and these things that are not common between the image and the abstract concept. And yeah, this essentially will be like, we'll have to do the extra task of doing synthesis in representation space. So we think that using that sort of mapping for an audio language models will be very challenging. So based on this, we motivated our proposal. Our proposal is essentially this architecture that Samir has described at the beginning of the presentation, in which what we do is we model jointly text and audio. So essentially we rely on text language modeling to learn these long-range dependencies with high-level complex features, like syntax, semantics, all of these complex concepts. And we engineer the training data, so the tasks essentially in which we train our model, so that we can promote a knowledge transfer from the text domain to the audio domain. And then since we already have a text input space, we can apply the same procedures that you use to map other modalities to text language models in our case. So we can take an image and linearly map it to the input space of our language model, and then we expect to be able to have audio generation condition also on visual inputs. So roughly the two objectives, the big objectives are, first, enable the knowledge transfer between text and, well, this is an acronym for neural audio codec language models. And we also want to give vision capabilities to the neural audio codec language model using text as a sort of middleman, as an interface between the two of them. Now for the workshop, we have focused entirely on the first one. And this, yeah, we'll leave it as post-workshop things to do. So on the first one, we also chose to focus on speech because, I mean, we think it's a nice signal to consider in this case because first, it has a lot of underlying text information. So essentially speech has text plus another bunch of extra information. And we have large amounts of data. So in the audio domain, I guess that speech is one of the most abundant modalities that we have in both unpaired and paired setups. So we can have also these paired samples of text and speech that they will be useful for reasons that I will describe afterwards. And we have lots of benchmarks and lots of possible evaluations. So now I'll go into the description of the specifics of our model. So first, on the inputs. So text is just tokenized using a standard BP text tokenizer. So we input text and we get as output tokens with a value up to a vocabulary size. There is nothing special here. For the audio, we use a neural codec, so a residual vector quantization codec, meaning that for, let's say, each one of these being 10 milliseconds chunk of audio, so we will get for each 10 milliseconds, we will get 4 discrete values, so 4 tokens. And each one of those tokens is of 10 bits, so up to 1,000, from 0 up to 1,023. Now I want to go into how does a forward pass through the model look like. So as I mentioned, we process both text and audio, so the input to the model can be a text modality, audio modality, or a mixture of the two, as it is the case here. So we see we have the multi-code book input, which is the audio, and then the text tokens. Now, we follow just a standard procedure that you use to train a language model. So we embed those tokens. Namely, we map the integer values to a vector, to an embedding. The only particularity here is that since the audio inputs have more than one code per time step, we add up the embeddings across the different codes. And this makes sense because they were residual, so it makes sense to add them up to recover the original, well, something close to the original signal. Then the embeddings are passed through a decoder-only transformer, and this is your classical GPT llama type of thing, so just a transformer with causal masking. The transformer produces some contextual features that we linearly project to compute the predictions, and these predictions are just this probability distribution over our vocabulary size of tokens. And once again, the particularity is that since for audio tokens we have multiple codes per input, we have multiple projections of the output to map to the different codebooks. And finally, the model is trained as a standard language model for next token prediction using a standard cross-entropy loss. Now, as for the tasks, as I mentioned, language modeling is interesting because you can frame a lot of tasks as language modeling. So we did that. We did that here. We frame several tasks as language modeling. The first one is just the vanilla language modeling, so mainly unimodal generation, learning to model the density of a particular distribution of tokens, can be audio or text. And here the advantage is that we don't need any sort of paired data, supervised data. We just can rely on large amounts of unlabeled, untranscribed audio or speech. And then for the cases where we do have transcripts, we want to train the model to do some useful things. So for instance, conditional generation. So we can have this setup in which we have a prefix. Let's say in this case is audio. Let's say we want to do automatic speech recognition. So we'll have a prefix of audio. And the prefix, we pass it to the language model delimited by a couple of special tokens. So beginning of prefix and end of prefix. And the task of the language model is to predict the upcoming text tokens. So namely, transcribing, let's say, the speech. And you can have the opposite setup, and it will be something equivalent to TTS. If you deal with general audio, will be text condition audio generation or audio captioning. So a lot of things, a lot of tasks fit within this framework. And then finally, we have interleave generation. And this is not with a particular application in mind, in a downstream setup, but it's mostly because we want to promote the knowledge transfer between the two modalities. So what we do here is that, well, first we need to count with time alignments. That's important. And what we do is, let's say we have this input. So the sentence, it can be hello world. And we can have the audio representation of hello, the text representation of hello, and same for world. And we give the model, let's say, the first part as an audio. So hello is given the model as an audio. Then we pass it a special token indicated to switch modalities. And when the model receives the switch modality, it knows that it needs to continue the sequence, but this time in the opposite modality. So this time predicting, in this case, text, so the word world. And what we hope with this is that, it can be both ways, right? The switch can be between audio and text and audio. And what we hope with this is that the model will, since it needs to have a representation that randomly can be asked to predict upcoming audio tokens or upcoming text tokens, this representation should encode whatever that is mutual between those two modalities. So this task is mainly for the purpose of knowledge transfer in the language model. Now, these ideas don't come in a vacuum. Like, we have a lot of prior data on the literature, but the literature has been almost exclusively focused on language modeling on semantic audio tokens. So what we're doing here with the neural codex is new in that sense. So there is, for instance, a paper in which they show that you get much better convergence and much better losses if you initialize your audio language model from a pre-trained text language model. So just with a very simple initialization from a pre-trained model, you get already knowledge transfer. And similarly, there is another paper in which they propose something very similar to us. So namely this setup of having multiple tasks of interleave modalities between speech and text as input, also on language modeling on semantic tokens. And what they showed is that when you do that, you can beat the performance of a model that was trained exclusively on speech, meaning that you do get knowledge transfer from the text modality. So as for the workshop, like our main focus has been on first investigating the impact of the audio tokenizers in our task of language modeling and this objective of getting knowledge transfer. And assessing the effects of this multitask, multimodal language modeling that we're proposing. So first, we wanted to determine the feasibility of doing ASR and TTS as language modeling with codec language models, because it's something that, as far as we know, there is also no prior art in the literature. And we do it both in a single and multitask, so meaning a model that does only ASR or TTS, or a model that does ASR and TTS. And then we try to study the knowledge transfer across tasks and modalities. And now we give the word to Adel so that he can explain to you the experiments that we did online with this research access of us.
Thank you very much, Santiago. So now that you have all of the background about the project, the model, and how you can do a forward pass, let's move on to the research experiment. So let's recall the objective that we had is that we want to enable the knowledge transfer between text and neural audio codec language models. And one of the first research question that we wanted to explore is about the effect of audio tokenizer on the language model. Namely, we want to study the effect of bitrate and also see the effect of semantic knowledge distillation in the task of audio modeling. We want to work on multitask, multimodal language modeling, where we want to study doing ASA and TTS, and also to study knowledge transfer between those two tasks. So a bit of context about our experiment is that during this workshop, we've been mainly focusing on small-scale experiment. We use only 6.5K hours of audio, so with the transcription, which is very few with respect to the literature. And our model, they range from 150 million to 350 million parameters, so it's really shallow in comparison to pre-trained text language models that can go up to 1 billion of tokens, parameters. One thing is that there is a huge computational challenge. Because we do require timestamp alignment, you need to extract those, and we were using MMS force aligner, which needs to use GPUs. And for instance, if you don't want to wait for 1 month, you need to use a lot of V100 GPUs. So here in our case, when we try to extract on Libri heavy large set, we had to use 400 GPUs. And also, if you want to train models, you need a lot of A100, which is not usually the case when you are an academic. We are usually GPU poor. I wanted to show that in the previous slide of Santiago, he mentioned a paper called Twist, where we do see benefits of using text language model for audio language modeling. And in their paper, they use 100 GPU with 150K hours of data. So we are really in a small scale setup, but we plan in the future to scale. And how are we going to do it? Is that because thanks to this workshop, we've been during the first couple of weeks making up the code base from scratch. So we developed our own toolkit to do multitask language modeling with audio and text. And we really try to optimize everything so that in the future, we can really scale to billion of parameters. So for instance, if model flop utilization, trying to make it compatible with torch.compile, and also a lot of engineering that was required in order to pursue this workshop and also after the workshop. So getting back to the research question, so the first research question is how does the audio tokenizer impact the audio modeling task? We consider 3 different tokenizers. The first one is semantic tokens. So you already heard about those tokenizers in the previous presentation, codec and hybrid. Hybrid meaning that you have distillation of semantic tokens across the codebook. And we use the semantic baseline because we wanted to explore the result of the Twist paper where they showed the benefits of using TextLM on audio modeling. So we wanted to reproduce this experiment to see if at our scale, can we see also these benefits. So the setup for this experiment has the following. We use GPT-2, so 150 million of parameters, so the small one, trained on only 10K steps, so it's roughly 15 epochs of Libre speech. So Libre speech is 1,000 hours. And each experiment is using 18100. As I said, small scale experiment, but we do believe that in the future we could scale with more data and see maybe more things. So this first chart is a comparison of DAC and also speech tokenizer and Hubert. You can see, so on the y-axis, it's the number of steps, and then there is the loss of the cross-entropy loss. You can see at the very bottom, so the blue curve, that the semantic token from Hubert obtain the best cross-entropy because it's much easier to disentangle because there's no other information, it's only semantics token, so it's easier for the model to process them. While for discrete audio codec, so tokenizer using codebooks, you can see that it's much harder for the model. But we can see that with a speech tokenizer, thanks to this distillation, we can see that the model can benefit from this distillation and reach result that can be more competitive than DAC that is getting stuck at this loss. One thing is that DAC is using 12 codebooks, while speech tokenizer is only using 8. So one thing is that it might be due to the number of codebooks or the number of bits that the language model has to process. And so we did an experiment in which we are
downsampling, so we are using DAC with 12 codebooks and DAC with 8 codebooks compared to speech tokenizer with 8 codebooks. So trying to understand like the effect of distillation on the task of audio modeling. And you can see at the very top that even by decreasing the number of codebook, it doesn't yield to result as good as the one from speech tokenizer. But you know, losses, sometimes it's not always a way to understand how qualitative the model can be. And so I propose to you to just listen to some audio sample from this model. So the setup is really simple. We use DEC model and speech tokenizer, so both with only 8 codebooks, trained on 10K steps of LibreSpeech. And we randomly chose like a sample from the validation set of LibreSpeech, and we conditioned the model on 2 seconds of the audio. So the full sample that we are using is the following one.
Dance by way of showing the gossoons which she had seen in the fairy rings at night.
Even for me, it's hard sometimes to understand. So I guess that for models, it can be also challenging. Yep.
Dance by way of showing the gossoons which she had seen in the fairy rings at night.
So it can be a challenging one. And when you take the prompt, so 2 seconds of the audio.
Dance by way of showing the gossoons.
So you can see it can be hard for the model to try to generate new audio tokens. So these are the results with DAC, so 8 codebooks.
Alvin's, you read the Torah.
So it's really, really bad. Like it fails to catch up to preserve like speaker information and just to generate coherent content. And with speech tokenizer, and just remind that you need to remember that they use the same number of steps on the same data set and the same number of codebooks.
Past her night of quickness of the person, she couldn't crack to them with the verses some all. And then, and down morning that you from the hut.
So with speech tokenizer, you can keep more information about the speaker, about trying to condition of the audio, and you can also have, we can recognize words. It's not proper English, but we can recognize words. And then, so that's all of these results are motivating the choice of using speech tokenizer for our next experiment. And then we have, we studied the effect of warm initialization, so using GPT-2 as a pre-trained model against random GPT-2 on all of the different audio tokenizers. So we really wanted to understand if we were seeing a benefit of using a pre-trained language model. So what we can see first is that for DAC, we don't see any benefits of using a pre-trained text language model. Our intuition is that since the tokens are very different, so they don't necessarily encode in the first layer, the first codebook semantic, it can be hard for the model to disentangle the information, so to reuse text knowledge to do the task. But for the other two, we can see that there is those benefits. For sure, for Hubert, we can see it. For speech tokenizer, we can see a benefit, but it's still very small. So we plan to see at larger scale if we can really see a benefit on this specific tokenizer. Okay, so to wrap up about this experiment, so we've seen that audio tokenizer, so the choice of using audio tokenizer can greatly impact language model performance. So if you use the wrong one, then you might not get the expected results. And in terms of differences, we can see that speech tokenizer can really yield to better performances in terms of audio language modeling. And for some runs, for some experiments, we can see a faster convergence when using warm text language model, but we need to scale a bit more because we expect to see a larger transfer, but it's not sure. We have to do the experiment. So moving on the multitask part and also about training on downstream tasks such as ASA and TTS. So the first question was really, can we train a neural audio codec language model to perform ASR, TTS, and other tasks? And can we also benefit from using both of these two tasks together? So the task that we are continuing is our ASR and TTS. We use LibreSpeech and also LibreHeavy, small and medium, so roughly speaking 6.5K hours of data, annotated data. We use the official set of LibreSpeech dev and test for the evaluation.
And the architecture of the decoder-only model is a llama of 150 million parameters trained on 30 case steps, so 10 epochs. And we use for each experiment 2 8100 for 48 hours. For the evaluation metrics, we use the order rate, so lower is better. It gives you, it quantifies how well the system has transcribed spoken word into text. And we consider the following top lines. So the first one is Whisper, large V2. It's an decoder of 1.5B parameters trained on a lot of data. Brainstormer, this is a from-scratch model trained on LibreSpeech of roughly 350 million parameters. And finally, SpiritLM, which is a new paper that is using pre-trained llama to perform audio and text tokens, so different tasks, ASR, TTS, unimodal generation, that is trained on 570K hours of data. So we use way less hours data, and also our model are smaller, so you need to take this into account. So the results are the following. You can see first that, as expected, the top lines got very nice results. For SpiritLM, we don't display the dev clean and the dev loader because the model is not open source, so we directly reused the claim numbers. And when we look at our baseline, so NICLM, we can see that the model can actually learn to perform ASR with only 150 million parameters, and also with only 6K hours of data, which, as I said, is very small, given what has been demonstrated by Santiago earlier and the scaling laws of audio models. It can achieve great performances, but we expect still to get even better in the future. Regarding text-to-speech, we use the order rate, so this way we can know about how well the model can learn about the semantics and the linguistic. And then we also use the mean opinion score, which goes from 1 to 5 and gives you the information about what is the quality of the audio. So we want to study the quality and also like the content, the linguistic of the model. So the top line are the following. So we use BARC large, which is an open weight transformer-based TTS model. So 1 billion of tokens. Billion of parameters. SpeechGPT, a pre-trained llama of 13 billion of parameters trained on 60K hours of data, and also SpiritLM. So still keep in mind, we are using way less data and also parameters. So the results are the following. So as I explained earlier, like SpiritLM, it's not open source, so we could only display the order rate. So as expected, we are seeing from BARC and SpiritLM better results across TTS because they just use more data, and for BARC it's only solely working on TTS. For SpeechGPT, we were surprised to see that it doesn't actually work that well. So on the task of TTS, it has very bad order rate, and even the MOS is not that high. And in comparison of us, so the last row, we got a order rate of 40%, but we actually think that we can go lower, that actually the system can be lower because this system is currently doing a lot of insertion because it doesn't predict the EOS due to the codebook pattern. But this is something that we are aware and we will fix this. But for the MOS, we can see better MOS, but equivalent to the BARC one, but with a higher standard deviation. And this can be due to the fact that the model is not conditioned on a single speaker, but it can generate multiple speakers at each generation. Let's look at some samples that the model can generate. So the first one is, may the force be with you.
May the force be with you.
So you can see that it can generate like coherent speech and also have nice paralinguistic information. And then the second one is about life is like riding a bicycle. To keep your balance, you must keep moving. A famous quote by Einstein. Yeah.
Life is like riding a bicycle. To keep your balance, you must keep moving. You must keep.
Yeah, you can see that at the end, like it didn't predict the EOS, so it can still continue to generate. But we are kind of happy to see these results. They are encouraging. So now, can such a model perform multitask learning? It will be very quick, but still on the same task, ASR and TTS. What we've seen, so with the setup that we use, it's the same one,
except that now we use a multitask llama model, same number of parameters, less number of steps that is being achieved, and same setup of GPUs. And we can see that in terms of perplexity, the blue curve is the ASR one that you've seen earlier, and the green curve is the ASR one that you can see, ASR plus TTS. So this plot is only on ASR. And you can see that actually the model is, at the beginning, really starting to learn about both tasks and also can benefit from using TTS to perform ASR. We don't see a degradation. And for text-to-speech, we do see a similar pattern. But in this case, if we continue the training, we can see that at some point it will plateau and both of them will be at the same convergence point. So to wrap up, we've seen that a language model can learn to perform the task of ASA and TTS using audio codecs tokens. And we can also see some early benefits from using multitask learning, but we expect to see more with more compute and more data sets. And we also have like other results on mono audio, mono text, and interleaving, but because they are very early, we decided to postpone them for the presentation. So in terms of key takeaway of the presentation, we can see that for the task of audio language modeling, using an audio tokenizer, you need to find the right one. Otherwise, you might get in trouble for the model. The model can also learn to do ASR and TTS, and you can see benefits in the multitask regime. And also, we've seen throughout the presentation some early transfer of pre-trained text knowledge to audio, to the task of audio. So what next? One point is that we need to overcome this bottleneck of scaling. As I said, we've really spent a lot of time during the first week of the workshop making sure that our model works, that everything can scale. And now we are really in the moment where we can increase the number of parameters, we can increase the number of data. So we hope to see new and stronger results in the future. So that's the thing. We have more than 120 experiments that we need, with results that we need to analyze carefully with multitask using all of the combination that you can think about different tasks. But we need to take the time to learn about them and see what we can extract from them. And then we also have a lot of potential ideas that we want to explore. One of them is we want to see how to, because it's hard for the language model to align audio tokens to BPEs. So we may want to find a new way to, instead of doing BPEs, to use characters, because the model we've seen that the model can align audio with characters more easily than with BPEs. So thank you very much. If you have any question, please feel free to let us know. And I hope that you enjoy the presentation.
Questions?
Okay, thank you guys for the talk and some insightful results. I have a specific questions regarding applying the discrete audio codec into downstream task. So first, there's a knowledge distillation audio codec that you guys developed, and it basically trying to learn the content, transfer the content embedding from Hubert to the first layer of codec. So when you applied it to speaker recognition task and emotion recognition task, do you think if we use the rest of the codecs, like the 7 layers, other than the first layers, will the performance improve?
So let me just repeat if I understand the question. So you're saying that if we don't use the first layer, only the last 7 or like last n-1s, if the performance on those tasks improves, right?
Yep.
So you're comparing it to the model without distillation, right?
Yes.
So we've seen, for example, on like for example, pitch classification improved.
Mhm.
But I'm not sure if emotion improves or even the phoneme recognition. Or what was the another task? Speaker recognition.
Yeah.
So the thing is that we didn't see this improvement, and we need to analyze it even further. But given that we are subtracting, like kind of first, distilling the knowledge from Hubert to the first layer, then we may expect that more speaker-related information is kind of like fine audio details will be distributed across the codebook.
Yes.
So we, I guess, have some numbers regarding just summing all the subsequent layers and then trying to perform probing on those layers, but we all need to analyze them because we mainly focus on analyzing these knowledge distillation results.
I see. So the classifier you built is actually based on all the layers.
The classifier we built, like we have two kind of probings. The first one is using all the quantization layers and summing them up, which means the quantized embedding at the end. And the another one was per layer.
Mhm.
But we perform, I don't remember if you perform speaker ID per layer. Okay.
Interesting.
Yeah, we don't have per layer, but we have.
I see.
Do you know the result for per rest of the speaker? Okay.
Yeah.
As far as I remember, I don't remember that it was better. It was. I remember that after the ZQ, after the whole all layers summed up, it was better than from the first or from the rest, like -0 layer.
I see.
So like basically using all the layers can improve compared to using only first one, but well, I guess we will need to analyze these results even more.
Yeah, that would be some. I think it will be some interesting results.
No,
from
definitely.
that.
So we did do layer-wise probing, but for speaker ID in particular, like we were surprised to see low performance. We were hoping to get pretty good performance. So we need to investigate that particular task more. But we did do layer-wise probing, and we did not see any kind of interesting trends. So we just did not present it.
Cool. Yeah. And another question is, can we play the audio, like when you were switching to
The
layers
swapping,
of
yeah.
the layer? Can we play the audio again?
This is the purely generative one where you just start generating audio.
No,
No, it's like the swapping of
yeah,
the content and
swapping
style.
the two code books of the original speech.
If you hear, intently, you can actually hear the words from the other utterance.
Yeah.
After this slide. Yeah. So, do you want to play the original or
Play
just
the last one,
the
can
swap?
we?
Okay.
Thank you.
Perhaps you could put on your clothes and go out with me for a few minutes, etc.
So, what is the source of this audio? Is it from the male or female?
This is from the content is from the female speaker.
I see.
And the voice is supposed to be, the style is supposed to be from this male speaker.
I see.
So that's the content.
Perhaps you could put on your coat and walk out with me for a few minutes, said Trevelyan.
And this is the style supposed to be.
The hospitality of the wigwam is only limited by the institution of war.
So the gender is changed.
Sorry.
So the gender is changed by just swapping the first two quantization
So by
layers.
swapping, we actually want the content of this utterance to be in this style. Basically.
Yes.
But yeah.
That's great.
Yeah. So that's why we hear the words from that utterance. I mean, if you hear closely, it's not very clear, but it's like some sign of disentanglement, and we want to investigate.
Yeah, it already has.
Yeah.
Nice.
Perhaps you could put on your clothes and go out with me for a few minutes, etc.
Great. And can I ask one more question? Yeah,
Yeah,
thank
of
you.
course.
So regarding the design of the model, the distillation, knowledge distillation, I think just for discussion. So do you think if we use let the Hubert model use the exact same use the same share codebook, the first codebook, and then train another VAE model.
Yeah.
Just based on the reconstructing the Hubert features.
Yeah.
Does that also work?
So you want to initialize the first quantization layer with the features from Hubert, or a codebook that is initialized with Hubert features?
So let's say we have another VAE VAE model.
Okay.
And it basically trying to learn codebooks from the Hubert features.
So it's compressing Hubert features.
Yeah,
into
compressing
some
Hubert feature and reconstructing.
Yeah, and we
Hubert
use that
features.
codebook to initialize the VQ-GAN model, for example.
Or maybe share the same codebook and train it together.
So we did think about those type of ideas, and those are like on our to-do list. But I mean, if you're interested, we can discuss more about that. Yeah,
Yeah,
I think we were thinking about those things, right? Like if we initialize the codebook with like Hubert features, or in this case, like from some other model that is compressing Hubert. Yeah, did we try those? No, I don't think so. Yeah. So, but here we can discuss more about this.
Yeah, thank you.
Yeah, of course.
Also, to the knowledge, to the initialization by Hubert, it's kind of tricky, because if you initialize the codebook using Hubert, then the distribution of Hubert is quite different from the DAC model, and we are distilling and matching only in the angular space, not like we are not matching the magnitude of the embeddings. So it may be also tricky to initialize these embeddings, because as I mentioned, Hubert has kind of different distribution of embeddings compared to these neural audio codec.
I have a question, but I'm looking at the audience to see if anybody else does. Okay, let me ask mine. Adil, maybe you should go back forward one or two slides. There was one where you played examples and I had some questions. This was where you're producing like English-like nonsense. So I guess I'll start talking. So one of the things I buy is that when it comes to just generative tasks, TTS, this one. TTS is reasonably well defined. You know the words, and if you have a little bit more information about the speaker and some other prosodic tags on it, then sure, you can have a generative model generated. Next, if you need to generate text in response to other text, like dialogue, maybe that's, like you said, because it's discrete, it's good. But to generate audio, you have this whole other dimension that's not there in the discrete tokens, and some of it was being described. So can you tell me again what the setup was for this? So how is the continuation being done here? You get a discrete set of words and then you continue audio, or do you get audio and then continue audio?
So we randomly sample an audio from the validation set.
Yeah.
And then we fit this audio inside of DAC or speech tokenizer. So we get the codecs. And then we only select up to a certain number of codebooks. So in this case, DAC, it was 8. And then we feed it inside of the model that has been trained on using 8 codebooks from this particular tokenizer. And then the model has to continue from the 2 seconds of audio that it sees to continue for 500 tokens.
Right. So I guess what you're saying essentially is that you have, of course, the audio is discretized, but you have some real audio samples as a prompt, and you're then asking the model to continue it, right? But you also had other things where you were swapping the thing. You're saying predicts the word tokens and so on, right? Did you finish that training, or?
You mean for the TTS one?
No, what I'm thinking is if you give it some audio tokens as input and then switch and say produce the next words.
Oh, yeah, so the interleaving pattern.
Yeah.
We might have some available, but the thing is that interleaving pattern strategy was a bit very slow to implement.
Okay.
So we have some training runs that goes until 15K steps, but we don't think that it is the model is actually really learning to do the task properly. So, but we expect that at the end it can do this switch. This switch.
I mean, what I was thinking conceptually was that if I had a sequence of audio tokens and I wanted to continue them, the way I might want to do it to make the learning task easier is take the audio tokens, make it do the transcription, make it continue the word tokens, and then synthesize what it continued. So that way you're breaking it down into a couple of relatively easier generation tasks. Yeah. So ASR is relatively easier because you need to transcribe. Text generation is relatively easier because, well, at least there's proof that LLMs can do it, and then synthesis. So I was just going to ask if you tried it, But the answer, I suppose, is you still have some computing issues.
Yeah,
so-
yeah.
Okay. So- Yeah, come up. You should actually, you guys should just stay there. Don't rush back to your seats.
I was just saying, like, there's some evidence in literature of, this idea, like the audio palm paper from Google. It breaks down a more complicated task into a cascaded task in the language model as well, and they found that they can do better, translation.
Okay.
But actually, I mean, something that we want to do is precisely get rid of that need of going to text as an intermediate. So we like to be able to do the full audio continuation, staying all the time in the audio domain.
No, you don't have to do it as an explicit task. It can be implicit.
For training, makes sense.
I mean, you do it for training and also just make it an implicit task. I mean, the real task is still to continue the audio, but let the model generate intermediate tokens.
So, I mean, you expected that from doing that, it will learn afterwards to continue the audio, just condition, let's say, on previous.
Yeah, for example, what I'm thinking is that you'll get the benefit of the text language model in at least figuring out semantically, well, don't like the word semantic in this context. I like lexical because semantic to me means a whole other thing. But at least the lexical continuations, you know how to do it because you've trained on 1 trillion word tokens or whatever it is. And then that at least gives you an anchor for synthesizing the speech. Otherwise, you're relying on this complete hidden transfer that may or may not have occurred. Shankar, come on up.
Yeah, my concern will be that afterwards, the model will, so if you just train it to generate the text and the audio, I don't really expect it to generalize afterwards.
Yeah, just a +1 to what Sanjeev said. Okay. For text, if I'm doing grammar correction, it makes a lot of sense to explain what the correction is. So people have or math reasoning. So in text-only tasks, the same decomposition has helped a lot because the model now has to it has less chance of hallucination. That's one way of thinking about it.
I see. So you're saying this is more the benefit of, what is it called? Jason, what's the name of that where you explained your steps?
A chain of thought.
Chain of thought.
Yeah. Exactly. It's one instance.
Okay. Yeah, it's interesting. Yeah.
Come on up. This is meant to be a free discussion with lots of people jumping in and shouting at each other.
Just thinking of, ASR and TTS and controlled output to avoid this hallucination and, prompt something you cannot control. Have you guys thought of a speech editing where you prompt it with a speech prompt and you want to replace being happy, say excited, or, add some, control the emotion of the speech? How could this fit in this training paradigm on what you have mentioned?
I mean, it can fit. It can be, it's one of many tasks that you can frame as language modeling, right? So, and it's one that for sure will be, I don't know if we had it on the original setup of the task that the model was
So that's
supposed
what
to.
I was going to say. So actually, we focused on these two tasks, but actually the goal is to frame different speech processing and audio generation tasks as sequence-to-sequence mapping problems and train a single model on that. So, you can think of T5 model from Google, which converts all text processing tasks into a sequence-to-sequence mapping, and that model can actually learn pretty interesting representations. Actually, that's our original goal. So that task is also, should be added to the mix. Yeah.
So pushing it a little bit further, when it comes to things like multilingual or code switching, how can this be addressed in this scenario as well? Because you have done some tokenization early and there is language dependency.
I think that's probably we'll have to think more about, but do you guys have any comments on that?
I mean, you have multilingual tokenizers, right? So
in particular,
it doesn't have to be an issue.
Particularly about code switching.
I'm thinking of this.
I'm not sure. Yeah.
I don't know either. I'm just asking.
But yeah, once we have an initial, multitask model, I think those type of issues can be addressed after that as well. Yeah, I think it would be interesting to see what kind of things model can do.
So I want to ask some implementation details of the inference process. So basically, you have 4 or 8 codes. So after the LLM output will output maybe 4 different kinds of tokens. And how do you select the tokens to generate for the next step generation? Because there are 4 of 8.
Yeah, but you're predicting the 4 of them in parallel.
Yeah.
So I mean, at the given time
The
step,
maximum one?
Sorry?
Are you selecting the maximum one?
No, it's just, I mean, because your input are 4 codebooks, right?
Yes.
Your output are also 4 codebooks.
Yes.
So you just take the output and feed it back at the input, as in usual language modeling.
Oh,
so the model
each
receives
code is independent?
Actually, I mean, that's a detail that we didn't mention here, that the codebooks are actually, since they are residual, they are not really independent, right?
Yeah.
So you need to deal with that, and what we do is to use some, maybe we have this slide over there somewhere. Yeah, I mean, this because we had a slide on that, but we didn't have the time to go through it. But you apply some patterns to the codebooks.
Yeah.
So that you apply a delay, for instance, to the second codebook, you apply a delay of 1. To the third one, a delay of 3. And then you end up removing that. I mean, you keep the dependencies of, let's say, the second code of the first input depends on the first code of the first input, right? And then you just play first the first input. And then one step afterwards, you will be using it to predict the second codebook. Yeah.
I see.
You don't have it? Okay. Well.
Okay.
No,
yeah,
I
but
think
that's
the picture is simple. You think of it as doing predictions in the dimension of the vector, as well as in time simultaneously. So at time 2, you're predicting the second coefficient of the first vector and the first coefficient of the second vector, and then so on and so forth.
So just as a point of reference, I think you can look at the paper called Music Gen from Meta. They actually look at these different patterns of how you model the code books.
Okay, any more questions? Well, yes, this has been a good session, a lot of discussion. That's always good to see. It's a good sign that people are following and are excited about your results. So let's thank all the presenters once again. Samir, do you have closing remarks or no? Okay, all right. Well, in that case, thank you very much. Let me put back the agenda slide so that you guys can see what's happening. Okay, so we are at the 12:30 mark, so it's the lunch break. Lunch options are very simple. If you want to do a quick in and out like John's team because they're coming back to talk, north of here is Levering. You can go get food, eat, come back. You'll be back in 45 minutes. Next option is due east. You can go to St. Paul Street. There are a number of restaurants there. Takes a little bit longer. And then the third option is to go south. It's called Our House, R for Remington. And there's a food court with nice food over there. Both St. Paul and Remington will probably take most of the 1.5 hours. So it takes like an hour 15. That's my estimate over the years. So those are your 3 choices. And if you're done with the session and you're going home, 83 is due west. Okay, all right. So I'll see you all let's get here a few minutes before 2 so that we can start right on the dot at 2 o'clock. Right? Okay. And once again, Samir, Antoine, rest of the team, excellent presentation. Thank you, guys. And we'll hear from John and his team at 2 o'clock.
Yeah, we can do a lot of time. Much chaos happening. Basically, the switch groups in all industry places are we have like 1 year. That's basically what it is. You have 1 year. Reinvent yourself.
Sanjay?
Yeah.
Is this the laptop we're all supposed to present on?
This would be the preferred laptop.
Okay, this is not the laptop. This is not the laptop of somebody from the last team.
No, this is mine.
This is yours.
Yeah.
Okay.
Yeah.
Can
However, if you do want to use your laptop, we need a big break. I did this because we didn't have time between their talk and mine.
We don't have to switch laptops. But
Yeah.
can I play with your laptop to see
Yeah,
if
absolutely.
everything will run on it?
Yeah, that you may very well do.
Thank you.
And I haven't, there's a browser open with your thing on it. I haven't downloaded it yet.
Well, okay. We will probably need two browsers open
Okay.
for our demo.
Let me do this for tomorrow. The thing is that between sessions we can change laptops. The main thing is he does something, connects the audio in this, and does some configuration stuff.
It may be okay to use your laptop as long as we can open up some windows on the header.
Yeah, yeah.
I just want to check that
Yeah.
the thing works on your laptop.
Go ahead, yeah. Yeah, yes, Thomas, sorry.
Yeah.
By the way, if there's any issue, you can always do this. You know how Paula has a seminar. So Najim is the instructor of record. Sorry, Paula is the instructor of record.
That's what we did last year when I was a postdoc. Loreano was the instructor. But I was thinking if I might have like other students, and that's my mistake.
When they want to take on students, I want them to have a section.
So what how to work with our faculty for research in the CSP website. Like a page where you have, like, how to work with our faculty with the process in okay, you need to get it, MSc or CS, choose, contact us at which, and like, that might also maybe encourage research students.
How about you do this? How about you use the fact that you're doing this to streamline our process?
That might be very
What they usually do, and I can send, for example, Pablo a list of you and Paula and whoever. So, for example, like, Martha now has an advisory. So you can just say in the section position and the section number something. You know how it is.
There is a in.faculty.
So that is the course number.
Oh, yeah,
the section number is the instructor. So the way we do teaching credits is everybody teaching credits is 520.800. And then .01, .07 is somebody on 30 last section number. So that's what we do. We create an independent research course and we just get all of us.
Yeah, that might be
one for the undergraduate level, one for the graduate level. All right.
Trying to find out how to have like mental or the graduate
All of you are there. So what you need to do is just say, these people are going to supervise and and that's why the credit is very easy faculty will be giving you to you. And then you go from there. And how else you will supervise undergraduate research. Whatever level you're approved at, you're approved for undergraduate only, you only get undergraduate.
That's ready, and then like introduce the concept of maybe we need to streamline that for CSP in general, and discussion is
Is it working okay?
I think so, yeah.
Okay. Do you play any audio? No. Good. I mean, otherwise I was going to ask you to test the audio. If it's only video, then as long as it works on this screen, they will make it work.
So I use like, how do I go to, when I'm full screen, Is there a keystroke that lets me go to the previous tab and the next tab?
No, you do escape. What are you? Are you in the browser?
I'm in the browser and I full screened it.
Oh, okay. Then no. Okay, go ahead. Go ahead. Full screen it.
Yeah.
Okay. I believe that this command angle bracket should.
No, those are kind of like back and forth. I want to go to the other tabs, not history.
Hold on. Okay, go back. Hold on. You're still there, right?
Yeah, that will go to other applications. I want to go to other tabs.
No, I know exactly what you want.
Sorry.
Trying to see if I have muscle memory.
I mean, it just show you the tabs.
No, I can't remember.
My browser doesn't work this way, even when I use Mac. There may be a setting. Select, oh, hang on, it should. That looks like shift tab. Yeah. No, sorry, sorry, control, just control from here. Yeah, which I've never. There you go. Okay, there we go. All right. Okay, thanks.
Okay, tab for tab. Maybe that's that.
Well, right, it's just I've never actually seen anybody use this control key.
No, I use it for a number of other things.
Okay, here is the default interface. Yeah. Here's our interface. Look, relevant stuff popping up.
Ruth is here. I'm going to go say hello to her.
Very good.
one code to go there, and it will ring, and then the other code will go there. There's only one data factor there, but you have to put the code over there. Now, the reason we don't do that, I didn't do that in the past, is because design the optimal code was very hard. Because numerical optimization problem is very hard. You can write down the distortion equation, and you can find the code that says that. Distortion is given by a statistical number. And that optimization problem doesn't have a good solution. But that's because in those days, we used to do anything analytical. If you can do gradient descent in the code base, so you're just putting something which approximates, basically you need a cost function which is a whole lot smaller than so that going far away is much more costly if it's more. Then what happens is that you say, okay, let me give up some code points over here because I'm really using all of those that. Oh, yeah, yeah. That's all the things exactly as I said. The optimal concept of what's the best, and that's what you have to do. So you need to do that way in the past. divide the space into two parts, this gets a 0 and this gets a 1. Divide that into two parts, then it is an and this gets a 0 and this gets a 1. Yes, so basically the idea about the birthday of this instrument how we convert. So then what you do is you basically have a digital to analog ADC converter, just a level. Is it above this level or below this level? First bit is 0. Is it above this or below that? Next bit is 1. Next bit is 0. So you can do this and you can have a flash converter, which basically in parallel gets you all 16 bits of quantized value. And each of these comparators is just at the right level. And some of them are conditional and so on. So basically, so what you do is, so on the binary tree, you have the thousand. And each one you have the thousand things. You take that and you add it up. Yeah, it's still in the data basically quite hierarchical. So that that also makes sense in the later part where you try to do the second improvement from the first one. It's basically putting in the first term overall there where the data is given this from here. Within this, how the distribution is done. You have a different orientation.
Oh, okay, thanks. I still probably have one.
My feeling is the time will come for free because the speaker that just code words does something different. Next time you're probably in the same code words and slightly different part. And this is cool. I'm going to get the basically, one is coming from our speaker, the other is coming from the speaker. But it's coming from the current speaker, but it's all motivated by the first code word of the source speaker. The content comes from the first, and how to synthesize it, well, how does that speaker synthesize something that they were trying to say here? And it's simply a matter of choosing different speakers with different setups. Got back early.
I wanted to make sure, because one or two of my team members was going to come back early.
So here's what it is, John. So
Yeah.
everything is on my laptop now.
Okay.
But since we have a break, if you want to switch, you can switch to your laptop.
You know,
Would you rather do that?
I have no strong preference.
Okay.
Let's see. So your laptop, you've loaded the slides and Google Slides, is that right? Yeah, it would certainly.
So let me do this. Should I download them or because they are in Google Slides right now?
Yeah, I actually think they'll load better on Google Slides because I think they'll pre-cache the videos for you and that sort of thing.
It's here.
Also, people are still making edits.
Okay.
Which of course should be expected at this point. Yep.
How about this? Like in another half hour,
Yeah.
Why don't you test run the whole thing yourself?
Perfect. Yep. I'm happy to do that.
I mean, it's not complicated. The only thing these guys want to do is they connect this USB-C to your laptop, which in turn is connected to that box they have inside.
Oh, I see.
And that box is connected to this display, their outgoing stream,
I see.
and other stuff.
Okay.
So the audio that you play out of here comes out of these loudspeakers and also goes out. Basically, they're doing the broadcast from their station. And
Right.
that everything needs to go into the broadcast.
I see.
That's
see.
it.
Yeah, that sounds fair.
Yeah, so what he did is he connected the USB-C, then he did some display configuration and audio configuration in my laptop.
Okay.
So that my default audio is my headphone.
Okay.
And my default video is that USB-C.
I see.
So my screen gets mirrored.
Perfect. Okay, so it's a mirror. Perfect.
Yeah.
Okay, that's good. And it's not going to show up on this PC.
No. The PC is just for the room projectors. Yeah, the PC is doing it. In fact, we end up choosing HDMI for the PC.
Okay, sounds good.
Yeah. Yeah, speak. Yeah. She's getting nervous.
Well, yeah, I mean, I asked her to make one figure outlining
No, that's okay. Whether she's speaking or not, that's what you want to do. You want to coach her some more?
Yeah, okay.
That's not right.
No, I know. I follow all of that.
No, I know. Me, she wants to. Not all the way back. Yeah. She's doing much better now, I think. I don't know her well, but
Yeah, exactly.
she's doing a whole lot better than she was even in March.
Yeah, no, for sure. Yeah, I remember. But yeah. Oh, okay. The other thing, I don't know, so there's a couple of things that I don't know if Charlie or Selena or some of the others have mentioned. One is that we have two web apps that are basically live on our resource. And it costs a lot.
No. We'll fund it. Like, if it's a few $100 or whatever per month, if it's in that ballpark, then we can do it for like a year. by then we'll find it. So
that sounds good. The other thing is that
what we'll do for that is the best way to do it is to talk to Paula and Danny and set up so that the billing comes straight to us.
Yeah, so we should do that. The second thing is that a lot of SAE work, as far as all that which actually was just submitted. Perfect. So I very much but it's they did bring up a fire bill. Yep. So I don't know how to tell this one too. But I mean, I think we have.
Jason also is that he also again it's on your breast of your
Okay. I think yeah. And let me know if
no, so let's get all the things that I do. Okay.
the final validation is very like yeah,
No, and tomorrow we'll say more about the timeline. So it'll be almost the same as this year. If it was 7, if it was 9, November 8, 9, 10, it's like 10, 11, 12, just off by a few days. To align with Friday, Saturday.
I'm not sure what her exact plan is, but I know that
Unless you know the person is warmer than you.
yes, I did notice that. I wasn't sure.
There was a I was about to say that's probably why they're okay.
part of the other side of the knowledge border. So there is PDS, they develop documents, they finally start software languages, and they want to do the evaluation of the competition for other technologies. So we are, and they basically explore the two parts, like one for the evaluators and the other for the participants. So we managed to get the evaluators that are shown with their guys from close with they are not using the but they want to do the specialized and so we on this side of the they come down. Yeah, no, I will show you the exchange. We've been working on that on the web system. Start with the
we had it? Harold this morning? Yeah. Okay. They're in that little black box. I think the ones that are flipped upside down. See, this one's still full, so I think we'll still. The ones that we used. Is this that right? 'Cause we
And you have to remember it's not the same as like, if you have like something battery powered because you're turning that off and on, it probably uses so little power. It takes so much of the battery power. It's like that's why the kaput and like power.
Yeah, and especially it makes it so people can't walk around with them too.
I know that's my favorite. For me, I like it because you put any mic in it, it doesn't matter.
It makes so much more sense. I'm trying to think what we have to.
And maybe it's just this like part echo. Yes, when it comes back on.
that well, the red. Yeah, yeah.
You know, I'm going to reset the screen. No, it's up here. Don't worry about it.
Oh, it's on it. Do you have the
Yeah. I'm just going to reset the whole thing.
No, but like
It was like these are just
I just wanted the conversation, but and I didn't know you wanted a reason like it's a certain so it's super high, super rich and the gas pumps, like there's so much of
And then the newborn stars are extremely hot, and then they just like absolutely destroy their surroundings. And so what you're seeing is basically like, imagine like taking a high power laser beam and just burning away everything nearby, just smoking, and that's basically like the edge of that pump.
the blue part was where there's nothing.
It's like just carved out a big bubble with all that crap.
Was this actually
Correct.
we just what?
Nice. It's the thing that's here. I did CCY in crafting that.
Oh yeah, you're talking about you have 3 XCCY
Real Lincoln?
Yeah.
Okay, I was there.
Really?
Yeah.
Okay. Good call.
I was probably there before.
Where were you? Lancaster?
Lancaster and then I don't know. Maybe I was. I don't know what.
But anyway, I did it with Johnny.
I've heard something. Wait, who else was texting? Christine?
What's
Summer camp pros. Well, better now than in the middle of our talk, I guess.
Yeah. No, I reset
Oh,
it
you
myself
did it on
purpose.
purpose.
Yeah.
Okay.
Yes. Hey, John. So I have this message, but I also have the video separately.
I think the embedding would work well. That's okay. This is good to check. Maybe should I just put it in myself? Like if I pull the USB-C without.
No, so let's show this. So
I mean,
I have another tab open and the demo is in this one, and here it works.
Yeah, but I think this is the old one.
Oh, this is the old one.
Yeah,
Okay.
yeah. So.
Okay, so I should go into the slide.
So if you click, is there a way to click request or something?
Yeah, I'm sure I can get to that point.
Just immediately.
Yeah, exactly. I'll get to that point in request. And that's the other.
Thank you for trying this.
Yeah, that's right. I thought that I thought we were outside because the other one had the video. So tell me where the demo is.
Okay, so there's two demos. One's around slide below.
I'm going
up
to
here.
Run Pathfinder by going to TLDR.app on any browser.
Yeah, so for some reason it starts out low resolution and then it becomes fine. Yeah, it's
Just a network. No, John, it's fine.
Yeah, I can come back.
Okay, so this one works. Okay, and then keep going. Actually, you know what I'll do? Let me do this.
Don't bother making it full screen. Or just
Let me do this. Let me go slideshow.
Yeah.
And then let's see what happens. I'll go here.
Maybe we just click this view. I'm curious about this. Because there's a second video. I wonder. There we go. Did you click that? Yeah, just I don't know. I don't know if it's that for me.
Are you excited?
There we go. I sent in a request. Hopefully something. Yeah. Yes. Okay, so give me 1 minute. I'll sort this problem out and then we'll talk. Yeah. Okay. Cool. I know you have to do a demo. So yeah.
Sanjeev, could you try now? Oh, perfect.
This one is working.
This one is working, so then maybe go down many more slides. Well, there's one.
This one's working.
Okay, good. And then I think there may be another one on the next page.
Is that a different one?
Possibly. Yes, yes. Let's keep going. Down.
So that's this one. It's a little bit play through. It's 11 seconds.
Yeah, that one's fine.
Okay, that's the end of that.
That's that. This is the one, yeah. And then this should now work. Good. All right. Splendid. All right, thank you.
Go back to the beginning and I'll ask the projection guys wanted me to set this up and let them have a go.
Okay, let me just make sure everybody got their last.
Yeah.
Everybody got your last edit? sure. Oh, Anjali has the lead.
None of those videos have audio, do they? No. Because she wanted to test it, I said no.
Sanjeev, I'm going to plug in a clicker. Is that all right?
Sure. Actually, they have a clicker built in.
Yeah.
Yeah?
All right. Oh. Yeah. If it will advance your slide. Okay. Yeah. Generally function back. Everything all right? I mean, because I'm happy to. Oh, okay.
This should work.
On. All right. Good.
Yeah. Now that's okay. Now I'm free to answer your question. What is your technical
Good. All right.
So the way you have set it up is, let me show you the computer audio by default is, first of all, you present
Ergonomic. Well, you just press like.
Okay. Okay.
My face is very.
You set the audio output and you set the video output. Whatever you see, whatever you're hearing on the computer goes.
These broken then, aren't these?
They split it, like one goes up to the Zoom, and then one goes to the screen. I don't know what happened. So basically what happens is, I just think the main thing is computer video and audio both go out and they distribute the video to the and I don't know what they do this. We don't have to worry. To us, there's only one house. Video flows. Worst comes to worst, the slides are already here. What do you need to run this? Is the browser enough? That's fine.
Yeah.
Independent Mac.
That's there, yeah. Like it will attack you.
No, it's a native terminal.
I've already been bitten.
And you can do export and things.
These are pretty bad.
It just like hurted me into like as a
So out of here, we're sending out a USB-C and the audio.
Yes.
And then
The USB-C is
Okay. Yeah, no, you can use the HDMI to it. Perfect. That would be the best thing to do. Just test it before you leave today and get first thing in the morning. Randy, is this too little light on the speaker? Okay. Because I don't know what this does. Is this better? Okay. No, I'm just trying to make it less than full on, but still enough for the camera. Okay, let me try one more setting, and I'll go back to this if that doesn't work. Okay, this is too dark. All right.
This is nice.
All right. So this is really weird. This with the buttons are called dim, dimmer, and dimmest. So dimmest was what we had. What do you think that this one is compared to the first one, dim or dimmer?
This is dim, I thought, but it's actually dimmer.
So what is this? So this is dim, and when I switch to this, it's called dimmer. I feel lights coming on. I know. Anyway, it doesn't matter. This is the setting we're going with.
That's true. I mean, let's try. Like, no, I'm done reading it, so like, there was already
Okay, while check. That's yours? Okay, all right. So could I have volume on this and I can get started? Yeah, thank you. All right, guys, let's start settling in. Let me just put up the schedule once again to remind people what we're doing. Okay, so we are about to start the post-lunch session. Again, a couple of quick housekeeping things. Ruth, Julia, Maya did manage to get our coffee refreshed, so we'll have a coffee break. You can get some if you like that time. Another thing, all the cups and juice bottles and all that you bring to your table, please put them away before you leave or when you leave, because there's no housekeeping in this classroom and the registrar yells at us if we leave food behind. So please clean up after yourself. Next, I don't know if people feel it, but the room is a little bit warmer than one would like it. Apparently, some fan in the AC unit is broken, but they're working on it, and it might even get fixed before we leave, so it might get better. In the meantime, we have kept the doors open in the hope that there'll be better circulation. There is air, there's just not cold air, or maybe not enough. I'm not sure what it is, but it's just, we are at the threshold where we'll survive, so we should be all right. And other than that, it's almost 2 o'clock, so when the clock hits 2, we'll get started. As you can see from the schedule, we'll have John and his team talk about using LLMs in research astronomy. There'll be a break in the middle, bio break if you want to call it that. I call it ambulatory break because I feel like getting up and moving my feet. And that's about that. Any logistical questions before we get started from anyone? Okay. I just wanted to say for all our visitors who are here just for the day, especially those who are here from out of town, we don't have any dinner plans tonight as such. However, if you guys want company, I can stay back and we can pick a time like 6 p.m. and I can walk with you guys to some nearby restaurant. So if you feel like hanging out with each other and me, just meet me, let's say, here at 6 o'clock, and we'll walk over to somewhere for dinner. By the way, this is open to everybody in the workshop. If you want to talk to some of our visitors, come with us. Depending on how many people there are, we'll go to some appropriate place. If there are 30 of us, it'll be a challenge, but we'll solve it. All right, so with that and with no further ado, let me call John and his team and switch the display in the meantime. All right, all yours on this one.
Thank you. Just walk around with this. All right, well, good afternoon. Thank you so much, Sanjeev, for the introduction. And it's been a pleasure to work with our team and to interact with the other teams these past 6 to 8 weeks. And it's my pleasure to tell you about how our team tackled the evaluation of large language models in order to better the research process. So it's worth backing up a little bit as we get started here. When we talk about LLMs, large language models, they are commonly employed by a lot of us. We find them to be useful, or at least we can see the potential for them to be useful. But this may not be true for the general public. And specifically, I'm going to speak on behalf of scientists. So I'm an astronomer by training. My background is in physics and astronomy. And there's an innate level of skepticism that often comes with that. And so when we talk about evaluating LLM performance for science, there are a lot of different considerations that we want to go through. So we'll cover many of those in a bit. But to undertake this question or answering this question, I've had the pleasure of working alongside the best team I could ask for. Keep in mind, I'm going to ask actually everybody when they come up to present that they will share their names. But we've had 4 wonderful undergrads, 2 amazing graduate students, and 6 incredible senior researchers. We are perfectly balanced in that half of the names shown here are
for people who have backgrounds in astronomy, and the other half generally in computer science. And then half of us are sort of people with PhDs, and the other half do not. And so it's really been a lot of fun working, tackling this in a multidisciplinary kind of way. And I also want to give a special shout out, especially to all the admins, to all the support, to Sanjeev, Paula, and the many others who have made this endeavor possible. I also want to give a shout out to those working at Space Telescope, professional astronomers who have contributed by acting as the users for and testing our systems. So we'll get more into that in a second, but just this project would not be possible without all these faces here and many, many more names, which I cannot even list here. Okay, so the core question is this: how might large language models be useful for scientific research? And specifically, let's start with astronomy. Astronomy is really nice in that there's all these wonderful pictures. Also, by the way, thanks, Anjali, for suggesting that I add in all these fun astronomy pictures. Otherwise, the slides are a lot less interesting to look at. But astronomy is great because, well, yeah, it captures the public imagination and blah, blah, blah. But also, it's a lot of open data. It's a pretty tight-knit, small community with open access to the literature, to data sets, and things like that. And it's also very low stakes, right? You don't have personally identifiable information. It's okay if you get things wrong. At the end of the day, this is like an ideal science in order to perform test beds for evaluating AI. And so that's what we sought out to do. Specifically, when we talk about scientific research or astronomy research, we're going to be talking about question answering and retrieving, basically searching for literature which supports, or which would be useful for answering research questions. And then, of course, when we're talking about AI here, we're really just talking about large language models, specifically augmented with retrieval, so retrieval augmented generation. So that's a core question. Please keep that in mind. As I'm basically going to go through a table of contents here. So I'm just going to give actually a high-level summary of all of our results first. So that's a good takeaway in case you want to tune out for the extra two hours. I prefer you did not do that. But actually, what I'd also like you to do is, as we reach the end of each of these subsections, please just feel free to raise your hand, and I think we should do questions there. That way we can be a little more we can basically keep track of what's going on here. And I anticipate that the break will happen sort of in between sections 4 and 5 here, okay? So without further ado, I'd just like to give the high-level summary. We are in the process of writing 4 papers. One is just submitted to arXiv this morning. One already is on arXiv, and 2 more we expect to be submitting, one sort of at the end of this week, and then one probably in a few weeks' time. So we think we're going to have a nice compendium of papers for which we can reference the work that we've been doing. So please, keep an eye out for those papers. I think that they'll detail a lot of the stuff that I'm about to discuss, or our team will about to discuss. On top of that, we're going to release user interaction data with large language models. So that has been anonymized and analyzed, and that will come through with some of the papers. But there will be, a nice data set, to understand how scientists, how astronomers are using LLMs. We're going to have the gold answer data set, which is actually a set of questions and answers which were asked natively by a bunch of astronomers, in basically in a realistic dynamic setting, and then answered with actual astronomers who basically came up with the highest quality answer they could muster. There are 2 web apps that are now live. One is using sparse autoencoders to explore the latent space of paper embeddings of astronomy and actually CS literature. And then Pathfinder is another way of sort of exploring this embedding space as well, as a way to sort of better and integrating sort of all the retrieval bells and whistles that we actually ended up improving. And then finally, all of these are going to come with code repositories. We're still in the process of fixing those up and documenting them well, but they'll be attached to the papers. So just to set the stage, the design and the data collection phase is basically what we started off with. A lot of this is our pre-work. We deployed a Slack bot, which is powered by an LLM that has retrieval capabilities. It essentially is able to retrieve, a couple of documents from an arXiv source, which is relevant to a user query. Hopefully that user query is a research question, because that's what we set out to evaluate. And we compiled a bunch of useful information there. That is, again, that paper is sort of in the works. That anonymized data has been analyzed, and so interesting statistical trends, which you'll hear more about in a second. On top of that, some detailed interview studies have all been completed. So we've got 11 interviews, which is a heroic effort by some of our team members. And that paper is also sort of being written up alongside the anonymized data set. And that's going to be submitted to the CHI conference. In terms of document retrieval, we had a very simple version of RAG at the start of this workshop, of this research workshop, but since then it's evolved into this very advanced pipeline for retrieval, and that also exists in this Pathfinder web app. You're actually going to see a recorded demo of that, but that also exists live. So in fact, if you kind of go to this website, you should be able to pull that up even right now. And what that allows you to do is look around through this embedding space of archive papers for astronomy, and you can see, Stable Diffusion or whatever made a very nice looking map here of where different concepts in astronomy space actually reside. So you can see something like galaxy formation evolution up here in these mountains where there's actually a mountain of papers. You can see neutron stars and other peaks, gravitational waves, and so on. How these kind of are projected down into a 2D space. This is just like a nice way to give an intuitive feel when people see something like, a dimensionality reduced, projection of some high D space and they don't really know what the axes are. It's always nice to give them a little bit of a map feel. And so that paper is very nearing submission as well to an astronomy journal. We think that this will be useful for astronomers, but also this tool is obviously can be geared for anyone who's doing research with an open literature base. And then finally, in terms of sparse autoencoders or SAEs, there's the ability to actually steer the different types of concepts and how well they activate and in order to basically have some sort of control over the search process. So this is another web app which exists on Hugging Face, and there'll probably be another URL that will sort of that will link to that. And anyhow, so this is there's a lot of interesting emergent phenomena that come out of this, and this paper has just been submitted to arXiv this morning. So again, what I want to highlight is that there's a ton of work that we've done, which all loosely come out of this idea of trying to make the research process, interacting with literature, and making the lives of researchers a little bit easier. So we're very excited to announce all those papers, which are coming up soon. And now we're going to kind of get into the nitty-gritty details. So I'd like to invite folks from the data and evaluation sub-team to talk about how people use models. So the first person is probably going to be Sanjeev, I believe, tackling this question: how do you answer research questions in astronomy?
Thank you, John. So I'm Sanjeev Sharma. I am an associate astronomer at Space Telescope Science Institute. So what I'm going to talk about is what is the basic problem we are trying to solve here. So we're trying to answer research questions, right? So here's an example of a research question. For example, how are magnetic dynamos of M dwarfs different from the sun? If you think about a problem like this, what first you would do is you would break up the problem into sub-problems, and then you would try to look for some broad background of some of the topics involved here. For example, you would say, okay, it talks about dynamos. Let's go to Wikipedia and look dynamo theory. You learn about that and says, okay, now I'm confident about to say, what is the magnetic dynamo of sun? So maybe you go to ADS or Google Scholars. So ADS is like a bibliographic database of astronomy papers or also earth sciences and science in general. So this is what we use generally. And so after searching for them, you might find a few papers on that topic. Then you would probably read abstract and intro of those papers. And there you might get some links about new papers. And you'll run this in a loop kind of till you reach like the saturation of your knowledge. You think you have sampled enough. And then you would assimilate everything into coming up with an answer. So as you can see, this is a time-consuming process. If you know about the topic, it might take like 20 minutes. And if you don't know much about the topic, it can easily take more time. And then there are other challenges, like if the query, for example, is not the main topic of your paper, then it is rarely answered directly. For example, this is one of there's a relevant paper, and this is what was written in the conclusion. We interpret the fact that if stars have similar stellar parameters, they can have radically different magnetic topologies, and this might be an evidence that there's a switch between two dynamic dynamo states. So as you can see, it's not easy to interpret this and say, what does it mean to answer my question? Then again, there are things like simple factual questions. You might think these are very simple to answer. For example, what is the value of Hubble constant? Now, you might think it's a number, but it turns out that there are different measurements of Hubble constant depending upon if the data is coming from nearby universe or early universe. And there are different theories being floated around as why these numbers are different. So it's easily an unresolved topic. So it is same as trying to answer what is the tension between different measurements of Hubble constant. Finally, even when the papers say the same thing or talking about the same thing, it is somehow sometimes difficult to make that out. For example, this might be due to the style of writing or the fact that the phenomena or an entity is being described or referred to it differently. Sometimes it's not clear that is it an opinion speculation or is it something, a conclusion backed by evidence. And sometimes you have to also think about assumptions, like are these assumptions justified? Should I consider this paper? Finally, if you think about it, the understanding, the norms and conventions of describing something, all these things develop over time and are settled when the research field itself is well established, right? Before that, it's a bit chaotic. So I like to think of this story of blind folded people trying to probe the elephant and trying to come up with answers. So research is a little bit chaotic like this. You're looking at the same thing from different perspective and you come up with slightly different description of it. So that's what complicates the whole process. So now we are going to pass on to John again to see how we actually tackle this problem.
Right, thanks. I forgot that I failed to actually introduce myself. So again, I'm John Wu. I'm an astronomer at Space Telescope Science Institute, and I'm also a research scientist at Hopkins in the Department of Physics and Astronomy. Okay, Doak, so definitely keep in mind what Sanjeev just said. The research question, the idea of answering a research question is generally very hard, especially if you're not in stress testing mode. If you're actually trying to get the real answer to a research question, it's often not well known. But in any event, we're going to go and try. And so the first way we set out to do this is by creating a very simple retrieval augmented generation pipeline where a user might ask some sort of query. We've got all of archive AstroPH. That's the listing under which basically all astronomy papers are posted or cross-listed. And so that's of order 300,000 papers there. We grab all their abstracts, which we hope is a reasonable summary of the paper and also doesn't need to be chunked or doesn't exceed some gigantic context length or any of that sort of stuff. And we basically do some sort of similarity search in the embedding space. So we pass both the query and the abstracts into some common encoder model, and then we go ahead and concatenate that into the query you just run with our standard RAG pipeline, and we get a response. So this is essentially what we set out to do, but we put it into a Slackbot front end so that astronomers at Space Telescope Science Institute could participate in this kind of user study. So big thanks to one of the pre-work steps that we had to get out of the way was to get IRB approval because we're actually working in ways with human subject research. Very, very minimal stakes human subject research since everybody is basically just chatting with a bot in a Slack workspace where we can see everybody else's posts anyway. But what this allows us to do is basically ping a bot and say, hey, I got a question for you. How can compressed sensing be used for image deconvolution in radio astrometry or radio interferometry? And so it can go ahead and think about that for a little bit, grab some relevant documents, some of which made it into the final answer, and then synthesize an answer, right? What we gave the power for, or at least what Slack allows us to do is actually to scrape not only these questions and answers, the QA pairs, but also get a sense of, maybe people want to go and give an emoji reaction. So we sort of use that to our advantage in taking these emoji reactions and counting them as a way to determine how well did people like the answer, or at least how are people rating the answer. Thumbs up or thumbs down. Of course, this bot also, we sort of wanted to put some guardrails onto this. And so we tried our best to prompt it in a way so that it wasn't going to just, ramble into random other territory. So, there are cases in which the bot should not be able to answer the question if it's not related to astronomy research. With all that being said, we found this is actually quite a tricky task to do in practice. Okay, so once that Slack bot is done, as I said, we're actually able to track some of this data. So we have the question answer pairs, and we basically have a big database of all this, all the user interactions here. And this is one of the things that we end up we're getting ready to publish after anonymization and analysis. The reactions are the emoji reactions. So you can think of this as the vote fraction of thumbs up versus thumbs down. Any feedback, so actually in this, in this thread, users can actually leave a response, and they might say something like, hey, actually one of these citations is kind of irrelevant. I checked on that paper. I'm not sure why it grabbed that. So we can actually go ahead and follow that up as well. And then finally, the retrieval scores. These are basically the relevance scores of the retrieved documents. Top K equals, say, 5 in this case. We can also manually or automatically go through and evaluate later. Hear more about that. So this kind of sets up, the initial data set. This is the anonymized user interaction data that our team set out to analyze. Okay, so let's go and pass it on to Anjali. Yep.
Hi, everyone. So my name's Anjali Field. I'm an assistant professor in the computer science department here at Johns Hopkins. So I work mostly on natural language processing. And what I'm going to talk about is some of the work we've done to analyze this data, particularly with the goal of looking at how people use models. And first, I want to motivate a little bit why we care about this question. Why should we do this analysis? It seems like large language models are everywhere these days, but if you think about it, you probably would notice that their actual uptake has been pretty uneven. So I imagine everyone here has a friend who says, I love Claude or I love ChatGPT and I use it every day in my work every hour. And you also probably have a friend who says, well, I tried it once and it was terrible and then I never used it again. I would guess that all of you here in this room are also one of the two people on this slide. I'll do you a favor and not ask you which one you are. So what's going on here? Because we're all, for the most part, using the same models, right? So why are people having really different experiences? And we can guess what's happening. We could probably guess that people are trying to use these models for different things, and they're better at some things than other things. Probably also the first few interactions are pretty impactful. If someone had a good experience the first time, then they kept going. And if not, then they didn't. And we also might guess that there's some kind of a learning curve here, so some people were sort of better at figuring out what these models were good at. But all of this is speculation. We don't actually really know. There's very little public data on what people are actually doing with these models. And in a broader sense, we really need to know. So if we're trying to build models, and in our case, models that are going to be useful for astronomers, for people trying to do research in astronomy, we need to be able to understand how people use and evaluate these models. If we want them to be usable broadly, we want them to increase participation in astronomy research, make it more accessible to people, and not just sort of be useful to a couple of super users who managed to figure out what it was good at. So we can formalize this. As John kind of told you, we launched an initial system, and so that actually gives us a lot of data that we can use to address some of these questions. And more formally, we can sort of formalize the speculation into some specific research questions that are answerable from the data that we've collected. So first, we look at what strategies do people use to evaluate model capabilities. And so this is in presumably those first kind of couple interactions. What are they trying to get the model to do? And how are they trying to judge what it's good at? We can look at how those strategies vary across people and across time, as the bot was deployed for a couple of weeks. We can also do some deeper dives into what kind of features scientists are looking for in this model. What do they actually want to be able to use it for? And finally, because we deployed this bot in Slack, which is sort of a group setting, we had a channel where people could interact with the bot, and were able to see each other's interactions, as well as a space where people could direct message the bot, and so they could have more private interactions. We can look at this kind of, how did this group deployment setting influence some of these other factors? How might people be learning from each other? The way that we approached this problem, these research questions, is starting with the data that we collect with. So just as kind of a recap, we have about 4.5 weeks of data. And this consists of around 37 astronomers who interacted with the Slack bot at least one time. And this was resulted in a total of 378 queries to the bot over this period. So this is the data that we start with in order to look at these questions. So then the next thing is, what do we do with this data? And here we took a pretty standard qualitative research approach. This was some kind of a fun learning experience, as most of us in the workshop were not really familiar with qualitative research, and I think probably most of the people in the room are not either, so I'll kind of go super briefly into what we actually did. So we did inductive coding over these user queries. And what that means is we labeled the queries where we inferred the labels directly from the data rather than like first deciding on some labeling scheme and imposing it on the data. So how that works is 4 of us independently labeled a bunch of queries. Then we sat down and we talked about it and we discussed and we recoded and we talked about it some more until we finalized a label set. And then we used that label set to code the rest of the data. We also did semi-structured interviews. So we did follow-up interviews with people who had interacted with the bot, and we used their interactions to decide who to talk to. So we looked at 2 kind of primary groups of people. The first were people who interacted with the bot or gave a lot of feedback, and the second were people who had high rates of positive or negative interactions. Where we were looking at was the bot's answer to their query, thumbs up or thumbs down. And so the first one is selecting for people who are kind of more active in practice. What the second one selects for is people who tried the bot a couple of times and either said this is terrible or this is great and then never used it again. And we talked to a total of 11 people, did a couple rounds of invites. I was pretty impressed with us that we were able to get 11 people to talk to us over the short time frame of the workshop. So that was really nice of the astronomers to be willing to schedule with us on kind of short notice. And finally, the interviews that we did were semi-structured. So we started with an initial script that sort of probed how the person interacted with the bot, what they thought were strengths and weaknesses, what they were trying to accomplish with their queries. As part of that, we showed the people their queries and let them talk through a couple of examples. But we didn't stick 100% to the script, so the interviewers were allowed to kind of deviate a little bit and ask follow-up questions. And since we have kind of 2 main data sources here, so one is the user query data and the other one is the interviews, we have a little flag down here that we're going to use to show you as we go through the results, where the results that we're presenting are kind of coming from. Once we had collected the interview data, we also had to analyze this data somehow, right? How do we draw conclusions from semi-structured interviews? So here again, we took an inductive coding approach where effectively we go through and label everything that we think is interesting, and then we kind of try to categorize this into higher level themes, and we go back and recode the data kind of repeatedly as needed. And we'll also show you some kind of word statistics and lexical scores from both of these data sources as well. Okay, and this is just to kind of give you a little bit of a picture of what our coding scheme for the semi-structured interviews looked like. And this is still a little bit of a work in progress. We have an initial scheme, but we're continuing to revise it and to try to consolidate it. As you can see, there's quite a lot of things that we're pulling out of the interview, so we're still kind of working on making sense of them. But we will go ahead and show you some of our results that we have so far based on the work we have done. And so I'll pass off to Alina to do that. This one's a click.
Okay, hi everyone, my name is Alina. I waited for entire workshop to wear this suit and I will utilize this opportunity. So to the results. As John mentioned, we had a couple of major research questions that we wanted to answer, and please keep in mind, pay attention to the flags, where they're coming from, because kind of all of the research questions are being answered from a different set of data, not just from one flag, one question. But let's start with, well, what are the structures in which user interacted with the model, and how users evaluated the model, how they build the trust interacting with the bot? Well, the most obvious thing to look at is what kind of questions users were asking. And here what you can see on histogram, those are some type of questions that we came up with. That's how we categorize the questions that were asked. And you see the counts of how many of those appeared. You can see a bunch of different labels in here, but they can all be kind of brought down to those 4 big picture categories. So we can do something that is called knowledge seeking. We can look for a specific information. It can be more complex or more simple, but it's specific piece of information. We can also do bibliometric search that is looking for citations, for specific author, for specific paper. There is also stress testing and bot capabilities, so anything kind of trick the model, try to break the model. And the broad discussion questions that ask more of the opinion and ask model to provide some reasoning. So, and here's just example for you for 3 most common types of questions, how question of this category can look like. So for knowledge seeking, I can ask, well, what is the most massive galaxy known in the universe? For the deep knowledge, I can ask something more complex. So three examples of discovery enabled by those cosmic flows catalogs, which might require a model to select those and describe those. And bibliometric search is something like, please provide 3 questions from this year or from this topic, or provide me the counts of citations for a given paper. Another question that you can ask here, well, do those types of questions differ across the time or across the user? And this is what this plot can tell you. It's a bit hard to read, but just bear with me. So on the x-axis, you have user IDs. So if you're looking at it kind of column-wise, the bar-wise, you can see what each user was doing, what kind of questions they were asking. And on the y-axis, you see the sequential order, which how we define time, and why we didn't use the factual timestamps. Well, because our interactions were pretty clustered and it wouldn't really make sense because of this imbalance to put them as a factual timestamps. So if you're looking at it row-wise, it gives you the summary for each sequential order across all users. What were the patterns of question asked? Main insights from here, well, at the beginning of the interactions, a lot of users are asking knowledge-seeking question, which is something that you would probably guess, the simple questions. Interestingly enough, as we kind of move above, users start asking bibliometric search questions, and users start asking the deep knowledge questions. So maybe as you develop this initial trust through looking for a specific piece of information, you now can answer the bot something that will require actually reasoning and looking through the literature. Also, coming back to thumbs up and thumbs down, we will share some insights that we gathered from those ratings later in the slides. But just to get an idea, we have a diverse sample, right? In Space Telescope, we have a lot of users. And the important thing to assess was, well, are some users generally tend to thumbs up or thumbs down more? What we found, there is no difference in gender, which is a really good thing. However, where we did find the difference is based on the age. For younger users, they tend to kind of put thumbs up more than thumbs down. And for older users, they tend to downgrade model more often. And this factor of age was also correlated with how recently person graduated PhD and how they defined in space telescopes. Are they astronomers, are they researchers, or are they postdoc? But the factor of age, we think, was something that's underlying. Yes.
Do you think that's about personality? Jason, please come to this microphone.
Can you disentangle whether that's a sociological thing or is about older people being better at detecting, being more experienced and being better at detecting bad answers?
It's hard to tell. We don't want to make an assumption. We don't want to play the ageism game and say that older people have more maybe experience in astronomy specifically. We think that there might be a sociological factor and there might be a factor of LLMs are pretty recent and maybe younger generation has more experience interacting with LLMs and generally more trust and believe in those. That's why they tend to rate the model more positively. Does that answer the question? Wasn't very confident. So moving to the next question, well, okay, we saw what are general evaluations and trust building process, but what are some specific things, some specific features that the user expected? Well, you take the user interactions, you take the interviews, you combine them, you analyze them, and you came up with a long list of stuff that user potentially wanted. This is something that we wrote down as data and evaluation team, going through the interviews and going through a whole bunch of insights from all data that we collected. Some of those features will be addressed in the improved system using new RAG that we will discuss later, as well as SAE search can be applied to address some of those. Some of those maybe are good things to look at in future. And some of those were beyond of the intentions of our particular tool, but would be a nice goal for future researchers. To put this in a bit more structure, first of all, we looked at the feedback column. So what were users providing in their feedback to Q&A pairs? And as you can see, some of those comments were very short, sweet, and nice. Some of those comments were discussion between astronomers, as you can see on the left. And while they were different and not all of them were super meaningful, there are some highlights of I like this model, or I don't like this model, or this was relevant, or this was irrelevant. So those can be analyzed and kind of what were the main takeaways, what were the main things that those were communicating. Taking this approach, we looked at what were some most common words that user mentioned when they were providing feedback. We took the entire column of the feedback as a text, and we looked at what are the most frequent words, where users were talking a lot about answer, about papers, about questions, and mentioning something is interesting, recent, or mentioning think and can, which refers more to bot capabilities.
Did the users know it was an LLM, or did they?
Yes, they did know it was LLM. We tricked our users there, thinking that they're interacting with astronomers, and then they wrote papers on it. We now have infected the literature. So those were kind of the insights on directly models response. We also did the same for interviews to see if there is a different pattern when users have more time to talk and share their experience more broadly. And you can see the difference because now we're talking about time, about information, about trust, again about relevancy, but those are nice to assess since while this one is directed towards model responses, this one is more comprehensive overview of the entire process and interaction. We also decided to look at, okay, well, we have all of those words, very nice, very meaningful, but where were some underlying emotions? What were some highlights of user experience? So we utilized the package that allows you to look at the most frequent words and assign them to 8 main emotions. And this is how 8 main emotions that user shared based on the text that we analyze from interviews, as you can see on the left, and from the feedback, as you can see on the right. Pleasant thing to see is that positive, trust, and anticipation were the most common on both, which suggests that interaction generally were more engaging and positive. However, we also see some feedback on stuff like negative or fear, which would be interesting to look in more closely, and this is something that we hope to address in the paper. So here's kind of summary of what we can say about what features do scientists seek. Well, on generation, we want the confidence statement and acknowledgement on limitations. A lot of astronomers share that they had to go and check every single reference because model never says that it's not certain, it just cites. So this is something to work on. We also want to see graceful refusals, which means that not just I cannot answer, but why I cannot answer. Astronomers also wanted to see more comprehensive and complete answers with more citations, especially for deeper questions that allow more discussion and reasoning, as well as ability to follow up on the past questions in the chat, but this is something that was outside of the scope of this tool. On the retrieval, we want bibliometric search because ADS apparently can do this. We more accurate retrieval and not referring to the papers that just briefly mentioned something, but papers that were targeting the question that user asked. We want more of the consensus evaluation, something that will be addressed in the new RAG. And we want metadata incorporation, so working with citation counts, authors that will also be discussed in the retrieval slides. Also broader impact, those are mostly insights from the interview, is that we want to save time for astronomers. And this relates to the confidence of the model and if the model can provide more detailed responses, because we don't want astronomers just to play for it, we want for them to be able to use it for research. No harm or misleading information, and also personal and collective insights and group dynamic. A lot of astronomers were sharing that model directed them to the papers that they would never think about when they're writing their paper. So this provides a very nice, kind of following the last point, reducing biases in research and make science more holistic application when you can make the citations or make access to information more diverse, since model is not biased, you know, by its field of research or by which authors it knows. A bit more on the group dynamic, since this was a big part of what our astronomers were mentioning. So the group dynamic interacting in the group chat allows to reduce a learning curve. So looking at how your peers formulating their questions is a very, very nice thing that astronomers pointed out. Also the group trust building. Maybe you would spend, you know, some time asking 10 different questions to stress test the model, or you can see that those questions, you know, were already asked, so it allows to kind of speed up the trust building. It's also a community building process because a lot of astronomers shared, and as you saw about debates in the feedback section, that interaction with this bot also initiated discussion between astronomers and maybe learning more about research that your peers are doing or questions that your peers are interested in. We also compared what were the questions asked in the direct channel message and in the group channel. So you can either interact where all astronomers are or pin the model directly. There were some type of questions that were not asked via direct messages. There were much more questions asked in the channel just because it was a more common way to interact with the model. But you can see the general pattern is fairly the same. Except of bibliometric search is more common for the direct messages, which maybe you want, you know, to search for your papers and you don't want to overwhelm group chat, but you want to do it in the direct messages. So a very big picture summary. There are lots of different user experiences. Thankfully, they all are more or less positive, and they allow us to investigate further what was the insights from each user, since we have small sample but a lot of interactions. Evaluation criteria are pretty difficult to be put in the statistical benchmark. However, we can definitely see some insights in terms of counts and descriptive statistic. The interactions in the group channel allows to speed up a trust building process and build the community. And there are many specific features that we learned user want to see, and this is something that the new RAG system and retrieval team will be addressing. Passing it down to whoever goes next.
I have a few questions. Yeah, no, you can tee up the next one, but I did want you to go back to your, let's call it the bubble chart, the one with the colored bubbles rising. Yeah. Bubbles. Yeah, okay. So, you know, this is, if I understood you correctly, each vertical line is longitudinal, one user doing things.
Correct.
And then the heights will tell you how long they interacted and so on and so forth. And you seem to have organized them alphabetically by their user number. So it's funny, but that's all right. Meaning it's 1, 10, and then 2 comes later and all that. So my thought was, are there ways to reorganize this data to get more insights? So one of the questions I had, for example, was, if I had to build a model for how a user's experience will go, what they will do, are there groups of users, meaning there are a bunch of people who do blue first, followed by green, and then yellow, and other things for that? Alternately, is there a grouping of this data where if you put all the tall bars on one side and the short ones on one side, you see different patterns? Another thing which is not in this, this picture is that it doesn't tell you when the user asked, for example, the first column, pink, blue, blue. So what happened in the second blue that made them change to green? You have some information, maybe you have the thumbs up, thumbs down. So what I was thinking is, what else can you do with this data to understand user behavior? Were there other things discussed? Do you have other things that you aren't showing us because you don't have enough time? I just wanted to learn more about this because this seems interesting.
Yes, there's definitely a lot of things that we will put in the paper, and some things that we're analyzing but didn't put in here for the sake of saving time. We did the grouping, so we have a nice 3D plotting that has different groups of users, the one that joined earlier in and the one that were joining or were the most active kind of later in the 4 weeks of data collection. We didn't find any statistically significant difference between what kinds of questions those different groups of people were asking. So it seems seems like general trend across groups. And I think we separated this sequential ordering into 5 different groups. So the types of questions that were asked were pretty uniformly distributed. As for looking at, okay, what made the user switch to a different kind of question in their next interaction, this is a fascinating question to learn about, but it is something that is more qualitative analysis, and would be the same as we're doing with interviews. So we're looking actually at those feedbacks and those patterns, but this is something that is very hard to put in numbers or in statistics because we're lacking the data. So this is something that we will share as a part of just general insights, but not necessarily in the table, if it makes sense.
Right. Let me go ahead and speculate. For example, the dark blue ones, if I read your legend correctly, are specific factual knowledge-seeking type things, right?
Correct.
So maybe they appear in the beginning for users who are trying to build up trust. And if it gets some of those right, they might go into deeper knowledge or other things. Whereas if it gets them wrong, they might do something else, or they might stop interacting. So for example, user 11 asks 2 specific questions and then stops interacting. A dead giveaway would be it got them both wrong, and the user is like, I forget it, this thing doesn't know anything, and things like that. So I was thinking that you should not just look at the categories, but also all other information, because that might be predictive of what people are doing. And I agree with you that there's not a very large data set. 37 is not a big number of users, but it's far better than 5. And so I think there's something to be said and done. So I would even do something like a very simple predictive model. Predict the next question type based on the history, predict the next question type based on the history, plus any feedback on that history or a couple of variables like that, and you might be able to draw some insights. Yeah, please.
Yeah, there's one other thing I want to point out here, which is, so like Alina and I have been talking about this, but this data is sequential, it's not temporal.
Agreed.
So these kinds of questions, like something that's not getting captured here is, for example, user 15 came in and they just started asking deep knowledge questions right away. Mm-hmm. It's possible that user 15 joined the study in week 2 and already read the specific factual questions that 19 and 20 and 23 asked. And so when we look at like trying to model individual users, that's really hard because they're coming into the study at different times and they were exposed to different like previous questions, and we have no idea how far back did they scroll when they started. So I think there's a lot of like really interesting questions that we want to get at with this data, but there is a limit because of how it's structured to like what we're going to be able to do.
Okay.
Yeah.
And my only concrete suggestion is, I know this qualitative kind of thing that you look at the things and then decide categories. Sometimes just making a predictive model can like bring to surface categories that you weren't thinking about.
Yeah, thank you. I think we maybe would take like one more question and then we could move to the next section, if there's any.
Thank you. All right. This is going to be fun. So my job here is mainly to set the stage for all the incredible students, Mikhail, Alena, Charlie, and Christine, that are going to sort of do the bulk of the work that's going to be in the pretty stuff that I get to show off. So I am Karthik Iyer. I'm a Hubble Fellow at Columbia, and my day job does a lot of galaxy evolution stuff. So it was really a pleasure to sort of come here and think about these questions, because it feels very useful as someone who writes papers and then 3 months later is like, I should have cited this one paper because it's super relevant to my work. To be able to build tools that will allow not just me, but everyone else to do that well. Okay, so when we are thinking of something that's an answerer of questions or a thinker of things, we wanted to be able to essentially take a question, preferably something phrased in natural language, and return a set of papers and a synthesized answer that sort of are useful and cut down the 20 minutes that Sanjay was talking about into something more manageable, into maybe a few minutes at best, and provide metrics in terms of how confident the answer is, how uncertain, how nuanced the question itself might be, and so on, that we were seeing in the user reviews. So the 3 pillars sort of that go into this is, one, a corpus of papers that sort of contains all the knowledge that we want these tools to be able to pull from. And it's entire workshop's worth of work, I think, just trying to curate a decent corpus. And I think we did the first few steps of getting there to the point where we are like, okay, we now have enough data where we can go ahead and train our tool. But I think that in itself merits a lot of study. The second is this tool that we put together that we're calling Pathfinder, which allows us to essentially take this corpus and given any question from a user, figure out which papers are the most relevant, pull them out, and then use that to make an answer. And then finally, this is the part that I had, not thought about at all. And working with all the people here, like Anjali, I realized that, okay, no, it actually matters what the user wants, which, seemed very self-evident to me. I was like, I want it to do good, but like, what does that mean? So, so what we ended up doing is over the first part of this workshop, we mined Archive, but not just Archive, but ADS, which is the Astrophysics Data System, which is the sort of library service for astronomy papers. It started out originally for astronomy, but now they're moving into earth sciences and other things as well. And the nice thing about that is it tends to contain a lot more papers than we tend to post just on Archive, because a lot of astronomy journals originally didn't have good agreements with preprint servers where we were allowed to post the things that we wrote about. So ADS has more complete records of everything that has been published, and it really has this extensive corpus of data that actually they're doing OCR on papers in astronomy that date back to like the 1600s and 1500s. So it really is an incredible resource in that regard. So we mined our sort of corpus of papers. That's about 350,000 abstracts, and we're sticking to abstracts again because of how journals are not really set up to use full text to train our models. And we restricted to a few journals because astronomy is actually quite nice in that regard, where most of the people we know tend to publish in like a small set of journals that all have relatively the same impact factor. So it really is a bit more democratic in that regard. Sorry? Yeah. Nice. All right, so this is sort of a visualization of this corpus that John teased earlier. So what we did is, once we have this corpus, we want to see if we can organize it in a way that makes sense. And in doing that, it's also a bit of a test of whether or not any vector representation that we choose to put these papers in is reasonably capturing the sort of semantic content of the papers themselves. So all of these abstracts then got run through OpenAI's embedding 3 small model and then projected down to 2D using a UMAP. And then that was used to make this visualization. So like the nice thing here is that distinct topics tend to cluster very differently in the space. So you can go from really like small scales at the top of this plot. So at the very top of this plot, you have things like the sun or comets and our own solar system. And then as you walk down this sort of continent, you get to stars. And then from stars, you go to galaxies. And then from galaxies, you come down to dark matter and cosmology, right? Like, so there's this pretty neat organization of topics by scale almost along one axis at least. And that sort of also differentiates how a lot of astronomers tend to think of what they work on. And the nice thing is you can sort of do a lot of visualization on this just to see whether or not these mappings make sense. So the first plot here, I'm showing essentially a bunch of auto-tagged keywords where you just find clusters and then you find the most commonly occurring keywords in each cluster, which was just mined using earlier NLP methods. The second is sort of keywords that come from the astronomy community doing this group effort where there's something called the Unified Astronomy Thesaurus, which essentially collects different topics and tries to organize them into hierarchies. And anyone who thinks that there's a new keyword can open a pull request and say, I think there's this new keyword in this category that should go in there. And then people will debate it, and then it either gets added or it doesn't. And then when we write papers, we tend to use the UAT to figure out like what to tag our paper with. So the nice thing is the hierarchy of the UAT also tends to separate quite cleanly into different categories when we figure out which papers sort of lie where.
And then the third is we tend to build telescopes and observatories that have very specific purposes, right? Like, so some are specifically solar observatories, some are meant to look at stars in the Milky Way, some are meant to look at distant galaxies, and some are meant to measure dark matter or dark energy. And so those also tend to be very localized in sort of specific areas of this embedding map and show that like it's capturing information in a coherent way about what topic lies in a certain area. So this is great. Like this sort of sets up some faith in our corpus and our embeddings, and then we can use that to do all our downstream tasks. So when we started, this was our old pipeline for how the bot that John talked about that was deployed on Slack worked. And the only thing it did was it took a query, computed a similarity measure, cosine similarity, I think, for the query being embedded in the same space as all of these abstracts, and then found the top K papers and tried to answer. And we're like, okay, so that's good. That works a decent amount of the time. In fact, better than what we thought it would be. But there are all of these things that the users want. And so if we try to put that into a pipeline, things get slightly more complex, just a bit. But like this has then been heroic effort by all of the students to sort of like implement vast sections of this into an actually functional app that then has things like, oh, waiting for citations or waiting for recency or figuring out if there's consensus between the abstracts that it has pulled in response to a question. And we'll hear a lot more about that in the next few minutes. But before I sort of give the floor over to the students, I wanted to do a quick demo of the actual app. So if you go to pfdr.app, it will sort of open this landing page. And you'll see that there's a small tooltip there that you can open up and see a brief description of the app itself. There's a bunch of settings on the side that you can use to tweak how you do your search. And then there's, in the middle, just the search bar that allows you to ask questions. So the first sort of application is asking this really quick question of what are galaxies, right? Like keeping things super simple. This should be almost the sort of summarization or general knowledge kind of question. And so when you ask that, it sort of loads up, and it also tells you like, here are all the settings that this search is running with. And if you tweak something, then it will show you that it's actually updated. And it's nice because you can keep track of that whenever you're trying out different things. So, okay, it does the search, picks out a bunch of papers, and you can see that it actually has pulled out papers that say things like, what's a galaxy? Cast your vote here, because like even for things like that, there really isn't as much consensus as we thought there would be. But then it also tells you like, here's the kind of question we think it is, which is in this case a single paper factual, because there should be an easy definition that it can pull out of any paper. And the fact that if it aggregates knowledge across the papers that it has pulled out, there's actually strong agreement. And they're like, most papers tend to agree that like that's the kind of system that galaxies are. You can download all of this as a JSON file and store it and look at it later if you want to. And you can look at where the question sort of pulled from in this embedding space so that you can see what it's actually looking at. So like, is it in the right area? Is it in the right ballpark for the question that you asked it? If the top K papers are from gravitational waves or planets or something, when you asked it a question, then that would be weird. The list of papers is also like a searchable data frame. So you can actually, if you have something specific, you can go look for like dark matter in the context of these papers and see what comes up. Right. So I'm going to fast forward a bit. Let's see. And yeah, you can click on any of the papers. It opens up as a full text. The other thing you can do is ask it more complex questions like this, right? Oh, so this is sort of from this mission called Planck that was doing a lot of experiments where there's been a ton of papers that are written using Planck data that have measured different cosmological constraints. And so when you run this, it also does it pulls from the dark matter, dark energy part of the embedding space, which is good. And the thing that I have changed here, let's see, do I toggle any of the settings? Yes, I do. Okay, so here you also have like specialized prompts that are broken down into a few different use cases, and so you can actually change the prompt type. You can make it bibliometric, and it'll just give you an ADS query. Here we pick something called broad but nuanced, which is a catch-all term for where you ask it to like come up with an answer, refine that answer, and then do a second estimate. So the top K papers don't change; those still remain the same. But then the way it uses the information in that to synthesize its answer changes. So here it has an initial response, and then it does this reflection and refinement step, and then it does a final response, and now you can see that across a bunch of papers, it's collected these different numbers for what the Hubble constant is, what the matter density of the universe is, and so on. So here it had to pull that information across a bunch of papers. There's also some bonus use cases that we did not originally anticipate when we were making this tool. So one of the nice things is you can ask it things like, what's the answer to life, the universe, and everything, and it says 42, which it should. Good. That's a solid astronomy question. You can ask it about something about supermassive black hole and the relation to its host galaxy, and you can say, please reply in Hindi, and it actually generates a response that is in the language that you asked to do it. And we tested this very roughly across a bunch of languages, but it would be nice to systematically try to do this across, with users that speak different languages to see how good the responses are. And I think that's where I will stop. There's more Easter eggs if we have time at the end. So with this, I will move over to, I think, Charlie and Christine, who are going to now go into the nuts and bolts of how all of this came together and sort of explain the different parts. Thank you.
Thank you, Karthik, for introducing us. So first, we're going to talk about how exactly Pathfinder retrieves documents through semantic search and also through metadata filtering. And then in like 10 minutes or so, we're going to pass it off to people to talk about question categorization and outlier detection.
So starting from the base semantic search, one of the first things we looked at as like a baseline retrieval method is the traditional search method of TF-IDF, which stands for term frequency inverse document frequency. Basically, this is just building a big index of all the different words that occur in your corpus. And then when a user inputs a query, we basically look over that index and see which documents contain the best matches, normalize a little bit, so we want to downweight words which occur in like every document, and there's a few different ways that people have experimented with that, but that's the basic idea. And so this is like quite a good baseline for you to be able to figure out how much you're improving over what is really quite a simple system. And yeah, this is the first thing we tried, and we got like decent results. Like, it's not like this is a bad method. People have been using this for a long time before semantic search came around. But this was what we used as our main baseline.
As an improvement over the semantic search, we used what's called hypothetical document embeddings. And the basic idea here is that the original query vector is kind of similar to the documents you want to retrieve, but it also has some other semantic artifacts. For example, it's phrased as a question and not as an abstract. And so we can think about all the document embeddings kind of being in a different semantic space, or a space in embedding space, than the original query. And so what we can do to kind of align that better and get better retrieval results is we can instead use an LLM instance to generate a hypothetical document based on the query. It doesn't need to be an accurate hypothetical document. It doesn't need to be grounded in the literature. It just needs to have kind of the right words, the right structure, and the right semantic features that the abstracts do. And ideally, that should align it more with the documents we want to retrieve.
And another thing that we realized that might help is filtering by metadata. So although semantic search is great, obviously it's very hard to embed concepts such as time and named entities and all that sort of stuff within a high dimensional vector. For instance, like 2016 is very semantically close to 2015. And so if you're actually doing search, like even places like Perplexity and EXA still need to use metadata stuff to supplement their semantic search. So we did the same thing. So we added a few different metadata filters in. So we have a time one. Basically, we came up with a system that uses regex to figure out if the user's query contains some sort of time element, and we put a little bit of effort into figuring out how to construct that. That was quite a bit of manual work. But if it does contain a time element, then we pass it off to a very small LLM to figure out a appropriate metadata filter for the query. So a user might be like papers in the last 10 years for Hubble, and then we'd set an appropriate metadata filter with the LLM. But using the regex means that we can just quickly check every query that comes in without having to use an LLM to do that specific part every time. Citations, we use a sort of like sigmoid weighted function to prioritize like highly cited papers, but obviously we don't want that to grow exponentially because there's a very, very skewed distribution of citations in astronomy in particular. And so we kind of weight papers quite a bit better if they have more than a few citations, but then we'd sort of tail that off as the number of citations grows because it's probably diminishing returns there. And then finally, we have sort of a few different like chains of reasoning within the retrieval system that manage things like keywords, and we even played around with this, just doing that with traditional search methods like filtering documents again based on a TF-IDF index before we do the whole big semantic search, which kind of saves a little bit of time when you're doing that vector matrix multiplication.
So overall, Pathfinder uses a two-stage retrieval system with re-ranking, and that allows us kind of the most bang for our buck and computation time. So starting from your full corpus of 270,000 documents, we first do the hypothetical document embedding, the semantic search using just dot product, and then filtering, and that gives us our top K, which we retrieve depending on the final amount we want, maybe around 250 or so, and then we re-rank using a cross-encoder. We're using one of Cohere's re-ranker models, and that helps basically give a relevance score that is more fine-tuned to the actual query and what kinds of documents we want to retrieve than the original semantic search. And then that gives us our final retrieval results, which then go into the context for retrieval augmented generation and are also returned directly to the user if they want to read the papers themselves.
So we had a few synthetic benchmarks to measure how well our improvements were doing, and these were used with things like TF-IDF as well. So the first one we used was called our single paper evaluations. These were synthetic, so the way we constructed these was we would sample a bunch of random papers from arXiv and get sort of Claude 3.5 Sonnet to come up with questions that would come directly from that paper, like with information that is specific enough that you could just get that paper to answer it. And so we constructed quite a few hundred of these. And so this gives us a pretty good proxy for like how well our retrieval system is doing at like single paper retrieval. Like if a user asks a question specific enough that it could be answered by a single paper, how well are we at getting that paper out? And there's a few different metrics we use to measure that.
The other synthetic benchmark we used to kind of check our development was the multi-paper evaluations, and it's based on the same idea as the single paper. We're finding sentences in review papers, which are kind of people that have already done all the literature search and retrieval for us and probably spent months and months doing it. And we find we call citation clusters. So for example, someone writing a review paper will give a statement that probably took a lot of research to formulate, and they'll substantiate it with 5 or more ish citations that are all papers relevant to that help kind of back up that claim. And so that's a very natural way to test if you give your retrieval system the same question or a question that the sentence answers. It's a natural way to test, are the right papers being retrieved as checked against what a professional astronomer writing a review paper would say. And so we have about 200 of these review papers. We scrape sentences with citation clusters, and then we use, again, Claude to generate a synthetic query and use the citations that are in the citation cluster as part of the gold standard. And then we retrieve the top K and check, how many of the gold standard papers that a review paper cited actually end up being retrieved when you're given the question that is answered by the sentence.
So quickly, just some results. So as you can see in the yellow, the bag of words, which is TF-IDF, did reasonably well on our metrics for single doc, but obviously like the stuff we've just talked about was a significant improvement in both the metrics we looked at for single doc. So success rate is simply just how, did we get the correct document for the single paper benchmark? And the reciprocal rank is at what position in the return results was that, 1 over that rank. So if it was on average at position 2, we'd have a reciprocal rank of 0.5 on average. So we do really quite well, and we basically considered our system to have solved single paper benchmark based on the amount of noise in the system and all that sort of stuff, because it's sort of getting an average reciprocal rank of up around 0.75, 0.8, which basically means it's returning the correct document first every time.
And then looking at the multi-paper evals, these are obviously a lot more challenging because there's so many documents that could be returned. And I want to point out that because there are so many documents that could be returned to answer any one question in a review paper, even people writing review papers have challenges. We really focused on metrics that don't penalize the precision at all and only on recall. So our goal was mainly how many of the papers that are really good at answering this question will end up retrieved in our system. And so looking at the recall at 50 and also the NDCG, you can see again that we see the same pattern of bag of words is like pretty okay, but you can do a lot better with semantic search and even better with hide and with re-ranking.
Yeah, we might pass this over again.
So the question I had was the thing you were doing with, I guess, hide. I'm not an information retrieval person, but some of my friends are, and they would say you're doing query expansion, right? So you could also do query expansion with something basic like TF-IDF. Did anyone talk about it? Any thoughts on how you might do it?
Yeah, so I think people have actually written a paper on this, and I think most of the benefit from hide doesn't come from the fact that you're expanding it out with similar keywords and all that sort of stuff. The benefit of hide comes from the fact that within these semantic embeddings, that there is representation which represents meta information about what type of text it is. So is this a archive paper or is this a casual query to a chatbot? And so the idea, most of the benefit from hide from what people have shown is not that sort of expansion thing, but more so aligning the query to the papers. So the stuff you retrieve doesn't have artifacts like this paper abstract is more like a casual chatbot query. It's like you remove all those artifacts, so the things you're searching for are actually related to the information you're retrieving.
People have written abstracts that are actually just like questions or like we've seen like abstracts in our database that are basically just a question or two, and we wouldn't want those to be like the primary retrieve results or like be, you know, polluting our top results unless they're actually topically relevant.
So you didn't really train the component. I didn't get it. So who trained the model that takes your query and converts it into a hypothetical document?
We just use Anthropic.
Okay, got it.
We just use Claude Sonnet, but I think the theory is that it doesn't matter how much of the domain knowledge it has or how accurate it is. It just matters more that you redirect it into the right kind of semantic space where all the documents are.
Yeah, okay, all right. And then the other question I had was, when you looked at your results for these multi-document cases, right? I think I understood your process of creating, let's call it ground truth, as you know, the citations of a cluster of papers together in support of something. Do you know how good that benchmark is? Meaning, did someone from astronomy look at other papers and evaluate and say, yeah, this is also considered correct, you should take it, or no, this is not right, you should leave it out? I'm just thinking because actually I'm more worried about the first kind, namely, even when somebody does a survey paper, they might cite for some aspect of the claim, they might cite the most authoritative paper on that. There might be two others that preceded them. Preceded it, and they're equally relevant. They're just not the first thing to cite. Yeah. So you might be underestimating your recall.
Yeah,
your precision. I'm sorry. Yeah.
We did have like astronomers look at a few examples of the things we constructed,
okay.
And they were like fairly confident. But saying that, we don't need to remove all the noise from these benchmarks. We just need the true results on our synthetic benchmarks to be correlated with the real results if we were to have a perfect gold standard data set, because we just need to know which one's better and by how much relatively.
And in like 20 minutes or so, you'll hear about the gold standard benchmark that was constructed and which we eventually also evaluated the end retrieval system on. So these were mostly just for development.
Okay, all right. I think we have one more question.
You mentioned TF-IDF. So over the years, a lot of heuristics have been developed in the IR community. Did you get a chance to, for example, BM25 or, you know, many? So any rough idea as to how sensitive things are?
Yeah, so this was actually not a final evaluation we did with BM25, but I ran BM25 with the like sort of initial versions of our benchmarks, and it was a modest improvement over TF-IDF. And so we just stuck with TF-IDF because like it was easy to track. Yeah. Cool. We might pass back to Alina. Is it?
So kind of to talk more about development part. So as you saw at the beginning, our data and evaluation team had their own categorization that were more conceptual and for the purposes of analysis of, well, how user interact with model and what they expect. Retrieval team had their own classifications of the questions that were targeting more, okay, what parts of the retrieval pipeline do you need to answer those questions successfully? Because if I'm asking you, well, what's the distance to the moon? You probably don't need a lot of citations. It probably didn't change in the last year by so dramatic that you need to make it time sensitive. And to optimize for the retrieval and not to run simple questions through the stuff that they don't need to be ran through, we developed a series of categories, which kind of here are structured from the simplest one in terms of retrieval to the most complicated one. Unclassified questions were something that we cannot determine what it should be, so up to compositional it gets in order. So single paper and multi-paper is once again looking for a piece of information, such as relying on top K. Consensus evaluation is something where the papers do not agree and you need to acknowledge it, or you need to make a note that you need to, make sure that in top K you have different opinion on it. What ifs and counterfactual are questions that cannot be addressed within the scope of existing literature, therefore might require more reasoning and inference from the model and as well in generation part. And what ifs and compositional questions were the questions that were asking about different instances. So, and the difference between those instances, I cannot come up with a good question in astronomy because I'm not an astronomer. But if you're asking about, oh, give me a galaxy and give me something about, I don't know, how atmosphere of the Earth is working, like those are very different questions. So the model needs to recognize this and separate it into actually two different queries and run two different queries through the pipeline and then combine them in the one response. So we classified those questions, and on the data that we collected, we decided to see, well, in terms of relevance scores, how well does the model perform on each category of those questions. And to make it easier, so here's the categories that we discussed, and here are some flags that are more related to the features that Charlie talked about. This is the average relevance scores from the naive RAG model. Once again, this was used for the development. That's why we're relying on the old collected data, not using the new retrieval model. What are some interesting takeaways here? When you're looking at the mean of the average relevance scores for each of the category, they're relatively the same. They're not statistically significant differently. But when you're looking at the distributions of the relevance score for each given category, you will see a lot of difference. You will see that some have peaks, very distinctive density peaks. At the high relevance, some of them are more generally distributed, and some of them are even bimodal. Why is it important? Well, to also acknowledge that different kinds of questions will have more variation within them, and some of those questions might need more tuning in the future to answer them successfully and being sustainable in those successful answers. Important note in here, those are, once again, developmental tools. The classification right now is not implemented within RAG. It's more of the, when you see the output of the Pathfinder, oh, my question was of this type, is for you to acknowledge how you expect the model to be answering. And if you asked, for example, compositional question, maybe it's worse for you to, go ahead and separate your question into two different queries. Also, a big takeaway kind of for future research and for development of future benchmarks and evaluations, we test if the relevance score is actually correlated with the amount of thumbs up and thumbs down. And they are in the ways that we're expected. So more relevant papers receive more thumbs up when they're cited in the model response, and less relevant papers, they receive less thumbs down. And both of those correlations are statistically significant. So basically what it tells you is that relevance score is a good predictor of the user satisfaction. So for the future research that do not have access to participants and cannot run the experiment, they can rely on the relevance score as something that will predict user satisfaction. And I will be passing it to Mikhail.
Hi, everyone. I'm Mikhail. I am a grad student in the physics and astronomy department. I work with John. I'm going to be talking about my work on outlier detection and consensus evaluation. This is the most downstream component of our retrieval pipeline. And the kind of broad idea is that we've gotten to a point where we can obtain a top K documents. And it's pretty good. It's like about 90% of the way there, but there can occasionally be one or more documents that topically are dissimilar to the other documents or dissimilar to the query. So we want to make sure that that doesn't happen. So this can be broken down into two tasks. One is pitting the top K against each other and seeing if anything sticks out like a sore thumb. The other is, once we've done that, evaluating if we look at the top K as a whole and evaluate that against the user query, if there is agreement, disagreement, or somewhere in between. But I'll first start with a little fun activity. I tested out a question the other day. In the literature, there isn't really a lot of overlap between gravitational waves and exoplanets, simply because exoplanets are too small. But one of these papers is very much an outlier. If you guys want to take a second, guess which one it could possibly be. And I will now explain how we find outliers in the top K. So we know that there will occasionally be outliers that have some sort of topical dissimilarity. In practice, we see this happen the most often when you ask like an interdisciplinary question, like something about gravitational waves and exoplanets, where the two topics have very little to do with each other. Papers will come up that have to do with one topic and not the other topic. So if we step back, we know that every paper in the corpus lives in this really high dimensional embedding space, which I kind of visualize using 3D over there. In Pathfinder, we do compress it to 2 dimensions using a UMAP. And we can visualize like topical clusters of papers and using that find outlier papers. So it's a 2-step process. Step 1 is finding what's called the outlier cutoff distance. I'm gonna kind of talk Pythonically here. You have this empty initially list. And if you're looking at a top K, say like K equals 10, you go through each paper in the corpus or some statistically significant sample of the corpus. And for each paper, you look at the 10 closest papers in the corpus. And you add all of those distances to this really big list. So if you have like 1,000 papers, this list of 10,000 distances. And then you find the 95th percentile and subtract a correction term that we experimentally determined. And that gets you this hard set distance called the outlier cutoff distance for some K. So once you have that distance, what you do is you look at your top K, and for every single paper in your top K, you compute the centroid of the other papers. You measure the distance between your subject paper and the centroid. And if that distance is bigger than the cutoff distance that we just determined, then we can flag it as an outlier. And conceptually speaking, the kind of logic behind this is if one of the papers is basically disobeying the natural clustering of topically similar papers in the corpus, it should not be part of that cluster and is too dissimilar. Here's an example of this being used in Pathfinder, kind of going to that earlier example question that I asked. The non-outliers, let me see if this is working. Okay. The non-outliers all live down here in this area that has to do with gravitational waves. And one outlier comes up that just lives in like the exoplanet area. near the top, and that comes up as an outlier in our system. And the answer to the earlier question, the culprit was the one, funny enough, that got caught speeding. And it's also a culprit because it is very much an exoplanet paper, has nothing to do with gravitational waves. I actually went into the abstract of this paper and tried to see why it was coming up in the top K in the first place, and it was because it said the word gravitational or gravitationally 3 times, but had nothing to do with gravitational waves. So that's kind of an example of something that's not being caught by the retrieval system until it goes through outlier detection. So part 2 of this is consensus evaluation. Once we kind of know what the top K is doing and what it's saying, how do we evaluate that against the user query? So if we have a query, like a yes or no query that's trying to probe the literature or just ask something in general about astrophysics, such as, are blue local galaxies generally older than red local galaxies? Quick side note, by the way, that's a false statement in the local universe. Blue stars they're young and they're hot and they burn through all of their fuel very, very quickly. So that should be a false statement. So if we probe the literature and see what the top K abstracts are saying, it should come up as a disagreement with this quote-unquote equivalent statement where you're rephrasing the query as a statement that doesn't necessarily have to be true. So the prompt is very long and arduous. Thank you, Kira, for the help on this. But basically, it's 4 parts. Rephrase the question as a statement. Evaluate the consensus between the question and the abstracts. Explain it for the user, and then provide an LLM-generated relevance score to see how relevant the papers are to the user query. And it works pretty well. So for the example question that I was just talking about, it comes up with strong disagreement. Something that it actually does that I didn't even tell it to do is it talks about some of the specific abstracts and why they specifically disagree with the sentiment of the query. And then another example is, do supermassive black holes co-evolve with their host galaxies? And that comes up with strong agreement, which also seems to be right. And that is it from me. I think I am passing it back to Charlie and Christine. Unless, are we taking a, we're taking a break. Okay, break time. Are there any questions? Yes.
My question has to do with these outliers.
Yes.
On one hand, indeed, these systems will produce outliers. You need to find a way to get rid of them. But I also am wondering when an outlier is an outlier in terms of statistical distance, but actually is a different point of view that needs to be shown. This goes back to some of the things that Anjali and Alina were saying, that if you want literature search to be more, let's just call it fair, these minority views need to be reflected in your search. So how do you,
Well, yeah, so thankfully, I think the outlier detection, the way it's set up right now, like at least in practice, what I've seen from running it, really targets like the keywords more than anything else. So if there's like a minority point of view that comes through, it'll still like, I'll go back to this example with.
Yeah, I remember the example about the speeding exoplanet. Yeah.
Oh no, I mean like this cluster, for example. Like, so say there's some paper that's like a minority opinion, but it still has to do with gravitational waves. It would still show up somewhere here and would not be flagged as an outlier.
Yeah, what it would need, if I understood your technique correctly, is that it would need a community of other papers with the same minority opinion, so that its distance, basically all of them or many of them would have to show up in your top K, so that when you leave that one paper out, the rest of them are, in other words, if there were 2 or 3 with the minority opinion, when you leave one of them out, the other 2 are in there. So the centroid of what remains isn't that far away.
Yeah,
but if this is the only one, then it gets left out. So, okay.
Yeah, I agree. It's a good point. I think if they're like talking about the same things but have different opinions on the same thing, they should hopefully come up in the same area. I think the one place where that is more of a concern is the consensus evaluation, because if minority opinions are coming through, and the system is basically looking at the top K as a collective and saying, oh, the top K all say this one thing. That is an area where we need to develop that and think about if minority opinions are getting phased out.
Okay.
And I will say, we're kind of dealing with that because our scale is going between like strong agreement, and I've actually seen instances like, for example, if you ask what's the Hubble constant, it comes up with moderate agreement, and in this explanation is crucial, by the way. In the explanation, it basically says we said moderate agreement because they're two very different schools of thought on what the Hubble constant is.
Yeah.
But that's a very good concern that we're going to have to think about a lot more.
Okay, there's one more question.
So like a quick addendum to your excellent explanation is that we also to some extent rely on the astronomical literature being sufficiently dense, right? Like in terms of, so basically if you're doing the same system with only 100 papers, right, then you might conceivably ask a lot of questions where there might be a second point of view, like a bimodal sampling of your embedding space with sparse enough number statistics where that gets classified as an outlier. But we tested this with solutions that actually needed to pull from two different paths and found that because there's enough papers, yeah, exactly. So I think it's once you're past the threshold, then you're fine. Yeah.
A great question, by the way.
So I have two questions about this slide, about the consensus validation process. And the first is actually very similar to Sanjeev's question, which is really, what do you do not about outlier questions, but about points where there's legitimate disagreement in the field or the question is unsettled, and presumably those are questions users will be particularly interested in asking. And so
absolutely.
Handling those kinds of debates fairly seems helpful. And then the other is maybe a little more technical, but strikes me that accuracy of the summary is really paramount in a thing like this, and a tool like this. Like the last thing you want to do is produce a summary that is in some way incorrect. And so I wonder if you've got a good way of evaluating and just making sure that the actual summaries are.
And when you talk about the summary, you're talking about the like detailed explanation in this? Yeah. Okay, it's a really good question. So to that first point, I think like we have a bare bones way of like if there are disagreements between astronomers, and you're 100% right that that's exactly what they're going to be using this tool for. We have a way of like at least probing that and saying something like, oh, there's moderate agreement because one camp is saying this, another camp is saying this, but they're not really resolving with each other. And I have seen a few examples of like just no clear consensus because the particular question is so nuanced that it's like sparse and everyone's saying something different. But that does take a lot of nuance, and we're definitely going to have to refine that even more. And then the second question about the summary, yeah. So we actually had an older version of this that, to your point, the summary would not like say the correct thing sometimes, and it was really frustrating, and it kind of threw everything askew. It's not as much of a problem now, but it's also something that we're going to need to like stress test the bot, see where it breaks, and then figure out how to fix that. And thank you for the question.
Probably you mentioned this before, but how many opinions do you need for consensus? Or is it like bias or?
Yeah, so it's looking for consensus within the top K. So if you have like 10 retrieved documents, basically it looks at those 10 documents and for example, if like the majority of them, like maybe 6 or 7 are saying one thing and then like 3 or 4 are saying the other, it will lean towards agreement, but it will say like moderate and kind of elaborate that there is some level of disagreement between the two. I don't really have a hard number for that, but from what I've seen, it's mainly like majority rules at the moment, and that's the thing is an earlier version of this that we implemented actually probed each individual paper, said, does this paper agree with the query? Does this paper agree with the query? Which was much better for letting minority opinions get heard. But the problem ended up being latency, that like computing for like, if your top K was like 30, you would have to make 30 LLM calls every time you did consensus evaluation. So that's another problem that we have to navigate and figure out. So one idea that I had for like after the workshop, I had to use the collective top K for the time being just because it was faster, but doing something where you still probe each individual paper, but you'd use something that's a lot lighter than an LLM for very like clear-cut cases, and you only bring the LLM in when you need it, and there's a lot of nuance. So that would help with something like that.
So just pushing a little bit further.
Of course,
so
yeah.
do you think that perhaps the results might be like a little bit biased towards the group of people that kind of gave an opinion about the different papers?
I think like just because of like the latency thing, unfortunately, yes, at the moment, but this is something that once we kind of refine what we're doing and like invoke things like what I just mentioned with not using LLMs all the time, that should be able to get rid of a lot of the bias. So I would say it's like slightly biased right now, but that's something that's a very fixable problem.
Thank you.
Thank you.
So I'm not sure if this is the right point at which to ask the question, so if it's better for the end to say so. When I think about the kinds of questions that I find hardest to answer by searching the literature, they're the ones where I don't know what the search terms are. And I have an idea typically, and I want to know if anybody's done it before. Maybe this doesn't show up as much in astronomy as it does in a field like machine learning or computer science, which is a more engineering field where you're trying to come up with something new to do. But if the idea is put together X and Y, I can just search for papers that just mention X and Y. But like suppose you invented hide or reverse hide, but you didn't know that it was called that.
Right.
So you're going to be asking the question with sort of common terms that show up,
like reinventing the wheel,
like relevance and rephrase and things like that might show up in lots and lots of papers, and you want to be able to match against a more abstract concept.
Mm-hmm. Yeah, I think I saw. Alina, correct me if I'm wrong. Do you talk about this? I saw you light up, and while Jason was asking that question. Maybe. Oh yeah, I saw you guys light up when I was like, "What are they talking about?" Yeah, SAE would be. Charlie and Christine are going to talk about this after the break. That would be really good for that. But I also find that like even Pathfinder, I've asked questions to it before, where I'm just like, "Tell me about X, Y, Z," because even as an astronomy grad student, I'm still like learning the ropes a lot, and there are things that I don't know much about. And I also, in my experience, like hit that roadblock where I'm like, I know some like keywords like very vaguely, but I don't exactly, sorry, my mic's going up. I don't exactly know how to answer this question, but even if I just say something to the effect of like, tell me about blank, and then it gives me a bot answer, and then it gives me, you saw in the Pathfinder demo earlier as well, it gives me like papers, and generally speaking, if I just look in those papers, it's kind of like any sort of research where you are just doing a literature search, but the literature search is streamlined, I guess. But
yeah, I think there's probably a difference here between ideas that have names,
yes,
and ideas that don't. So with an idea that had a name, you could.
Yeah. I was thinking that we should revisit the question since they're going to say more things in another part of the talk. So let's do that. Very good question. So yeah, so the question hasn't been answered yet,
yes,
and
sorry,
as a group you'll come back. No, that's good. That's good. So okay, so we'll come back to this question at the end of the presentations, right? Okay. So John, is this when you wanted a break?
Yeah.
Okay. Perfect. So let's do a 10-minute break. It's 3:35. Let's restart at 3:45.
Cookie time.
Good question, Jason.
Just, I'll say empirically, we tested these and it does okay. You can walk around the words all you want.
well, like for instance, you don't explicitly say dark matter, you say why are galaxy rotation curves fast? It will come up with modified dark matter or find other theories. Exactly, yeah. What I was going to say is, where you synthesize queries. Okay.
Pete to bring some tomorrow. He said he's got some in his bag. Yeah.
All right, boom. So it should be good.
Hello, guys. Let's get back and get started again. Hello, hello. Let's get back, everyone. All right. First, completely irrelevant thing. I've lost my glasses. So if you guys find a pair of glasses, like, no, that those are my spares.
that number is off by 0.5. So if you find a pair of glasses lying around, they're mine. At least they could be mine. All right. Thin black frames, very thin black frames. I don't think they're circular. They're like, an odd octagon-like thing. Okay, anyway, it doesn't matter. Rounded corners. So guys, let's get back. Who's up next, John? Okay. So SAE team, just line up. We'll queue up the slides, and in another 30 seconds, we'll get going. Okay, I think this is your slideshow. I think I'll leave you here. How's that? Okay, all right. Let's see, this mic should be turned on. You take this one, check that it's working. And this is your clicker. All right, so let's get started again. Christine, Charlie, all yours.
Thank you. So we've been talking a lot about semantic search with dense embeddings, right? That's the kind of basic unit of all the search we've been doing with Pathfinder and our retrieval system. But there are also a lot of challenges using dense embeddings for semantic search. One of them is the lack of interpretability, right? So embeddings come out of these sentence transformers. They're kind of a black box. You don't really understand the search results, unlike keyword search, where if you put in a keyword, you can be pretty sure that that's going to influence your search results. We don't really know what influences semantic search results. And in fact, because of that lack of interpretability, there might be unknown biases in the semantic search that we're not even aware of because everything's just kind of black box embedding. There's also limited user control, so it's kind of hard to engineer your query to get the exact things you want, again, because we don't really understand how that affects the embedding on the other side. There's the curse of dense retrieval, so performance degrades faster than for sparse methods as the index size increases. And then there's superposition, which is when multiple concepts are encoded in the same dimension, so like our 1536 dimensional dense embedding, for example, and that really complicates being able to manipulate certain semantic features, again, unless you do a lot of prompt or query engineering. And so to address all that, we're going to be talking about our work with sparse autoencoders.
Yep, so we'll try and keep the maths to a minimum because sparse autoencoders are actually quite simple things. So basically a sparse autoencoder consists of an encoder and a decoder. The encoder is a linear layer followed by a nonlinearity, and the decoder is simply a linear projection back to the space you came from. So at its core, the idea is that the green sign, so the encoder, takes in the embedding vector and figures out which features or like which dimensions in a much higher sparse dimensional basis, sparse basis are active for that particular embedding. So you might imagine there's a dimension in that higher dimensional space that corresponds to black holes for astronomy or for CNNs in computer science. And it figures out how much that direction is active. And then basically those are the coefficients. And then we simply take those coefficients and add up all our decoder feature vectors. And then they learn to reconstruct the embedding back in the original embedding space. And so if we train this with a sparsity penalty in the middle in that blue bit there, we can show that if you set this up properly, that we learn the proper sparse basis that these things came from. So the idea here is that we're learning the dimensions in the sparse basis to be features. So this is quite hard to define, but you might like to think of this as something which is interpretable by us, and it's an abstraction created by the model to represent some particular part of the input. And so another keyword is monosemantic. So neural networks obviously have these very distributed representations because they have many, many more features than neurons to represent them. So a lot of features are crammed into multiple neurons, and neurons represent multiple features and vice versa. And so we want to project this to a much higher dimensional space where we can disentangle everything and just have like one dimension corresponding to one feature. And so yeah, neurons are not monosemantic, as I just said, but SAE features, if we can set this up properly, are. And so this gives us a lot of information if we learn this properly. So we can not only reconstruct the embedding vectors, but we have these individual dimensions in the hidden representation which correspond to supposedly interpretable things. So the idea is after we've trained our sparse autoencoder on the abstract embeddings of scientific papers, so we did this for astronomy and computer science, so for almost 500,000 papers, we pass it off to a large language model to figure out what these features actually mean, because there's thousands and thousands and thousands of them. You can read the text if you want, but the basic idea is you have an interpreter model, so that's the one on the left in the green, and we take all the abstracts, and for each individual dimension in our sparse basis, we figure out which abstracts excite that feature the most when we pass the embeddings through our trained sparse autoencoder. And we take those and we also take some ones where the feature didn't activate at all, so abstracts where it didn't. And we say to Claude or GPT, what do you think this feature is? What do all the abstracts that activate the feature have in common that the ones that don't activate it don't? And we found that GPT does a pretty good job of figuring out or interpreting the feature. But we also need some way to like measure our confidence in how interpretable that feature actually is, because a lot of the way that models construct these things is actually quite non-obvious and yeah, difficult to interpret. And so what we do is we pass that label. So that label might be, again, black holes. It's a black hole feature, or a sign language feature in LLMs, which we also found in one of our essays. And we pass it to a different LLM, and we randomly sample some abstracts where it activated and where it didn't. And we say, do you think this feature would activate on this abstract? Then we basically measure with F1 score and Pearson correlation how well it is able to predict whether a feature activates or not. So that gives us a label for each feature, but also a measure of confidence in how interpretable it actually is. So this is our overall pipeline here. So we feed in our hundreds of thousands of embeddings into our SAE, which constructs the latents. So we, again, impose that sparsity penalty. So we only allow k latents to be active at any one time. And then this is the coefficients for our decoder vector. So typically we set k to about 64. So basically we're turning this into a task where for any given embedding, we need to reconstruct that embedding with a linear combination of 64 of the decoder's feature vectors. And so for any given abstract, those have to be the 64 most important concepts present in that abstract. And in terms of the higher dimensional space, we typically set that to about 8 times the embedding space, although with large language models, when people are training SAEs over actual activations, that tends to be even higher. And yeah, once we've got the trained decoder, we do what we just said. So we take each decoder column, which corresponds to an index or a feature, and we pass it to our interpreter model, and then we pass it to our predictor model, and we have a label and a level of confidence in what that is. So here are some results. So I think it's important to note that like we are the first to train SAEs for embeddings, for neural embeddings. People are really excited about this stuff for language model activations to try and interpret them and figure out what features are in there. In fact, Google DeepMind released SAEs trained for all layers of their Gemma models. And so SAEs are really like, everyone's really excited about them. And so we think it's quite cool that we managed to be the first to do this for embeddings. And I think it opens up a lot of ideas about how to use these for neural embedding models. And yeah, so what we see here is basically our final normalized mean squared error with the reconstructions. And we found that even more so than SAEs trained over language model activations, these embedding SAEs have very, very predictable scaling laws. And so you can basically pick your K and pick your number of dimensions for your higher dimensional basis and predict what your final mean squared error is going to be. There's a little bit of difference between computer science and astronomy. We're kind of chalking that down to how many computer science papers we used compared to astronomy papers. And so once we have our features, as we said, we give them a label and evaluate how interpretable they are. So on the top right there is our distribution of Pearson correlations between the predicted activation and the true activation. And so we find very high median Pearson correlation. So in astronomy, it's actually pretty close to 1, which is pretty cool because Anthropic has done a similar thing for SAEs for language models, and that median correlation tends to be about 0.4 to 0.5. So embedding model SAEs appear to be very, very interpretable. And we find that, perhaps an intuitive finding, that features fire more frequently in the large model SAEs than in the small ones. And it's quite a nice distribution of how often those features fire. Here's a couple of examples of features we've found. So obviously some of these features are going to correspond to the keywords in the abstracts, but we don't want just that because you can do keyword search with keywords. So I think a good feature to highlight is like the periodicity in astronomical data. Those abstracts don't really contain those keywords. And so the fact that the SAE has picked that up as a feature is quite cool. Similarly, arithmetic operations and transformers. If you look at the top 10, so this is the top 3 papers here, but if you look at the top 10, they actually really are quite varied. And not that many of them contain the words arithmetic operation. So it's quite cool that that was an abstract feature picked up by the SAE. Yeah, so part of this whole process was training like a bunch of different SAEs where we varied two things, which is the number of active latents at any one time, which is K, and the dimension that you're projecting up into, which is N. And we had a look at like how features tend to correspond to each other when we train different SAEs. So theoretically, the SAEs should in general learn the same features in the limit, but with different sizes, SAEs have to make different trade-offs about which features they're learning in order to minimize the reconstruction error. So what we see here is we compute the cosine similarity between each feature in a larger model and each feature in the smaller model, and look at which feature is the closest between those two models. And this is the distribution you're seeing here. So it's basically the nearest neighbor between a feature in one model and all the features in another model. And as we change K to be larger and N to be larger, we see that this distribution shifts significantly to the left. So when K and N are small, basically we're learning these like very general features you might interpret it as, which have very high cosine similarity to their nearest neighbor. But as we increase the number of possibilities and the spaces we're working in, the SAEs learn significantly different features, and this sort of leads into the idea of feature splitting and feature families, which Christine is going to talk about.
Yeah, so why does it matter if features are aligned or how features split? And also, why does it matter how features cluster or can be grouped together? Well, we want to kind of tie this back into our group's big picture definition of search. And so our thesis is kind of that these aligned features, or the features that appear in every single model, are the features we should have the highest confidence in. Those are features that, you know, we think have real semantic meaning, are really fundamental to how the model is doing these search calculations in the embeddings. And so if we manipulate those, we'd hopefully be able to get really semantically meaningful downstream effects. The same goes for clustering, right? If you have one feature that means one thing, that's great, but you have 9,000 features. So finding meaningful groups of features can help you do search and manipulate your search results, not just along one meaningful dimension, but along a whole group of meaningful dimensions, or even along a subspace in this kind of higher dimensional vector space. And so the first question we had was, how aligned are features between models? And as Charlie alluded to, there's a lot of kind of recurrence of the same features between models. So we'll find features that exist with, 90% plus cosine similarity. Here I've just plotted the number of triplets. So we look at models at 3 different sizes, and we try to find triplets where all of them have 90% or more. Or I think the x-axis is the cosine similarity threshold between models. And so obviously, as you kind of move up your threshold for tripletness, you get less of them. But at, for example, 95% cosine similarity, the K equals 16 model, which is our kind of model that's learning the most general features, has over 1,000 features that appear in every single model. And so that's really exciting because it points to these features being something really semantically meaningful and being kind of a direction in embedding space that will always be recovered and always mean something no matter how we change our hyperparameters. And so more on feature splitting and feature families. Just to kind of give you guys some grounding on what we're thinking about when we think about these phenomena. Every feature is something we can think of as a direction in this embedding space, right? So we think that sparse autoencoders are kind of learning to disentangle a bunch of semantically meaningful directions in embedding space into a more sparse direction where they're also all orthogonal and thus easier for us to manipulate. Feature splitting is a phenomenon that's been observed before, such as in the Anthropic paper, and it occurs when you change the sparse autoencoder capacity. So in a smaller sparse autoencoder, because there's just less features to be learned, the model will learn more general features so as to cover the amount of semantic space it has to cover. But if you give it a larger SAE and more capacity, then features will actually become smaller in topic and cover less semantic space. And so you'll see this phenomenon where larger sparse autoencoders split features into their more granular subtopics. If you have a top-level black holes feature in your smallest SAE, then you might get a black hole spin feature and a black hole superradiance feature in your smallest SAE because there's just more capacity for it. We also found the existence of feature families within a single sparse autoencoder, and we think we're the first to observe this. This is more of a hierarchical structure that occurs not between models, but in a single model. We find both a really a denser parent feature, so something that's more general and fires a lot more often, and then also some more sparse child features. An example of this would be in SAE 64, our largest model, we found both a black hole feature and then also a bunch of features dealing with, black hole mergers, black hole superradiance, and all of those kind of occur in the same semantic space. What we found is that this parent feature will actually fire alongside every single one of the child features, but the child features don't really fire with each other. And so looking at this parent-child hierarchical relationship gives us a really natural way to group together these features in a meaningful way. Here's kind of another look at feature splitting. So we, again, have these recurrent features that are appearing in every model. On the left here is an example with O-type stars, and I've plotted the color as cosine similarity. As you can see, the feature appears in every single model we train with really high cosine similarity, so that's a really strong sign that you're getting the same features in the same semantically meaningful directions, no matter what SAE you train. On the right side, this is a little more involved, so bear with me here. This is a kind of group of features that all kind of span the periodicity semantic space. In orange, I've highlighted the periodicity detection or periodicity top level feature, and that appears in all three of our models. Starting with SAE 32, which is our kind of medium-sized model, we also get periodic orbits and three-body problems. That doesn't exist in our smallest SAE, but it does exist in the largest SAE. And so that's the kind of feature that appears at the level when you expand your SAE capacity, and then you get thousands more new features that also take up new directions in meaning space. And then in SAE 64, we get quasi-periodic oscillations and blazars, and that's a totally new feature that is under this umbrella of general features, but doesn't really appear in any of our smaller models, and also has really low similarity with the models that with the features that other models learn. And so this is really exciting because it kind of shows us the ways that changing your SAE capacity also changes the features you learn, and can maybe help us understand, what's the right SAE size to use for the what kind of problem. And here's an example feature family. So this is kind of done with the graph-based clustering method that I alluded to. Looking at, we see that the parent feature optimization techniques fires by the strength of that arrow with all of these child features, and the child features kind of have relationships with each other. Sometimes they're co-occurring, but a lot of these child features, could be in their own paper without any mention of any of the others. But it's interesting to see that these sparse autoencoders recover this hierarchical structure where smaller features or technical terms are mapped to a big picture like domain umbrella. This is kind of technical detail, so I won't get into it, but the way we identify these phenomena in our features is by doing, for splitting, nearest neighbor matches via cosine similarity, so moving from the smallest model to the largest model and matching the nearest neighbors. And then to do the feature family, we compute the co-occurrence and activation similarity matrices, which basically tells us, what sorts of abstracts are these activating on and how similar is that. And then we construct graphs and maximum spanning trees, and then construct subtrees via depth first search. And so we find that these feature families, just like the individual features, are also interpretable. Here are two examples of really great feature families that we found. On the left here is pulsar astrophysics, and there's a bunch of really relevant terms such as interstellar scintillation in pulsars or pulsar conal emission geometry and altitude. And so you can imagine that if you wanted to do search, which we'll get to, you could either manipulate all these individual little pulsar features, or you could take the whole feature family and manipulate that all together and be able to kind of get the whole broader semantic space without having to do every individual feature by hand. On the right is astrobiology, and again, we have a bunch of interesting features that have their own interpretability scores, and then also the astrobiology feature family is highly interpretable on its own. And we find that for the best feature families, ones that really make semantic sense, the feature family is equally interpretable, if not more interpretable, than any of the group of the child features. And then here's something else fun. So we had this kind of thesis that if you looked at the feature graph on like the co-occurrence graph and you organized it by feature family, you'd have this really nice block diagonal structure. And that turns out to be true. So on the left is for AstroPH, and on the right is for CSLG. And we've organized the co-occurrence matrices by feature family and put the parent feature all the way on the right. And so you have this really, really nice block diagonal structure that's really visually appealing, but also really communicates this kind of hierarchical relationship, right? You have your top level feature that co-occurs with all the children, and the children are this kind of blank space. Some of them co-occur with each other, most of them don't. And it turns out you can really rearrange the whole, 9,000 by 9,000 co-occurrence matrix into blocks like this. And then finally, here's another fun thing. We also found features that occur in all of our sparse autoencoders within a specific domain, like I just alluded to, but what about between domains? So computer science and astronomy, as our presence here at this workshop indicates, obviously have some amount of overlap, but how much of that is really recovered when you're training sparse autoencoders over two totally different corpora? Well, it turns out that our SAEs, even though they're trained on totally different subsets of papers, they tend to learn really similar features that allude to the same semantic meanings that are kind of in the overlap space between astronomy and computer science. For example, in astronomy, we have transformer features, we have AI features, we have Gaussian processes features, and we also have best matches to all of those in the computer science sparse autoencoders. And so this is another sign that we're learning really universal and semantically meaningful features from our sparse autoencoders.
So yeah, so tying this back to the whole point of what we came to the workshop to do, which is sort of research astronomy and now computer science with LLMs. So we wanted to provide a way for people to be able to use sparse autoencoders, more particularly the interpretable features from sparse autoencoders to better control their search outputs. So Mikhail said this before, like often when you're researching a new topic and you have some very fuzzy idea about what you want to look for, it's very hard to type that into a query which is semantically meaningful and is going to give you a good semantic search. Or in a different situation, you might have two very disparate topics, so hierarchical VQVs and planning and transformers. And I've found that when you go to Semantic Scholar or any of those similar places, you might either get a lot of papers related to hierarchical VQVs or a lot of papers related to planning and transformers. So basically, we wanted to provide users with sliders or buttons or knobs, which they understood what they did and gave a very intuitive way to like re-rank search results. So I'll play this video, which is actually what spurred this idea. This is doing a similar thing with SEs trained over a diffusion model. So you can imagine live like twisting a feature for rustic or Elizabethan furniture or something like that and seeing your results change in front of your eyes. So this is what we wanted to kind of accomplish with the search stuff so that astronomers and computer scientists and scientists in general could sort of reshape their search results without having to prompt engineer in a very hacky way. And we thought we now had the ability to do this with our SAE features. And so here's a quick demo. So this is the web app we built. I'll put this 1080. So yeah, this is Search, which is very difficult to pronounce, but we like the name. And so basically this is live doing a semantic search. It's embedding your query and doing the very basic like vector matrix multiply, which gives you your results, and you can click on all these. This is all through our corpora. But on the right there is where we have our SAE features. So in this particular example, those are the SAE features that are most active. And so you can see that they're quite related to the topic we're doing. And so what we give the user the ability to do is downweight certain features or upweight certain features and re-rank their results. And so this is like quite a nice interface for people to be able to go in and like intuitively change things about the query that they want. So if we have a look at another example, I think I'm doing computer science here. So yeah, it's a similar thing. This one is particularly close to my heart because this is what my honors is on. So the semantic search is great, and we'll probably add the additional stuff that we've done with hide and cohere re-rank and stuff to this in the future. But yeah, the key benefit is being able to control those SE features. And so you see if like we might upweight this like adversarial attacks feature to 1, and that basically makes all the papers go to adversarial attacks. Ideally, you'd be somewhere in between. And getting a feel for how much you need to change those features is probably something we need to work on more. But yeah, the idea is there. And then one final thing you can do on this page is not only change features which are active, but search over all the other features. So you might want features which haven't actually been lit up in the sparse autoencoder for that particular query. And so you can go down to our little box down the bottom here. Sorry, I'm a bit slow with my demo in real life. I should have sped it up. And search for features which we've labeled with our auto-interp methods and add those. And then again, same idea. You can upweight that. So initially it's 0, but you can press that and re-rank. And if you go into those papers, you'll find that the causal graph discovery stuff is actually quite present in those papers. So that's cool. And then we've got this feature visualization tab, similar to sort of what Anthropic's built. And so you might go find, I want to look at this circuit feature in more detail. So we've got the interpretability metrics, we've got the abstracts it most activates on, which gives a quite good intuition for what the feature actually is. And then some statistics like the features it's most correlated with, like its activation distribution, and the features it co-occurs with most as well. For AstroPH in particular, which we're just implementing now, we also have the ability to look at features in the smaller SAEs, which are most similar to this feature. These are the largest SAEs we've got here. And so you can see that like the best match in the smallest SAE and the best match in the second smallest SAE are very, very close to the feature in the larger SAE that we've got. So that's quite cool for getting intuition about what these features are. And then finally, we've got a family visualization tab. So as Christine has talked about, we've gone through all these features and grouped them into sort of like these directed graphs of parent and child features. And so just here, like it's probably more general features, but you can get an idea of what sort of features are firing within those things. And I think the next step is to just give people a slider to be able to change the whole family at once, which shouldn't take too much work. So yeah, that's our search demo.
And then, so how do we evaluate whether search, which, looks really cool. We have this cool web interface. It's fun to be able to control your search with sliders. But how do we evaluate whether it's actually an improvement over search? So what we did was we evaluated the search interventions on specificity and also the causality. We took 50 queries from both machine learning and astronomy. For astronomy, we were fortunate enough to have wonderful real queries from our ecosystem, thanks to the wonderful Slack bot that was deployed earlier this year. And then we modified each query by up or down weighting the most interpretable features, and then getting a language model to guess what was changed. This is basically a self-consistency test, and also a test of how big the modification is, right? So, for example, if I have a query about black holes, and I really want to know more about galaxies, we would turn up the galaxy feature, and then we would ask a language model, given this original set of retrieved results, and then another set of retrieved results, and also all these features that you could have chosen from, which is the feature that's turned up? And so hopefully the language model and the results would be, kind of cohesive enough to be able to say, okay, the galaxy feature has been turned up. It's not the exoplanets feature. It's not any of these other features. I know what has been changed. And that's kind of a test of how, specific and causal are these interventions. We compared it to just basic rewriting. We had GPT-4o rewrite the queries that were given to either upweight or downweight specific features, basically the exact same features that were in the original sparse autoencoder interpretation. So, for example, if the feature was galaxies that we wanted to upweight, we would also tell the language model, please upweight galaxies in your query. And then we compared the accuracy of the language model interpreter, so the one that's saying, how am I guessing the correct feature that has been manipulated between the original and the improved retrieval results. We compared that between the query rewriting and also between manipulating the features through direct SAE feature intervention. And so on the bottom here, you can kind of see these Pareto curves almost. The dark blue is the downweighting and the light blue is the upweighting. The curve itself is from SAE feature interventions, and it's this nice curve because you can really change how much you want to intervene. Obviously, when you intervene to one, like Charlie showed, or when you intervene, to really high values, you'll pretty much change the whole query and you'll get totally new results. So those might be really obvious to the language model because it totally has changed the results, but it has low fidelity to the original query, so we don't really want that. What we really want is to strike a balance between how similar are we to the original query and how accurate and causal are our interventions. And so we show that with individual features, in both cases, the SAE feature intervention is a Pareto improvement over just traditional query rewriting. The right panel there is for feature families, and so we've done just kind of a naive test with feature families, upweighting all features the same amount, and we've shown that feature families do an improvement for when you want to downweight, but when you want to upweight, putting in the general feature into the query and rewriting it is still slightly better. We think that we can do better if we come up with more clever ways to upweight all the features that's not just upweighting everything uniformly, but that's kind of work that we have to do in the future. And our current theory is that it's easier to do downweighting with feature families because if you want to downweight, for example, black holes, really, if you want to get a good downweighting, you'd have to go through and downweight every single black hole related feature. And in a query about, black holes and galaxies, if you want less black holes, you'll really have a lot of features related to black holes firing. And so being able to do that on a family basis kind of helps you automatically turn down a bunch of related features.
Yeah, so just to wrap up, so basically we're pretty excited about this, not only the semantic search stuff that we've just gone through, but training SAEs for embeddings looks very promising. I've had some really good, we both had some really good conversations with people here already, like Marek, about how you might use these things for scientific discovery and coming up with new ideas and looking at patches in the embedding space that science hasn't really explored yet. And so that would be really cool. You can track scientific ideas over time. You can do all this sort of stuff with them. But yeah, the search stuff is really a very, very relevant use case to what we're doing. We think that having these interpretable features for people in search, in many other applications over embeddings, there's so many different things you could do with them. So if anyone has ideas, we would love to chat about them. But yeah, thanks for listening.
Hi, nice talk. Two questions. I'm trying to see the use case for this, so it's clearly very interesting, right? So one thing I can imagine is there is an expert user who doesn't get the results that using he or she is looking for, and then adjust knobs to get the results, and that's fine. And then maybe select black holes in maybe this galaxy or whatnot, right? But the second use case might be that through tweaking, the user discovers a set of some settings which can be used for subsequent queries. So is that is that crazy, or is that what you
No,
have
it's
in
a
mind?
very good idea, and in fact, John has previously floated this. So you might imagine like initializing a user. So like maybe we have access to all their archive papers or something, and I think from what you're saying, we could like give them a set of base features which are kind of turned up. So my archive papers would have like the sparse autoencoders feature turned up, and circuit discovery turned up. Christine's would have like galaxy formation and that sort of stuff. And so we're already initializing user in a good place. So that could be a really good way to like tweak stuff.
And you can imagine doing that not just for like, oh, what specific subfield do you work in, like circuit discovery, but also we found some more high-level features that kind of correspond more to the nature of the science being done. So for example, turning up a theory feature. If you're a theorist and you really don't want to see any experiment papers like ever, I don't know if that'd be good for you, but there are a lot of really interesting abstract features that could be even more useful for this personalization.
Yeah, so just a question of clarification first, and then maybe a follow-up. So when you're describing your hierarchy of features, right, you said the generic ones, and then when they fire, there might be others, some of which fire with them, but exclusively. Were you just trying to discover the hierarchy, or were you trying to induce a hierarchy?
Yeah, that's a really good question. So the idea from the hierarchy kind of just came out of initially visualizing the features and when they co-occur together. So I guess like in this matrix that I showed here, which really shows the hierarchy really clearly, we have tried to induce it by doing the graph-based clustering, right? We're clustering it in a way that kind of induces a parent-child relationship. But I would like say like very confidently that this is also natural to the features themselves. We do see like a more general feature and a bunch of child features. And that's also kind of motivated by the idea of some features being universal or only appearing in models when you give them enough capacity to. I think one like hypothesis I have for why these features appear is not necessarily that transformer models or like sentence transformers are so smart that they know all these features kind of cluster together, but also that these abstracts, you know, if I'm motivating a paper on galaxy evolution and I'm going to talk about a really specific part of it, first I'm going to talk about the broader problem of galaxy evolution, and then I'm going to speak about my specific subfield. And so there's naturally a subfield feature and a broader field feature there.
No, that's fine. I didn't mean to, I'm not questioning why they exist. That's fine. I had a specific thought, which is from the morning presentation, they were trying to induce these hierarchies in their audio encoding by saying at a higher level, we want something to do with lexical units or phonetic units, and then the details about the speaker or the emotion or whatever else. So could you do something like that? Train your L0 equals 16 model first, and then use its activations or whichever features it turns on to constrain the L0 equal 32 model and say, you got to use these, plus you can use 16 more. And then use that with the L equals 64 model and say you can use whatever was turned on in the first, this 32 model, plus you can turn on another 32. Yeah. So it would be a different optimization problem, but that way you'd more or less force a hierarchy. And then it would be perhaps, I don't know if it'll be easier or harder to implement, but you'll get your hierarchy.
Yeah. There was like a really recent paper on like stitching together SAEs of different sizes. Is that what you're gonna say? Like making Frankenstein sparse autoencoders, right? So like you take the smallest one and then you train a medium one and you tack on all the extra features. And they found that I think it seems to work pretty well. There's like a subset of features that really do improve the performance, and those are kind of new concepts, and also a subset of features that hurt the performance, and those are ones that have kind of already been discovered. So people have tried to do this sort of like hierarchical construction of sparse autoencoders. But I guess I don't really have intuition for whether that would work explicitly better than just kind of letting the hierarchy come out of the model itself. Maybe.
And also, like, you kind of just get back like Matryoshka embeddings at that point, sort of like you're forcing the first n dimensions to be like very general features, and then the next n on 2, and then the next n on 4, and whatever. But yeah, I guess you could try it. Yeah.
I mean, in terms of the learning algorithms and what they learn, you may want to play a little bit with other things, because at least what you're doing right now is that set of features from which you choose 32 or 64, that's the same for each model, no matter whether it's 32 or 64. And if you do that, when you train the model with 16, it'll use those for something, and to say now reuse something else, it'll have to do a lot more of rearranging. So what you may also want to do if you do that is increase the number of those hidden nodes as well, saying you get the first set for free, and you can use 16 of those, plus you have another set to learn, and you can use 32. So if you don't like some of the original nodes that you were using in the 16, you can instantiate new ones. And some training regimen like that might the problem is that this now says you're going to monkey with the network architecture, so it makes it a slightly trickier problem in terms of training, but you might want to think about it.
Yeah. Interesting. Cheers, Sanjay. Okay, so I think we're going to hand back to who's next? Is it Sanjeev?
Hello. Yeah, so I'm going to talk about benchmark and evaluation. So basically, how do we evaluate a system where we have a new iteration of the system? We have made some changes. One way would be to just redeploy the system and then ask the users to come up with some scores. But then this is like the most accurate thing you can do, but it's not practical because of the long iteration, long time that will require. Instead, what you can say is we already have collected this data. Why don't we create some benchmark out of it? For example, if you think like there's some kind of a ground truth, and then you could test against this. So this introduces the idea of the gold question answer pairs. What we did here was to say, remember we had this Slackbot data where astronomers gave us some real queries. So we then tasked a few astronomers, like 5 senior and 3 junior of them, and told them to provide answers and also references, but without looking at the bot answer so that you don't get biased by them. And so as I explained in the beginning, this is a very laborious process and typically takes like 20 minutes or so, and if you're not an expert, even more. So currently we have reached around 40, but the aim is to do about 100. So we made a few choices as to, we filtered down the original set of questions based on the fact that we intentionally ignored the bibliographic ones because we think there are other better deterministic tools for doing this, or even questions that were doing like stress testing or bot capability and so on. We tended to focus more on research-oriented questions like the knowledge-seeking one or debatable topics and so on. And there's another thing, like there are some questions that like are trying to find out an answer, like a number from a paper, from a table that is embedded in the paper, and the bot is currently not capable of doing that, so we also intentionally ignored it, but that will be something really useful to do in future. So like the use case for this is we want to benchmark the system. So let's say we have a new iteration of the bot and we generate a new answer, then we want to compare it with the gold answer and say, is it better or not, right? Also, another motivation for doing this was by going through all this exercise, we are learning like new steps and techniques like we as humans are using to answer complex queries, and that can inspire changes in our bot. We can introduce those things in the bot. With that, I'll pass it on to Kira for showing us all the results with this.
Okay. Hello, I'm Kira, and I'm going to give sort of a brief high-level overview of what the deliverables from the generation side are before I get into how I use the gold QA pairs. So basically, this is sort of an example of how the different ways this chatbot could have been deployed. So the original one was using Rockfish to deploy it on Slack. So if you look up to the right, sort of just an example of query and an answer. Another way was implementing it using Jupyter Notebook, which is shown at the bottom. So the actual answer is highlighted in pink, and it's not as user-friendly as in Slack, but it is much easier to give like updates to the pipeline. It's how I implemented the new retrieval system that they were working on. But I'm currently working on a GitHub repository to release so that more people can interact and use the chatbot. But in looking how the improvements to the bot, I use these gold QA pairs to create relevance scores and just sort of compare to see all of the improvements. So basically what I did was I would take an LLM and I would give it the gold response that the astronomers came up with, and I would give it both the old response and the new generated, and I would ask the LLM to go through with a very complicated prompt and sort of just give it a score between 0 and 1, with 1 being exactly the same as the gold response as to how it was answering. So sort of the idea was the closer to 1 you are, the better and more similar and more relevant that the response was. So for example, this is just one of the queries, and the new generated response had a 0.85 relevance score, which is pretty similar and overall pretty good. but this is a little hard to visualize and it's a lot of words to read. So a better way of seeing this information is on this heat map. So this sort of looks and compares responses from the original chatbot that was deployed in the first trial against the new response scores. So with all of the new retrieval system, the hide, the re-rank, all of that. So basically on the bottom here, between 0 and 1 is the comparison of the old response to the gold benchmark relevance scores. And then along the y-axis is the comparison with the new response. So the aim of this was sort of to have as many counts in the upper left triangle as possible. So as you can see, there's still room for improvement in accuracy, but it is, the new bot is performing consistently better and more reliably than the original chatbot. And I think now I'm passing it back to John.
Thanks. And it looks like we're right at 2.5 hours and we're basically done, but this is just the final summary slide. Again, as you can see, we've kind of taken a detour through a lot of different concepts, all motivated by the fact that our aim is to make the scientific research process better, more natural, and just to give researchers better control over the discovery and the formulation of new scientific ideas. But of course, there are different ways that people can use AI and large language models, and so we've gone from very qualitative analyses that involve poring over small amounts of data to allowing LLMs to basically analyze their own scores and things like that. And so as you can see, some of these papers are quite mature and will be on the archive very shortly, and some of these are coming up in the coming weeks. But we hope that you'll take a look through our anonymized user interaction data that set the stage for a lot of the decision making, including the updated retrieval pipeline that you heard about, and eventually, motivations for what went into the SAE space search. We painstakingly curated these gold answers. These are, again, taking astronomers 30 minutes to an hour per question to answer. So we're not fully done with the corpus, but we do hope that will prove to be a really important benchmark data set. In fact, no such data set like that exists. All the ones that sort of have more than, of order a dozen questions are all basically synthetically generated. So we think that we're going to be the first to launch that. And I think it will be a huge boon to the astronomy community. In terms of code repositories, those, as well as the web apps, of course, are open source, and so you can go ahead and view them or play with them. And we hope also that you guys can give us all sorts of new ideas. We think that multidisciplinary collaboration is a very rich way to go and explore ideas and combine our expertise to build something that's greater than the sum of its parts. So again, I'm super grateful to our team, again, our all-star team here. Really guided and made this project come alive in ways that we didn't envision when we first started. So again, thank you so much to JSALT too for enabling this to be possible. We're extremely grateful for all your support. And I'll take any questions. Thank you so much.
Let me kick off with a thought, actually. I don't know if it's a question. The gold answers that you have, things like that, I know we'll share it with the community. It'll be freely available. I'm wondering if there is some way to protect it from being slurped up by web crawlers and making it into the next iteration of GPT, whatever. The reason being that if these can be held back, they're genuine test suites and we can use them. But tomorrow, if GPT-5 uses them, and we tested it, it'll look silly because it has read all the answers. So I'm trying to figure out is there a good clean way? Has anyone thought about it? If you just put a do not crawl tag in the web page, do these people respect it?
They do not.
Yeah.
Robots.txt is, I think there are a couple of well-documented cases of that being ignored.
Violated, okay, yeah. I'm just thinking we should think about this because, these data sets are quite valuable, especially human curated ones. So just a thought. I mean, you guys are the experts, so you'll figure it out. I was just thinking about it and yeah.
No, you raise a very good point. Yeah, I mean, training on the test set is all the rage these days. And so I think, part of the benefit I think here too, though, is, we're hoping to build trust within, say, astronomers, who most of whom are not used to using LLMs, and so they don't really understand the capacity, the capabilities, and whether or not memorizing a test set is a good or a bad thing. But we're hoping that by deploying these kinds of services too, we're also like teaching them to gain the right levels, like to calibrate the level of skepticism, and to understand the kinds of methods that are useful for circumventing any sort of just memorizing certain answers and knowing how well some particular benchmark might generalize to performance in other real-world applications. So we're really hoping that by educating the community in some sense, we also can be okay with the fact that we're probably going to have this data set immediately slurped up. But that you raised a very good point. Thank you.
Other questions? Come on.
So I guess question to the team who is working on it. So I didn't see any, one of the things that would come up in a situation like this is a confidence classifier, right? How do you decide the model doesn't know enough and say, I don't know? Did you investigate that?
Yeah, this might be good for the Pathfinder team to talk a little bit about, but I think the consensus evaluations, as well as some of the sort of the distribution of retrieval scores, which was also discussed, those generally, will point you into the right direction. But defining thresholds and doing things like that can always be kind of messy, especially when you're combining different strategies. The interaction between hyperparameters often makes things tricky. So I do think that we would like to have better. Thanks. So I do think that we would like to have, more basically user testing and development of these systems. We were talking about also integrating like personalization and things like that in a way such that maybe certain users tolerate, So, okay, let me just back up and say that scholarly identity is, for example, something that we haven't talked much about, but can easily be integrated into our systems, whether it's, I don't know, training LoRa's or doing whatever else for individuals. You could imagine that you have a semantic scholar page or like an ORCID in astronomy. Basically, everybody has that. And that can be helpful for defining the kinds of thresholds and things that you're happy with. But whether or not you call something confident or like you're willing to accept a certain level of speculation, that also will heavily vary by user, right? And we saw that in our thumbs up, thumbs down scores. Like some users were just very unhappy with any slight deviation from what they were expecting, and other users were much more forgiving.
So a quick comment about robots. First, I looked into this. Turns out robots.txt sort of applies at the whole domain level, and that's very bad because you don't want to maybe you don't want to block out all of GitHub or something. So it's actually hard to protect your data with robots.txt. So I had a question about the way the gold data was compared to the previous data. Was it the LLM that was doing that? So how was the relevance score?
Are we talking about this right here? Yeah. So maybe so I realized that the word relevance score kind of got overloaded. Actually, Kira, do you want to take this or do you want? You just, all right.
So will you repeat the exact question?
Yeah, so basically how was the score computed between, in any particular
So basically what I did was I would give both responses, so like the gold benchmark or either the new or old, to an LLM. I was using GPT-4o Mini, I think.
Yeah.
Yes, GPT-4o Mini. And basically I gave it this very long detailed prompt, which I don't have up here, but it was similar to what Mikhail showed earlier, where I would give it like between like 0 and 2 means these answers are not the same, they have no similarity. And then I also gave it some description. Sorry?
It was the exact same.
Okay, well, I don't know, that was pretty far back.
Okay, yeah.
But, I went through all of them and I also gave it instructions to like answer based on like precision, accuracy, how concise it was, things such as that, and then told it to just compute it. And also sometimes I had it explain itself. So like when I was first testing this to see if it was accurate, I would have it give me reasons why it gave that relevance score, and then I would show the responses to like other people and be like, do you agree? Like, what do you think?
Okay, yeah, I mean, that makes me a little bit scared. So I don't know if there's other examples of these large language models like producing numerical results, since their outputs aren't normally like that. But the other question I had is, was it possible to do like a simpler baseline and compare it to that? Like just a simple, I don't know, like a blurt or a blue
or something like that instead of using the large language model?
The numerical response concern is like, that's definitely fair with the models we had like a year and a half ago. But do you want me out the front? Oh, the camera. Hello, camera. Yeah, so the numerical response concern was valid, I'd say, a year and a half ago. But now we're at the stage where like these language models are trained on enough structured JSON data and instructions where the actual instruction contains information about what to output, that's no longer a concern. So if you're scared about like, I don't know, making up numbers or things being output in the wrong way, then like I would say that's less than a 1% fail rate at this point with 4.0 and 4.0 mini. And then in terms of more a basic comparison, I would say there's not really a way in which to do that in a principled manner without getting either a human or an LLM to judge. Like something like cosine similarity doesn't capture the aspects of the answer that you want it to. Obviously, the LM is going to output something which is very semantically close to the query. The embedding just doesn't capture enough information to say this is a better response, this contains exactly what we need. So while I imagine you might get a little bit of signal from using something like cosine similarity or keyword matches or something like that, it really is about like tying that information together, which you need like a fair bit of complex chain of thought reasoning to do, either through a human or an LLM. So I definitely like back here at doing the evaluation with the LLM.
Yeah, and I should also mention that this similar type of methodology was used to extract scores which were reported in the SAE portion. So when you were looking at things like the F1 score and so on, like the specificity, all that is sort of evaluated as an LLM. So it does let you, really scale up the idea of using some sort of, some sort of judgment process, which is not a human, and presumably is constant over time, but obviously falls prey to other sorts of biases.
Sorry if I missed maybe a detail and ask a redundant question here, but so first of all, I think it's awesome to see this used by real users. It's a real application. And you started with a very simple pipeline for information retrieval, and then it evolved into something really big, right? So because of this complexity, have you actually tried to, instead making it more complex, feeding this kind of information that you use there to filter the data into the large language model to guide it to how to judge the different documents?
Sorry, so
I think you had something which said, oh, we try to find older documents that are more recent or in the right time frame, but did you also provide the information from when the paper was?
Do you mean like metadata?
Yeah.
Yes, indeed. So yeah, that did form part of the updated pipeline, and we do think that in certain cases that actually becomes much more relevant. So people might ask some questions like, oh, what were the biggest discoveries in exoplanet science in the last 3 years? And you would certainly need that kind of a thing. And indeed, so time weighted or weighting by citations, basically filtering on say actual keywords, because when you submit to a journal, you actually have keywords, or things like this, filter by author name. Those kinds of things exist as well. So I think that answers your question in saying that we did take that into account.
If you would not have changed your strategy but added this meta information, or did you have this meta information in there already in the first pipeline?
Ah, I see. So you're saying no changes to the semantic search in any sense, only just having that.
Yeah.
No, I don't believe that was evaluated by itself. I mean, using simple things like TF-IDF, or BM25, those, were evaluated. Those plus something like this simple filtering, we haven't done.
In front of the camera.
Yeah, we did add the time and other stuff to TF-IDF. but wasn't a significant improvement. In fact, I'd say it was less than the difference between BM25 and TF-IDF.
Yeah.
So I think that's more in cases of like, we had some other benchmarks which we didn't talk about. So for instance, there was a benchmark which were entirely temporal related questions. So like the one John just said, or like last 2 decades concept, most important papers in that. And we constructed those by hand. And so obviously time weighted helps significantly there. But in terms of like the overall types of questions like single paper and multi-paper benchmarks we had, it wasn't that important. So we did tack that onto just your basic like TF-IDF search, as well as basic semantic search. But obviously there's many, many different combinations of that when you like start plugging and playing with different methods. But yeah, not a hugely significant difference.
So in summary, what you say is getting the right documents is more important than actually providing the metadata. But now the alternative question is, if you remove the metadata, how much does it hurt?
Yeah, so I think it's like quite bimodal. So 90% of cases, it won't matter at all. And then in 10% of cases, it completely matters 100%. Like it doesn't matter how good your semantic search is if you can't put in the ability to change things by year or like search a specific author's name. So yeah, I would say like the main benchmarks we had, it doesn't affect much because 90% doesn't really affect. But yeah, in those ones where it is about time or it is about filtering by an author, then that metadata means you go from 0 to 1 basically.
And also just to add to that, like if we would think back to the slide on what type of questions user ask, at least in our data set that we have right now, there were questions on the bibliometric search, and a lot of those questions were like Charlie asked, referring specifically to give me papers between year X and Z, but it's also important to distinguish that different tools exist for different purposes, and you can use something like ADS to find the paper in the specific year if you want to. So I think a lot of limitations on the retrieval side can be resolved in a practical use cases when you're telling user, hey, we can do this, this, and this, and this, and that. We can return a really relevant paper, but just bear in mind that the system is not designed to like be able to say, oh, this paper was published between August and June of 2024. So it's also, I think, sometimes it's worth balancing out, aim towards more relevant papers and just provide more information to the users of what the specific tool was designed to.
Yeah, I totally agree. Thank you.
So I thought Thomas was proposing something a little more radical. I thought he was proposing that now that you've built this big complicated system, run lots and lots of queries through it and just take its output and use that to fine tune the simple system. And that way you don't need any of this. And I thought that's where you were going with it. Use it to generate synthetic data. And then
I see.
Sorry.
I see. Like
he wasn't, but that's what I thought he was doing. Yeah.
Yeah, no, that's certainly a thought. The other thing, maybe, sorry, just going back to though, is that and Alina kind of touched on this though, is that we kind of joke that in order to be an astronomer, you have to know how to use ADS, the Astrophysics Data System. It's like one-to-one mapping, because it really is essential for doing things like literature search, understanding, other papers and methods and things like that. And ADS already exists. This is an excellent baseline. We had the PI of ADS come and give a talk here, Alberto Akomazzi, and it's really remarkable all the sorts of things that they've already thought of and developed and tested over decades of work. And so, in some sense, we need a way to evaluate against that as well. But in another sense, we're not trying to replicate that wheel, right? Like we will happily, and Pathfinder does, direct you to say, let me ADS that for you, right? Like here's the exact query that you should just drop right into ADS, because for certain types of things, it just is better to use that, and it doesn't really make sense to have a semantic search. So. With all that said, maybe, I don't know, a few years down the road, we really should integrate that and come up with a proper way to benchmark against that as well. So I appreciate the comment.
In fact, this will then make Jason's statement even more true, which is that you'll enter into this queries where you don't quite know how to use ADS. Like, I don't know if I can do this, let me try this one. So Jason, going back to your point, you often query for things with this when you don't know exactly what to query. Do you want to go back to your question though? We didn't finish answering. Okay, all right.
There was a feeling that the LLMs actually maybe
Okay, you're saying the LLMs are good at it, so you want to elaborate?
Well, I can elaborate and give a specific example. So I think when Jason was saying, like, what do you do if you don't know how to phrase something into words, yet you still want to have relevant search results for it? Like if you're exploring a new concept and maybe somebody's given it some new piece of jargon and you didn't know that, then will you be able to find that kind of work? And so we have tested this a couple of times.
I just asked Jason, by the way.
but we did test this, which is why I want to kind of share it, right? Like for instance, you can say something like, oh well, what are ways to explain the fact that galaxy rotation curves are going too fast? And typically you would invoke either something like dark matter, or you would invoke something like modified Newtonian dynamics, and so on. And if you look in the embedding space on Pathfinder, it actually has two clusters in where those two regions are dominated. Now, if there's only a single paper, and I think this gets at the idea of the assumption that the embedding space must be somewhat dense enough in order to get a useful consensus kind of evaluation out of it, presupposing all of that, then I think you actually can formulate and find those kinds of responses in a coherent way, and you can have a degree of confidence about how well the model was able to recover those. So
So I have a follow-up question. So I don't know if it happens in your field, but sometimes in our field, the papers, we try to put like very fancy words, like new concepts that are not so new. So how do you deal with those things? I mean, something that is just, for example, in the title mentioned that is novel, but it's exactly the same concept or the same thing as mentioned, I don't know, perhaps 10 years ago or something like that.
Yeah, I think that actually probably is a failure mode of the system that we need to get around. Like for instance, like I imagine that most papers when they come out will claim that they are state of the art and so and so. So saying what is the state of the art and so will give you a paper from like 2015 or who knows? Like it doesn't really mean anything. Presumably, I don't know, like. I can only speculate. I mean, like if you have something like an inverse document frequency like term or some sort of way to normalize against that, which the model or the system already knows how to get around, or it gets around sort of what you were just describing. I mean, I'm hoping that these kinds of things are innately or implicitly learned, but I really don't know if there's a concrete answer to that. I imagine it could be a genuine failure mode. Yeah. I don't know. Anybody on the team want to comment?
Searching right now for like what concepts in astronomy have been rediscovered over time.
Yeah, or just renamed. I mean, things get renamed all the time, yeah. Like nebula used to be a galaxy.
Okay, you put this thing on GitHub, and I'm a cell biologist, and I want to adapt your system to my domain. What do I have to do?
Download some, generate a few API keys, make a conda environment, run Python app.py, something like that.
Well, I don't have like all the great stuff that astronomers have,
like you don't have all the open literature.
Well, that's one issue maybe, but also you're making use of some ontologies and things.
Not a priori.
No,
we just have we just have a big tar.gz file archive.
Yeah, okay. So basically, I would need to collect a lot of papers.
Yeah.
You have ADS. I'm maybe getting the acronym wrong.
Oh, ADS. Yeah, ADS now. I mean, you can't kind of. Yeah. So that's more through an API to access a lot of it stuff. I don't think you can bulk download everything in ADS. But presumably bioarchive or whatever analogous version of where the literature is stored. I think that's really the single. You need that, and then you need a way to convert those into some embedding space for which you might put,
Okay, so
pony up some money.
you're saying basically you've built something that's super general, could work for every area of human inquiry, and you just happen to have tested it on astronomy.
Well, that's what I would say to a VC, but that's not what I would say right now. To a fellow skeptical scientist, I would say that we think we understand some of the use cases in astronomy for which we know approximately what fraction of the literature really is in there, and we've noticed that many of the concepts we want to find do exist. But if that completeness cannot be guaranteed, if you're You know, if the publications are kind of scattered across like 40 different journals, half of which, you know, never ever allow you to view any of the text, then I don't know where you would start.
Well, that's an issue, right? But it's not the subject matter. So
Yeah.
basically, if I'm a biologist and I want to do this, I need data, and I can still use your evaluation metrics, but I need humans to provide
I'm
data
sorry.
to find out if it works.
Right, so the internal evaluation metrics will certainly need to also be redefined or you know, basically reconstructed. So this was again, so like the multi-paper and the single paper sort of recall metrics were ways of saying like, can I recover, you know, effectively query paper, you know, citation pairs. And so those are things that you would, you know, presumably you could regenerate all that.
Yeah, you would need ground truth from humans on the new data, if I understand right.
Yes, some of them are coming from humans, some of them are generated by LLMs actually.
Right, which makes it
for
easier.
internal testing, yeah. But,
Thank you.
Yeah, thanks.
Good news. A new era of science is at hand. Yeah.
Now, I was just going to say that it ultimately comes down to, can you get a corpus and can you vet the corpus in some way? The methods themselves are quite generalizable and the code's all there in the app. So.
Yep, thank you.
No, I would be a bit more pragmatic. If I were the VC, I would note that you need annotations. For example, one of them is probably pretty standard. You mentioned the astronomy terms, the AUT, UAT, whatever it was a three-letter acronym. Yeah, UAT, right? So I'm sure there's an equivalent for that in cell biology. Most librarians created these things decades, if not centuries ago, to try and keep track of exactly things like this. So you'd need that. Some of the things you had human annotations for, like extracting these questions out of things where, like Christine talked about, if these 6 papers are cited in a survey paper with a claim attached to them, then you make a query out of that. So those are the kind of things that the resources that you'd need. So what might be good when you guys write up your technical report is to sort of have a template that says, these are the data resources, these are the annotation resources, these are the evaluation decisions, and so on and so forth. And some sort of, basically it says, if you want to replicate this in another field, these are what you need to put in. And a large archive of papers is just one of them. I think you guys did a lot more that would need to be redone.
Yeah, that's absolutely right. So yeah, no, thanks for pointing that out. So I think, yeah, exactly. So in terms of all the the deliverables or all the things that became the web apps or the code bases and things like that, the bare minimum you need is what Kartik just said. But in terms of being able to replicate also the trust building studies, the kind of things that we embarked on these past 6 weeks, indeed you would need a lot of personnel.
All right. Yeah. Other questions? We have a few more minutes. Hansa, come on.
So this is a great work, guys, but it's still about text. So it's like kind of classical NLP. There is lots of information that is in the papers, like the tables, the graphics, the references even, and there is like so huge amount of information outside of the papers, like the measurement data, the radial telescopes, whatever. You guys know this much better than me. So probably this cannot be taken into account during a 6-week workshop. It's like lifelong work. But if you could pick one thing that is either the easiest or the lowest hanging fruit, or the one that is the most requested by the community, what is it? What is the next information that you would add to your work, in addition to the text?
I think probably the most important one would be multimodal search and embeddings, basically going over the concepts that are represented in key figures within papers. This is because in astronomy, almost all key results are disseminated in figure form rather than in table form. We don't tend to have many common benchmarks or whatever. It's not really about methods and stuff in general, right? It's about random physics and things which can affect all sorts of different phenomena. But oftentimes you will have a variety of figures which and rarely will you see the same figure in many papers. I mean, there are a few figures which will show up, types of figures, that people will often see. But a lot of times astronomers try to tell a story through the paper, which involves pulling up a whole variety of figures, each of which just substantiates a part of that narrative. And you're really missing out, we're really missing out when we try to parse these papers without access to the figures or a good way to understand what's going on there. Now, I think that there's been a lot of progress made already, so I can envision this being quite realistic. Even now, it's probably worth taking a stab at it if we have more time. So
Okay,
indeed,
okay.
yeah.
Yeah, thank you.
Yeah, thanks. Thanks for helping us think about the next direction.
One more. All right, so thanks to John, thanks to all the people on the team. Again, another excellent presentation. All right, let me set us up for tomorrow. Here we go. So this is the agenda for tomorrow. So we adjourn now at 5. We start up again at 9 o'clock tomorrow. We again go 9 to 5 with a half-hour shift. So we'll start off with technical presentations. First, there'll be Marek's team on sign language, and then Jason's on democratic discourse. And then we'll close out with a little section, the coda at the end. So again, thank you everybody for persevering through the day. It's been a long day. Get some rest. Come back bright and fresh tomorrow. And for all our out-of-town guests, I will be here at 6. We can go for dinner if you feel like company. To everybody else in the workshop, if you feel like joining us, do the same. We will meet, let's say, not on this floor. This is the basement. The floor above, the main level where we come in and out of the building. So let's just meet at that door around 6 o'clock and go for dinner somewhere nearby. We can decide where based on how many people show up. All right? Okay, so see you all tomorrow. This one is working.